Hello and welcome to this full course on Generative AI by Intellipaat. Generative AI is a branch of artificial intelligence that creates new content. It can write stories, paint pictures, compose music, generate videos, or even produce human like voices. And the most fascinating part? All of this starts with something as simple as your description, which we call a prompt. You just tell the AI what you want and it creates it for you. Behind the scenes, these AI systems have been trained on massive amounts of data. By learning patterns and connections, they're able to generate content that feels fresh, creative, and sometimes so real that it's hard to tell apart from human made work. And what you're seeing right now is only a small glimpse of the massive shift happening worldwide. Global corporations and startups alike are in a race to build smarter AI agents, next gen chatbots, and tools that feel almost human. The generative AI market has already crossed tens of billions of dollars and is on track to reach the $1 trillion mark within this decade. But here's the reality: skills that were in demand just a few years ago are becoming obsolete, and the people who adapt fastest will shape the future. That's why learning generative AI today isn't just a smart choice, it's an absolute necessity. And to help you with that, we have built the most practical and beginner friendly generative AI full course. In this course, you'll not only understand the core concepts of deep learning but also master generative AI models, transformers, and autoencoders. You'll get hands on with powerful tools like LangChain, Hugging Face, and MCP servers, all while working through simple real world examples. So, without further ado, let's get started.
There was a time when machine used to be like an assistant. They followed a set of instructions and they could only do what you told them and exactly how you told them. And every task had to be broken into clear pieces in detailed instructions written by a programmer line by line and rule by rule. And if you want a machine to calculate something, for example, if you have coding for a calculator, you have to write a program for it. And if you want to sort a file, you have to write another program for it. Even the smallest task for the computer needed a manual guide step by step and rule by rule that the programmer has to give to the computer in order to execute the task. But now, in the era of an internet where AI is booming, the world is changing fast. We are stepping into an era of a machine where you just don't have to give the machine the instructions step by step. They understand what you mean. And this shift is happening because of something called generative AI. But what is this generative AI? Generative AI basically analyzes the input that you basically give to it and produces a customized output according to you. For example, if you're giving it a scenario where you have different conditions, so it will basically analyze all the condition and will generate an output according to your scenario and the conditions that you have given to it, and will generate a customized output for you. But when we talk about artificial intelligence today, especially generative AI, it's important to first understand what actually makes it different from earlier form of AI we have been using. We have already discussed that we have to program for everything. Like for example, if you want to build a calculator before, you have to manually write a code for it. But in today's world, you don't have to write a code for it. You can directly generate this code from the generative AI itself. You don't have to manually write anything in your code. Let's compare generative AI with earlier forms. For example, generative AI, it is a creative generation tool. For example, you can use platforms like Dora to immediately build a website that used to take a lot of time when generative AI was not there, and it is adaptable to new tasks. For example, if you have given an input to it and it has generated an output for it, but you want this output to be customized again, you can again give a set of instructions to it and it will generate a new output according to your customization. Now let's see the earlier form of AI. It was a rule-based learning method and it performs specific applications only. For example, if you've written a code for calculating something, so it will build a calculator itself only. Now let's see the evolution of AI from weak AI to AGI and super AI. Let's start with weak AI. Weak AI is good at one specific task. For example, in Netflix recommendation system or Siri settings alarm for you, that you have set an alarm and it is good at just this task only. And this recommendation was able to give you the recommendation based on your previous watches. Now moving forward to AGI, that is artificial general intelligence. It's like human intelligence that can learn and do things. For example, a robot can code in the morning, teach the kids in the afternoon, cook dinner in the evening, and write the music at night. And it is able to do all the tasks efficiently, like coding, teaching, dinner, and the music. And it is not like the specific task one, like in the weak AI, it was like designed for a specific task. Like Siri can't do anything, but a robot can. Now moving forward to the super AI that is smarter than the humans in every way. So basically, this super AI consists of a huge documentation that consists of everything, that all the case studies had been fed into it from Wikipedia and other platforms, Google, Reddit, and it can read all the data and perform the best out of it. Now let's move forward and see the categories of the AI. At the very first level, there is one non-generative AI and the second one is generative AI. So what is non-generative AI? Non-generative AI is used to analyze the existing data. For example, if you have an X-ray of a person, so you can put this X-ray in a pre-trained model that can help you to predict and evaluate if a person is suffering from a certain disease or not. And the other category is generative AI that basically is used to create new content with innovation and personalization. For example, if you want to see a cat on the moon or if you want to see Einstein as a doctor. But how this AI actually works, how generative AI actually works, you can imagine generative AI as a person who is able to read text, images, video, code, audio, and multimodals from all over the world. You can fetch the data from the internet, the Wikipedia, or anywhere you want. The generative AI is being created like this. Like you have fed everything into one human, and then that human plus AI mindset has created this generative AI thing. And you can access the AI innovation by just few prompts, and that is called prompt engineering. You might have seen GPT, Gemini, Dora for image generation, website generation, and text generation. And they all work on LLMs that we can see over here. And we will see how GPT was actually built using a neural network. So for understanding the neural network, we will take a simple input-output table as an example. Here in this example, we have taken a simple input-output table where we have data for 4 employees. Employee number 1, 2, 3, and 4. Where we have features like hours worked, task completed, age, and we have the productivity as an output. We have the data for 3 employees and their productivity, but we don't have any data for employee number 4. So our model basically get trained on the 3 data that we have and will help us to predict the productivity of employee number 4. Now we will see the math behind how neural network basically take input from employee number 1, 2, and 3 and help us to predict the productivity of employee number 4. At first, we will feed our neural network with the data of employee number 1 with the hours worked, task completed, and age. And we should get output near to 85. So, before putting the data into neural network, we have 3 layers in neural network. The input layer where we are going to put the data 7, 2, and 25 as an employee number 1. We are just doing it for employee number 1. And then we have this hidden layer and this output layer. Neural network basically passes the input to input layer, then to hidden layer, and to the output layer, and we get the predicted output. But how does it actually works? After feeding the data into the input layer, it goes to the hidden layer and then goes to the output layer, and we get the output out of it. And for employee number 1, we will try that our model predicts the data near to 85, as it will improve the accuracy of our model. As if a new data comes in like employee number 4, it will give the right result for the productivity. Now we will see how this input layer, hidden layer, and output layers actually works. So basically, this x1, x2, and x3 over here are like hours worked, tasks completed, and the age. These are basically the features of the input output table. So we have mentioned over here as a feature x1, x2, and x3. The 7, 2, and 25. But what actually happens after we have fed the data in the input layer and it goes to the hidden layer? In this input layer, we have two parts. The first one is submission and the other one is activation function. The submission function basically helps the neural network to combine all the input coming from the input layer, and then it passes the submission result to the activation function over here, and the activation function basically gives an output. Now let's see the math behind it. We have weights in this neural network and the weights decide how much importance to be given to each input. Like if we have input number 1, we have weight number 1 over here, and we have weight number 2 on this node, we have weight number 3, we have weight number 4, and we have weight number 5 and weight number 6. So these weights basically goes to the hidden layer, and these weights basically decide to how much importance to be given to which input. And we have biases over this node, like we have bias number 1, bias number 2, and we have bias number 3. So what are these biases? Biases basically helps the model to make a better prediction by shifting the output. For example, for employee number 1, we want our output to come out to be 85, as given in input output table, and our model is predicting the productivity of this employee to be like 60. So biases basically help to shift this 60 to 85, so it can improve the accuracy of our model. And if any new data like employee number 4 comes in, it gives the correct productivity for employee number 4. Now let's see what's the math behind it. And to make it simple, we have just taken single collections from the nodes. And this is basically your input layer. This is your hidden layer. So how this input layer like 7, 2 and 25. We have like weights attached to it. We have weights like W1, W3 and W5. So we'll mention it over here. W1, W3 and W5. And we have hidden layer over here which has two parts. The first part is the submission part and the other part is your activation part. What this submission part basically do is it collects the input as like W1, W3 and W5 over here, and it passes as a single unit. We have like W1, W3 and W5. So we pass it as a single input to this activation function, and this activation function gives an output. Now let's see how this submission function actually works. We have a formula for it over here. As you can see, we have this formula. Z is equals to W1 x1, W2 x2 and so on plus B. B is basically the bias over here. This node has its own bias that we have mentioned before, bias number 1. So what submission function actually does is, we can just make this node over here to make it more clear. Like, we have this node, we will split this node into two parts. The first part will contain this submission and the other part will contain the activation. Then the submission function, the formula we have seen just now, this Z formula, after calculating this Z, we will use this Z formula in the submission function. And after getting the output for Z, let's say we have a number over here like 0.3, we will pass this as an input to this activation function. So let's first see how to calculate the value of the Z. We have like W1, X1, W2, X2 and B. So we need the value for like W1, W3, W5, X1, X2 and X3 and the value of this bias. We can randomly assign the value of this weights and the biases at the initial, and I'm just assigning 0.1 for the simpler calculation for W1, 0.1 for W3 and 0.1 for W5 as well. And it is not necessary that you take the exact same value. You can take any value like 2 over here, 5 over here, 6 over here. You can take like any value. I'm just taking 0.1 for the simpler calculation. And we can just randomly assign the value for B1 also. We can just say that B1 is 0.1 itself. And later, when we calculate the prediction using this weights and the biases value, for employee number 1, it should come near to 85. And if it is not coming, so we will just adjust the value of this weights and the biases accordingly. So it approaches this 81. And you can take any value like we have taken the positive number like 0.1. You can even take the negative number for it. Let's say if we adjust the bias to like -4, we can just take the negative number for it, and we can just calculate the z accordingly. Now that we have the value for our weights and the biases, let's calculate the value for a z. We will just simply calculate the value of the z using the inputs that we have created over here. Like we have 0.1 over here for W1, 0.1 here for W3 and 0.1 for W5. We'll just simply put the value of W1, X1, W2, X2 and the bias in this Z formula. And we have the value of W1 as 0.1. We have the value of X1 as 7, X2 as 2 and X3 as 25. So we'll just simply put it over here and we'll just put the value of this bias also. We will just put the value of bias as -4. So after calculating all this, we have 0.6 as our output. After getting this 0.6 as an output of the Z, we will just pass it into our activation function. That is an other half of an hidden layer that we have over here. We'll just simply pass this 0.6 as an input to this activation function. So before passing any input to an activation function, we will first understand what an activation function is. So what an activation function is? Activation function basically helps you to understand the behavior of a data. If you have in data and you want to understand the behavior of a data, activation function basically helps you to understand that. What do you understand when I say understanding the behavior of a data? Your data can be in the linear form, like in the straight line, and it can be like in the equation y is equals to mx plus c. But what if your data is in non-linear form? Let's say your data is giving your result like this, and it is showing when you escalate your car, the temperature of the car varies like this in your car. It's in this form and it is not in this linear form. So your output is coming like this in the bended form. So this activation function basically helps you to understand the non-linear data. When your data is in non-linear form, the activation function basically helps to understand that. And to understand the model behavior that is in non-linear form, the activation function uses something called sigmoid function, which is represented like this: 1 by 1 plus e to the power minus z, where this z represents that we have just calculated w1 x1 plus w2 x2, similarly plus b. So basically we pass this z value in this activation function, and it will help us to understand what our model is behaving like. Now let's try to understand this formula with more clarity. So we'll just go here. We'll read this. The sigmoid function maps any real value number into a range between 0 and 1. And it is commonly used in binary classification tasks. And we are just seeing the formula over here. And we can just take z as an input over here because we have taken z initially. So z input to the neuron, and e is a Euler number that is close to 2.71. For very negative z, for example, like if we take minus 10 over here, the output would be close to 0. And for very positive z, let's say we are taking positive 10 over here, the output would be close to 1. And if the z value is near to 0, so the output would be exactly 0.5. So how we are predicting 0.5 value? Because if we put 0 in this formula, 1 by 1 e to the power 0, so it would be 1 by 2, it would be turning into 1, and it would be 0.5. Now that we understand what an activation function is, and we have a value of z over here as 0.6, so we'll just simply put into the activation function formula over here. Let's say we have a value of 0.6 over here. So we'll just simply put the value of z into the activation function formula. What is the formula over here? 1 by 1 plus e to the power minus z. We'll just simply put in the values. So basically we calculate for G1. G1 is basically the output of an activation function that an activation function gives. We can just mention that as G1 also. So we can just put it 1 by 1 e to the power minus z. I can just simply put the value over here, 1 by 1 plus e to the power minus of 0.6. That would come out to be 0.354 after calculating. So we have the value of our G1 over here. So we will just go up to the diagram that we have. We have now the value of G1 also, that is 0.354. Now that we have a value of our G1 and we have calculated the value of Z, we can just mark it as Z1. So we can calculate the value of Z2 and G2. So we have just taken one node over here in the hidden layer. In this hidden layer, we have just taken one node, and there is one another node that we have ignored for the understanding. So it will give us the value of Z2 and G2 in the similar way as we have calculated for this node. Now we will calculate the value of Z2 and G2 in a similar way that we have calculated the value of Z1 and G1. And for calculating the value of Z2, we will just take the weights to be W2, W4 and W6, as these are the only weights that are directly connected to this node. So we will take W2, W4 and W6 over here, and we will take the value of X1, X2, X3 as 7, 2 and 25 for employee number 1 as in our input output table. So we'll just proceed with the calculation that we have done previously for Z1. So we will just put W2 X1 plus W4 X2 and W6 X3 plus B2. So we have to assume the value of the weights as we have assumed while calculating the value of Z1. So we will just assume the value of, let's say, we will assume the value of W2, W4 and W6. Let's assume a random number, a value of weight 2 to be 0.16. For W4, it can be 0.5, And for W6, it can be, let's say, 0.6. We have to later adjust the weight if the outcome is not coming near to 85 as it is giving in the input output table. So we adjust the weight and try to come close to this 85. So we'll just put the value of W2 0.16 and the value of X1. The value of X1 is 7, X2 is 2 and X3 is 25. So we will just simply put the value over here and we will put the value over here as 7 and W4 to be like 0.5 and the value of X2 is 2 and W6 is 0.6 and the value of X3 is 25 and we have to assume a value for B2 also. We will adjust the bias accordingly with the weight. So we will later see how we will adjust it, but for now, let's say we have assumed the value to be -4 itself. So we will just put -4 and after calculating it, it could be near to 13.12. So we will just simply put the value of Z2 over here. And for calculating the value of G2, we will just use the formula that we have previously used. So we will just put e to the power minus z. So we will just put the value of z that we have just calculated 1 plus e to the power minus 13.12. So let me calculate the value of this for you, like it would come around to be 1. So we have G2 as 1. So let me put all the value that we have calculated at a single place for you. Like we have calculated the value of Z1 and it is 0.6. G1, that is our activation function value that we calculated to be 0.354. Value of Z2 is 13.12 and G2 is 1. So we have calculated all these values. So we have these values. Z1 as 0.6, G1 as 0.354, Z2 as 13.12 and G2 as 1. Now that we have calculated the value of Z1, G1, Z2 and G2, we'll just simply mark it over here in the cleaner diagram. We will just put G1 over here. The value of G1 is 0.354 and the value of G2 is 1. So now we will calculate the value of Y predicted. This is basically the value that our neural network is giving us against the input of employee number 1. And the expected output is 85 as of input output table. So we will just calculate the value of Y predicted over here. So we also have a weight to this node that is W7 and W8. We also have weights over here. So we will calculate the value of Y predicted using the weights. To calculate the value of Y predicted, we will just simply use this formula. We will just write Y predicted is equals to W7, the weight of this node, and into G1 plus W8 into G2 plus the bias of this node, that is B3. We have put the bias over here as B1 and in this node we have the bias of B2. For this node we have a bias for B3. This is nothing but the same formula that we used to calculate the value of Z. Z is equals to W1x1 plus W2x2 dot plus B, the bias. It is the same formula we are using here to calculate the value of Y predicted. So we can just put the value of W7. We can just assume the value of W7 to be 7 and the value of W8 to be 3. And the value of base can be anything like 12. So we will just put all the value over here. The value of W7 that we have put is 7. So it's 7.0.354. It is a value of G1 that we have calculated above. And what is the value of W8? It is 3. And value of G2 is nothing but 1. And value of B3 is 12. So we'll just calculate this and it should come around 17.47. So it's a value for Y predicted. So we will just use this value as Y predicted. But the actual value was 85. So what is the error that we are getting over here? So we'll just calculate the error. For calculating the error, we don't have to do anything. We just can subtract 85 from this 17.47. This is nothing but the error that we are getting in the model. So it will come out to be around 67.522. So this is the error that we are getting over here. The whole purpose of the model is to reduce the error and improve the accuracy of the model. So how we are going to improve the accuracy of the model? We are just going to back propagate. What is back propagation in this case is like we forward propagated in this direction from input layer to hidden layer to the y predicted, and we calculate the value of y predicted. Now we have to just go back in the same direction from which we came from. We just had to jump from y predicted to this hidden layer. So we'll just go back and we will modify these weights as W1, W2 that we have just taken, and we'll just try to overall reduce the error of this model. For reducing the error, we use something called gradient descent. It's a gradient descent, and back propagation is a method. So we have already seen how to back propagate. We will just move back from y predicted to the hidden layers. And what is basically this back propagation? And till when we have to update the weights and the biases? It's being decided by something called global minima and local minima. So we'll just see what a global and local minima is. So we are basically updating these weights and biases in this neural network that we have just created over here. So we'll just look at when to stop updating these weights and the biases. So there is something called global and local minima. So what are these? So imagine that this is a curve that you have and you are here. You're trying to reduce the error. And at this point of time, you will feel like this is the minimum error that you are getting in exchange of x. If x is your input and y is your output, it is the minimum error that you are getting. And at a certain point, you will start again increasing the error. So we have to achieve this point. This is something called global minima. So we have to achieve this in order to know when to stop updating this weights and biases. So there is something called local minima also. So if you have a curve something like this, and you just place a ball over here and you are just trying to reduce the error. See, at a point you will feel that this is a point where you have reached and you have again started increasing the error. But when you move forward and reach this point against x, you will find that this is much lesser than the previous one. So this is called local minima, and this point is a global minima. Local minima is something that you can achieve, but the global minima is the one that decides when to stop updating this weights and the biases. So we'll just look forward to it. So we basically use gradient descent to update these weights and the biases. So what actually is gradient descent? In neural network, the model makes prediction as we have made it over here 67.52, and you compare it to the actual output. At the initial, we have an actual output of 85 in this input output table, as you can see over here for the employee number 1. It is a 85 over here. That is an actual output for us. Then you calculate how wrong the model is. Like in our case, 67 was an error, and the gradient descent helps you to update the weight to reduce the error. So how gradient descent works? We have a formula for it. We'll just see into it. Gradient descent basically works at the formula cost is equals to actual minus predicted square. So why we are taking the square of it? Because we are going to differentiate it, so it will help us in that, and we want a positive number. We don't want a negative number to come out of cost. We can also take an absolute value, but in the later part when we're going to do the differentiation part, it would be difficult for us in the absolute value. But if we take the square of it, it would be easy to differentiate. For example, when we are differentiating x square with respect to x, it is very easy to differentiate it. Like it would come out to be like 2x. But if you are differentiating the absolute value of x, it would be much difficult for us. So we just want our cost when we differentiate it later to come into positive value, and differentiation becomes easy. That's why we take the square values. Now we will look at this back propagation part. We'll just zoom in and we will see that this is nothing but the hidden layer that we have seen before. So it contains both a summation function and the activation function. Contains both summation function and the activation function. We have weights assigned to it, W7 as we have seen before, and it's 7. And we have weight assigned to this node also, that is W8, that is 3. And we have G1 over here as we have calculated, that is 0.54. And we have G2 over here, that is 1 for this node. So we'll basically going to back propagate it from here to here. So we are going to calculate the cost as we have seen before. We are just going to calculate the cost by y actual minus y predicted square. And now we are going to see how to calculate the gradient descent for it. We'll just see that what is the formula for calculating the gradient descent. So we are going to differentiate this cost against weight 7. I'm going to explain you this formula, so don't worry. We have y predicted over here, and then we have y predicted by differentiation of with respect to W7. So basically, what is happening over here in this formula? We are just basically seeing the y predicted is connected to W7. Like y predicted over here is directly connected to W7. So we are first calculating it for W7. So what actually is happening here in this formula is we are just checking ki how much y predicted is affected by W7. As W7 is directly connected to y predicted, as you can see over here, and it is directly affecting the result of y predicted. So we'll just calculate first for W7 and then for W8. So we are just seeing over here for W7, and then we are going back that how the cost is being affected by y predicted. This cost is directly connected to y predicted. So we are seeing this, and this is the whole concept of this formula, how W7 is affecting the cost of it. Like what changes that we can do in W7 so that the cost can be improved. Like the predicted value can be closer to the actual value. So we are improving the accuracy of the model. We are trying to establish a relationship between W7 and the cost. That how W7, the weight, is affecting the cost over here. As cost is directly affected by y predicted, and y predicted is directly affected by W7. So we'll just calculate for W7 first, and then we will just calculate it. So we have seen that before that y predicted is equals to W7 G1 plus W8 G2 plus B3. We have seen this formula before. As we have seen over here, y predicted is equals to W7 G1, W8 G2 and B3. So we are just directly using this formula over here, that W7 G1, W8 G2 and B3. Now that we have a value for y predicted, so we first check ki what y predicted is being affected by. So it is affected by weight 7. As you can see over here, that we are calculating for weight 7 and y predicted is affected by weight 7. So we will first check for y predicted affected by weight 7. So we will use this formula as we have the value of y predicted over here, and we are just checking it for weight 7 that is associated with G1, the value that we have calculated over here. So we'll just consider this part, this G1 part, and we'll just nullify this part. We'll just directly do it 0. So what is the value of it? We have the value of W7 to be 1. We are assuming it to be 1 as it contains G1 as its coefficient, and the value of G2 and B3 would be directly nullified, and the value of G1 would be as it is. So we only have G1 left. So the value of this whole part is G1. So now that we have a value for y pred to W7, we can just replace it over here as G1. So this formula would be like this. So it would be like cost by W7 is equals to change in cost due to y pred into G1. And what is this part? So this is nothing but cost, and cost is actual minus predicted. And if we are taking the whole square for it, so if we are differentiating it to this y pred only, so we can just understand it like this, as we have seen it before also. If we are differentiating x square with respect to x, so it would be 2x. So considering the same fact, so we can just put cos to W7. So we can just make this part as 2 into actual value minus the predicted value that we got. This is the predicted value we got into G1. We will just get the G1 value over here, that is 0.354. So we will just calculate it, and it would be coming around minus 47.80. So this is the value for this, and we are just keeping this value, and it would be required while updating the weight. We are just like we have calculated it against W7. Now using the gradient descent formula, we will update the weight of W7. First we will calculate the same for W8 and B3, and we'll update it all together. We got this value of 17.478 from the y predicted value. So we can see over here that we have calculated y predicted over here 17.478, and we are just using it over here. Now we will do same for W8 and B3. So we will just do it similarly for W8 and B3. Similarly, we can just do it for W8 also. We are going to calculate it for W8 first. So how we are going to calculate for W8? We can just put it like cost affected by weight 8, as we have done for W7. We can just use the same formula, cost by ypred into ypred by W8. So we are just going to use the same formula. So similarly, we can just do it for this also, y predicted into G2. So how G2 is coming over here, as we can see over here that we calculated G1 out of it, as the W7 and y predicted is directly connected through G1. So in the same way, we will get G2 for this W8 part when we are updating W8. So we are getting G2 over here. So we can just write over here like 2 into 17.47 into value of G2, that is 1. So we'll get an output of minus 135.044. So this is a value for cost that is being affected by weight 8. Now similarly, we will do it for B3 also. Why we are doing it for W7, W8 and B3? Because the Y predicted and the cost is directly being affected by W7, W8 and the B3. The B3 is in this node. So the Y predicted is directly affected by B3, W7 and W8. So we are just checking that how we can update the value of W7, W8 and B3 so that we can improve the cost. And we'll just calculate for B3 also in the similar way. So the cost, the same formula that we are using for W7 and W8, the cost being affected by B3, we are just going to use cost and y pred over here, y predicted into y predicted by B3. So you can calculate it like 2 into y actual minus y predicted into 1. And we are just going to solve this portion first. So for solving this, we are just using the same formula, W7 G1 plus W8 G2 plus B3. So we are just directly going to nullify this part 0 0, and this part is going to be 1. So we can just put directly 1 over here, and we can just calculate the cost function. We have taken this one from this formula itself, and we are just going to calculate the cost affected by B3. So it will come out to be around 135.044. So this is the cost. Now that we have the value of cost being affected by W7, W8 and B3, we have the value for all of this. The cost is being affected by all of this directly, W7, W8 and B3. So we will try to update all these three using the formula of gradient descent. So what is the formula for gradient descent? We can just write updated weights. If we are updating the weights, is equals to old weight that we were using as W7 minus the learning rate. It is being generally represented by eta like this into gradient. This gradient is basically this only, the cost being affected by W7 that we have calculated individually. So if you want to update the value of W7 weight, like we can just represent it at W7 plus. So we'll just write the value of old weight, that is W7 minus the learning rate. We generally take learning rate to be 0.01. The value of eta, that is our learning rate, is generally 0.01. So we can just write over here minus 0.01 into the value of the gradient that we have calculated, that is cost by W7. This is our gradient value. So this is minus 47.8 that we have calculated. So we'll just put it over here minus 47.8, and we will just calculate this, and it will come out to be 7.47. So this is our updated weight for weight 7. So in a similar way, we are going to do it for W8 and B3. For W8, we can just write W8 plus and we'll just write the old weight minus the learning rate, that is 0.01, into the gradient, that is cost by W8. So we will just write 3 minus 0.01 into minus 135.04. These are the values that we have calculated. This is the learning and this is the old weight. So we are just going to calculate it and it will come around 4.35. And this is the updated weight for weight 8. Now similarly, we are going to do it for B3. For B3, we are going to calculate over here. We can just write a B3 plus is equals to B3 minus eta, that is the learning rate, into cost by B3. It is the same thing, the learning rate. So we will just write a 12 minus 0.01 minus 135.044. So we're just going to calculate it. That is coming out to be 13.55. So this becomes our updated bias for bias 3. So we are going to again recalculate the error using the updated weights and the biases. The updated weights we have, finally we can just write it over here. We'll just write it over here that these are the updated weights and the biases. For W7, it is coming out to be 7.47. For W8, it is coming out to be 4.35. And for bias 3, it is coming out to be 13.55. So these are the updated weights and the biases that we have calculated over here. We'll just recheck the values. That is 7.47, 4.35 and 13.55. So we are going to use these weights and the biases in the neural network that we have created over here. So we'll just update these weights over here like W7, W8 and the bias 3, and we'll recalculate the value of Y predicted. And then we will recheck that the error is being reduced and it is coming close to the actual value, that we have here in the input output table, that is 85. And overall we have to achieve this output that is being given in input output table, and we have to reach close to this 85, and we have to overall reduce the error over it in this neural network. So if any new data like employee number 4 comes in, it gives the correct productivity for it also. Like this, you have to update the weights and the biases of the neural network using the gradient descent formula, and you have to overall reduce the error and improve the accuracy of your neural network and make the correct predictions. This is how neural network works with the data that you feed them. That's how weights and biases are being updated in artificial neural network to reduce the error. Now let's see some other example to understand it better. In this example, we have this input output table where income, education and healthcare is being given, and in this input output table we are being expected to predict the life expectancy of an individual. So we have income of different person from different countries maybe. For example, we have this income from India, we have this income from USA, and we have this income from China. So we are expected to predict the life expectancy of India, USA and China citizens over here in this example. So in this table, like we have one more row over here where we are expected to predict the output of like UK. We have some sort of education like 8 over here in UK. We have a health score like 3.5, and we have to predict the life expectancy of the UK citizens. So let's see how we do it. We put the income 4,000 over here, education is 12 and the health score is 7.5. So we are taking the example of India over here. We are just taking the data from India over here. So we are just gonna input all this data over here in the similar way. We will put 4K over here, 12 and 7.5 over here. So this is basically our input layer and this is our hidden layer over here. So our data is being gone from input to hidden layer as we have seen in the urban neural network also. So we'll just mention the weights over here. We will mention the weight like W11, W12, W13, and similarly we will do the weights for like this also. W21, W22, W23, W31, W32 and W33. So we will get these three linear equations from this hidden layer. Like for example, H1 would be W11 X1, because this is our X1, this is our X2 and this is our X3. 7.5 is our X3, 12 is our X2 and X1 is 4K. So we are taking this input with the weights. We are using the same formula of the Z that we are seeing above. W is equals to W1x1 plus W2x2 plus the bias. So we will just create the linear equation for H1, W11x1 plus W12x2 plus W13x3. Similarly, we will do it for H2 and H3. Then we will create a matrix over here using these three linear equation. So how the matrix is being created over here? We'll just grab the matrix over here. So we will create a matrix from this. So the matrix would be H is equals to, it will first contain the weights. So the weights would be W11, W12, W13, similarly W21, W22, W23, W31, W32 and W33. So we have this, and in the other part we would have this x value x1, x2 and x3. So we have created this matrix out of these three linear equations that we get from the hidden layer. So we can just mention this matrix as H is equals to W into X. So we have this matrix over here where W is this and X is the value of X1, X2 and X3. So this would be the H value, W into X. We'll just put this H value into an activation function. So it would be H is equals to F1 W into X. So this will become our hidden layer activation function. So this is our hidden layer output basically. The output that is being generated from our hidden layer over here. From H1, H2 and H3, this is the output. It is being generated totally. So the output of H1, H2 and H3, after applying the activation function, it would be H. So the output is this, H is equals to F1 and this is the input data from H1, H2 and H3. Now that we have this output over here of the hidden layer, what will happen like if we have one more hidden layer over here? So this is basically the output of an hidden layer 1. So H1, H2 and H3 are basically our one hidden layer, that is H totally. What if we have one more hidden layer over here like H1, 1. So it might contain HA, HB and HC as an hidden layer, as we have H1, H2 and H3. What if we have one more hidden layer over here, HA, HB and HC, and it is then generating an output Y over here. So we'll just see how it works. This is our basically step 1. This is our step 2. We have just increased one more hidden layer over here that is then generating the output Y. So we have seen till step 1 that we had this equation over here. This is our step 1 that we have seen how we are getting step 1 over here. Now let's see how we are getting step 2 over here. The step 2 is saying in step 2 basically what we are doing is we are just calculating the value of y, that is our output over here. So we are just calculating the value of y. So how we will calculate the value of y over here? Y is basically F2 B F1 W X. So what is F2? F2 is basically the activation function of the second layer that we have just inserted like HA, HB and HC. It will also have an activation function over here. So we are just using that activation function over here as F2. As we have used F1 for the first hidden layer, we are using F2 for the second hidden layer. Now we have this B over here. This is the weight of the second layer. As we are having the weights over here for the first layer, it would also having some weights over here. So it is being represented as B over here. This is the weights of the second hidden layer and this is the activation of the second hidden layer. And then this whole becomes an input from the step 1. So we have this F2 B and this is nothing but H over here. So this is H. So we have this as an input because after calculating the value of this, we are just passing it as an input to the second hidden layer. So we are just applying weight over here of the second hidden layer and the activation function of the second hidden layer. Similarly, if we have to create it for 3 layers, like for example, if we have one more hidden layer over here, this is basically our third hidden layer that is then generating the output Y. So how we are going to calculate it for 3 layers? We are just going to do it like the activation function of third hidden layer, the weights of the third hidden layer and the activation function of the second hidden layer, and we are just passing the output of second hidden layer as an input in the third hidden layer basically. If we want to calculate the value of y after 3 layers, the y value would be y is equals to f3 c into the input of step 2. Let's say it's y1 over here, so we'll just say y1. So this is the activation function of third layer, and the c is the weights of the third hidden layer, and y1 is the output of step 2 that is being used as the input in step 3. This is how we calculate the value of y if we have 3 layers. Similarly, we can do it for 4, 5 and 6. So here we are using step 1, step 2 and step 3 as we are using 3 hidden layers. So these hidden layers are basically improving the accuracy of our model. In ANN we just use one hidden layer, but what if we are using more hidden layer? This is something called DNN. This is our deep neural network where we are using more than one hidden layer to improve the accuracy of a model. This DNN comprises of two things. The first is RNN and the second is CNN. So in this DNN, we are just basically using more than one hidden layer to improve the accuracy of the model. We have two subparts over here in DNN. The first one is CNN and the second one is RNN. You might have heard of this. So now let's see what CNN is and how CNN actually works. So CNN is basically a convolutional neural network, which is a special type of a deep learning model. So this is basically used to analyze the images and the videos. Like this DNN and AN are basically used for analyzing the text. So how you analyze an image? For example, when you see an image of an face, you see the features of the face. Like this is feature number 1, that is the eyes. This is feature number 2, that is the nose, and this is feature number 3, that is smile. So your brain says if a person is having eyes, nose and this smile, so this must be a face of a person. Similarly, computers also analyze this similarly by analyzing the features of it. For example, this can be used for detecting a digit, for example 9, detecting faces like face detection, it can be used. So we will take this example of 9 number. So how a computer would gonna analyze if someone has different handwriting? Someone has written 9 like this, someone has written 9 like this, someone has written 9 like this. So how computer will analyze this is digit 9? So we are gonna see it for digit detection. So how a computer analyze which number is this? We are taking the example of number 9. So computer will map number 9 like this in this grid. So this is number 9 over here, that someone has written 9 like this. So 9 would be placed like this in this grid. So how a neural network will analyze that this is a number 9? So we will just zoom in over here. So basically it will make a feature out of it. So it will run this feature at the body of this digit 9 and break it into small parts. For example, that we have seen over here, we have seen the features of a face of a person. So it will also analyze the feature of number 9 over here. So it will just see the features over here. So for example, this can be one feature, that is the head of 9. This can be a second feature, that is a body of 9. And this can be the third feature, that is a tail of 9. Similarly, like eyes, nose, and the third is the smile. So it will similarly just see the features of number 9, that is head, body and tail. So how basically a neural network does this? So it basically convert this number 9 into this grid, and then we apply a small feature that we have seen over here, like in these boxes. It will apply these features in this form. It will just take a this 3 by 3 matrix that contains 1 and a minus 1, and we have number 9 over here. So it will run this small feature. This is basically called a feature or a kernel. So basically it will run this kernel over this grid. Basically, first we have seen in step 1, this neural network will map this 9 number in this grid. Then this feature will map this grid. For example, we will just take this grid, we'll just copy it. So what this feature and kernel do? It just map it like this. It will go over here it in a 3 by 3 manner. Then it will shift it to here. Then it will shift over here. Then it will shift over here. And like this, it will cover the whole grid. So, so how basically this is done is like this. we will just map this grid. This is number 9 over here. So we will generate a feature map out of it. So how feature map is being generated? We will generate a feature map, that what are the features over here, like the head, body and the tail. So we will like to generate a feature map over here. So how this feature map is being generated out of this? So we will just multiply each number with this grid. To generate the feature map, basically we will just map each number with it. We'll just not see the final output, we'll just try to calculate it. To generate this feature map, we will just do the matrix multiplication over here. So we will just multiply this number with this. So we will have -1. Then we will add this into this over here. That is 1. So basically we are doing it for 3 by 3 matrix. So what basically we will get when we multiply this and this feature with this 3 by 3 matrix. So we will get -1 plus 1 plus 1 -1 -1 -1 -1 plus 1 and plus 1. So we will get an output of -1 over here. Then we will calculate the average over here. So we will just divide it by 9, -1 by 9. So it would be like minus 0.11. Similarly, we will do it for this other 3 by 3 matrix also, like over here. This is the 3 by 3 matrix over here. The next 3 by 3 matrix. So we will get an output of 1 over here. So like this, we are going to create the feature map over here. Like we will just put minus 0.11, then 1, then we'll get 0.11 over here. We have calculated this minus 0.11 for this initial 3 by 3 matrix, that we have used this filter over this 3 by 3 matrix in this only this part. But now we will move on to this next, we will just move this matrix over this area. Now we will use this part. Next 3 by 3 part, we will use this part. Now we will multiply 1 by this, then add multiplication of this both, then add multiplication of this both. Like this, we will just move this filter throughout this matrix, like in this 3 by 3 pattern. And at the later stages, we will get the final output as this. This is a feature map. So in this feature map, basically, when you get the 1 over here, so this 1 in this feature map basically tells that there is some sort of feature over here. For example, in case of 9, you can just tell that this is the loopy head. So this can be the feature of this head. This one can be the feature of this head. So now we'll move forward. Now we know how to calculate the feature map. So we will look at this by just the 9 example itself. So we'll just make this 9. So after calculating all this and multiplying this with this filter, we get 1 over here in this feature map. We got 1 over here in the feature map. So this 1 is telling that there is some sort of loopy pattern. So we can say that this 1 indicates the head feature for number 9. Now moving forward, when we get this feature over here, so we can say that it might be a number 6, maybe, because we are getting the loopy pattern over here. So similar to 9, if we get the loopy pattern of the 9 over here, like at the head of it, so 1 is coming over here. For number 6, the loopy pattern must be somewhere here. So similarly, if we get 1 over here, so we can say that it might be a number 8, because we get the loopy pattern of 8 over here also and here also. If we get a loopy pattern over here, so this might be a number 8, because we have a loop over here also, that this one is representing, and we have a loop over here also, that this one is representing over here. If we take a number 9 example again, so we got an head feature over here as 1. So maybe we can get the body feature, maybe this part. We can get a body feature number 1 over here somewhere. And for the tail, we might get a feature over here. We can say it as tail feature, that this number is being representing. So we get a loopy pattern over here, the body over here, and the tail feature over here. So this might form a number 9. Now we will move forward and see what happens after the feature table. This is basically a feature map. So this activation function, ReLU, is basically an activation function. After getting this feature map, we apply an activation function over it. This ReLU over here is basically an activation function itself. So what this basically do is, like we have seen activation function as like sigmoid. We have seen the sigmoid activation function in the previous part that is being represented like this. But this is the activation function that we are seeing over here. This is similar to sigmoid, but we use different activation function according to their use cases. Like this ReLU, basically it converts every negative number into zero. As you can see, every negative number, it can be like -5, -4. So it is giving an output of 0 over here. But every number after 0 is being kept as it is. For every negative number in the feature map, this activation function is basically converting it to 0. For example, -0.11 is being converted to 0. But 0.11 is kept as it is. 0.33 is also kept as it is. And rest all the negative number is being converted to 0 over here, as you can see. So this is basically an activation function role. So we will just see forward what happens after the activation function is being applied. After applying activation function to it, we get an other feature map table. So what we do in CNN after applying the activation function, we do a max pooling operation over here. For understanding pooling, we can take an example over here. For example, we take this 4 by 4 grid over here. So what is happening in this pooling part, if we have this number like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'll just fill the number randomly over here. So we will just see in this pooling operation over here that we will take this 2 by 2 grid first, and we will just make a smaller grid out of it. We will just make this 4 by 4 grid into 2 by 2 grid. If we just want to compress the grid size, we just do this pooling operation. We will just see in the initial part what is the largest number. If we are doing a max pooling, so we will just see the largest number over here. Like 1, 2, 3, 4, the maximum number is 4. For 5, 6, 7, 8, the maximum number is 8. For 9, 10, 11, 12, the maximum number is 12. And for 13, 14, 15, 16, the maximum number is 16 over here. So we have just converted this 4 by 4 grid into 2 by 2 grid by doing max pooling. So there are different type of pooling that you can do in CNN. The first is the max pooling that we have seen. There is average pooling and there is a global pooling also. So in average pooling, basically we do the average of first 4 number and we'll put in this first cell. Like we have put 4 over here. By seeing the maximum number, we'll just take the average of first 4 number and we'll put over here. And in the global pooling, we'll just take the maximum number out of it. For example, in this, the global pooling would be number 16. So basically we reduce the entire feature map into a single value over here. So the single value would be number 16, as it's a global pooling. So now we'll move forward to the benefits of pooling. So what are the benefits of pooling? Pooling basically reduces the dimension and shrinks the feature map into lower sizes. Like we have seen into 4 by 4, we can convert it into 2 by 2. It basically retains the key features. So like in this, the key feature is 4. So we are just retaining the 4 over here, 8 from this grid, 12 from this grid, and 16 from this grid. So basically, we are just retaining and the key features out of it. And we also reduces the overfitting that eliminates the noise and helps the model generate better. And it also traces the model to the ropers for the small shift or distortions in input. Now we'll move forward how CNN actually works for image detection. For example, we have an image of a koala over here. So you can see that we have eyes over here of the koala. So we have applied a eye filter over here. This is basically eye filter. So this eye filter will just take out the exact location where the eyes are being located of the koala. And then we have applied the nose filter. So it will just detect the place of the nose. Then the ear filter, we have the 2 ears of the koala over here. Similarly, we'll just do it for hands and for the legs also. That where are the legs of the koala. So this is how basically the filters are being applied to the image. Now we will see how CNN will work on it. So basically, CNN will filter all the features out of it, like this eyes, nose, ears, hand, and legs. So basically, this eyes, nose, and the ears are basically making the head of the koala. So this is one feature, that is the head of the koala. Then the hands and the legs are making the body of the koala. So we are just making head and body as a feature, and we are just flattening it. We are just flattening the 2D features into 1D feature. So we are just flattening those features like from 2D to 1D, and then feeding the features into the neural network, into this 1D array. This is nothing but the 1D array over here. So we are just compressing our 2D to 1D array. Then we are just passing the features of flattened head and the flattened body in the form of 1D array into the neural network. And the neural network is then predicting that this is a koala or not. So now we will see how it actually works. So after we have the image of the koala, then a convolutional and a ReLU activation function works on it. ReLU is the same activation function that we had just discussed, that just looks like this. This is the activation function. To understand this convolution, we can just take an example of a pizza over here. We have a pizza over here. We have few toppings over here. We can take onion and we can take corn. These are the two toppings. So basically in this convolution, this basically breaks the pizza into different toppings, and it identifies the topping individually, so that this is an onion, this is an corn. So basically it identifies each topping separately, and in this 1D vector basically we are just putting all these topping all together to recognize that it is a pizza or not. So in this convolution, we can say we have a dough, we have onions, we have corn, maybe we have cheese over here. So it can predict in this 1D vector when we put everything in a plate. So it can predict in this neural network that it might be an pizza over here. So this is how convolution works. It basically breaks every ingredient of a pizza into individual parts and recognize the individual part separately. And in this 1D vector, we put all the individual part all together into a single plate. And then it predicts that it might be a pizza or not. So basically it breaks every feature into small individual parts in this convolution part. After convolution and ReLU, we do the pooling that we have seen above. Then again, we do a convolution and ReLU, and then we again do the pooling part, and then we flatten where we are converting 2D into 1D vector, and then passing it to the neural network. The neural network map behave the same way. We just decide some weights over here, so that can be any weight. We just take the input, add the bias, and for example, if you have fed a image of a cat over here, and your network is predicting your cat to be 80% and your dog to be at 20%. Like the image that you have fed of a cat, it can be in cat 80% that they are the probability, and it can be a dog also, that is in 20% probability. So basically, you train a model again and again over some pictures, and it gets started being trained over some of the features that it is a cat or not. So basically, you train your model again and again on different basically images. So you can improve the accuracy of your model. So we also get an probability over here. We use the same formula, z is equals to wx plus b over here, and we just again and again train our model on the different images, so it can improve the accuracy over here. So basically it works like this. First we break down the feature into eye, nose and ears, and then this eyes, nose and ears make the head, and maybe legs and hands make body over here. Then we again do the convolution and ReLU operation over here. We again pull it and we flatten it and get an output over here. That's all how CNN actually works. Now we'll move forward to RNN. RNN is a recurrent neural network which is made up of repeating unit connected in a chain-like structure. And each unit or time step take two inputs, the current input and the previous input. So basically what RNN is, basically if this is our input layer and this is our hidden layer. So if we give any input like x1, x2 and x3 over here, so it will get over here and it might generate an output y1, and from here we get an output of y2. So we again feed this output back in this neural network as an input in RNN, and we again put maybe x1 as an input over here. So basically we're training the model on the output that we are getting out of the model, and we're continuously tracking the current state. We will understand this with an example in the later part. So basically RNN processes these inputs and produces a new hidden state and the output based on the current and the past state. That if we are at this is our current state x, and x2, this is our current state, and x1 is our past state, and it has generated an output of y over here. So we feed this y1 and this x2 together in the neural network to generate an output of y2. And we again feed this y2 back with an current input x3. So basically, why we do like this over here. This is basically a looping in nature allows the RNN to remember the past information and use it for the current prediction also. So we will just take a simple example over here to see how RNN actually works. So we'll just take a line, maybe I love to study. So we can just take a string over here as an example, maybe I love to study. This is an example string over here that we are taking to understand the RNN. So how RNN will actually work? This will break this I into vectors. Maybe it will break it into a form like 0, 1, 0, 0, 1. So maybe this is a vector form of I. For example, this is a vector form of I. So we will just put this vector form into the hidden layer and it will generate an output Y over here. Then we will use this love as an input because this was I. So we'll just go down. So we will take input love now. And love is the second word. So we are taking love over here and we'll just break it down into maybe some form of vector. Now we will not only put love as an input, we'll also put this y as an input over here in the hidden layer. So we are just putting y as an input also over here. So we might get some answer over here that is being generated from love. So what basically we are doing is we are basically just giving an input in a vector form. This is an input 1 for I. Okay. And we are getting an output for it. Maybe this. And we are just looping this output as an input in the neural network again with an input of second word. Maybe it can be love. So this is how RNN basically works. So we will try to understand it better over here by seeing this diagram over here. So RNN basically is being represented like this 0, 0, 0, 0. This is a vector and what is taking as an input as x, it is giving output as y, and we are again and again looping in the same network. This is how basically we represent an RNN. But to understand the structure of RNN well, we'll just draw it over here. So we'll just write our example over here. I love to study. So basically in RNN model, we will just add this layer over here and just drawing this the iterations that we are doing over here that we are looping. I'm just drawing it over here. But remember that this is only one layer over here. So it's not like this. Like we don't have all these 4 layers over here. We have only one layer. And just drawing this one layer 4 times to show you the iteration so you can be clear with the iteration how it can be done. These are not 4 different layers. This is one layer itself. This is basically one layer itself. I've drawn it 4 times. So don't confuse it to be like it is having 4 layers. It is only having one layer. I've drawn it 4 times over here. So what happens is when I say I love, so basically I goes over here. Okay. So RNN is basically used for sequential data. Like I love to study. It can't be study, love, I too. This is the incorrect form of the sentence, right? So in RNN, basically, we do understand the sequence of the data. So what is a sequence? How the sequence is important to us. For example, if we are translating something, like if we have to translate, I love to eat. If I have to translate this sentence, so I will translate it into English like मुझे खाना पसंद है. So the sequence of the line is very important to make it meaningful. So basically RNN help us to understand the importance of the sequence basically. So that we do everything in a sequential manner. So basically you got an idea what RNN do is basically it maintains the sequence of the data that is required to understand the sentence well, and it is required while translating a sentence maybe. If we are putting I as an input over here, so I should remain as it is and love should come later. So like love should remember that I was there before, and when 2 comes, it should remember that the two words were before me. So it should be I love to. It should be not starting from to itself. So that's why the sequence is important, and that's why we are looping it again and again to understand what came first into the line. So we just put I over here. So it will just get into the neural network and it will have an activation function over here. We can just write A1. This is nothing but an activation function. This is the activation function. Then we will just put the other word love over here. So I will generate some output from this activation function, and then it will be getting feeded into the second iteration over here. This is basically the iterations. This is the single layer itself of RNN, but I'm just showing as iterations over here. We can see over time what is happening. So basically this is the timeline. So we'll just put the output of I after activation function is being applied, and we will just put love as an input in the second iteration. So in the second iteration, it would be like the activation function would be applied to love itself. So love would have an activation function of itself, and then we will apply to it. So it would be I love to within love after gone from the activation function. Then 2 would be going from an activation function in the third iteration. So after we applied activation function to this 2 and we get an output over here, we'll just put this output back to the network, and we'll just put the fourth word over here, that is study. So it would be I love to study. This is how the RNN basically works. This is a single layer. So it is happening again and again in the single layer itself. It is not like this in the 4 layers. It is happening again and again in the single layer. The activation function is being applied again and again to each word, and the output is being generated after the activation function is applied. And the next word love is being fed into the neural network later. The sequence of the line should be I love to study. So basically RNN looks at the sequence of the line, basically the structure of the line. So after all the activation function is being applied to each word of the sentence, so it will give an output like 1 over here, maybe 0 over here, and 1 over here. I'll just mark it with different color, 1, 0, and 1. So these are nothing but the NUR output. What is NUR? NUR is basically named entity recognition. This is name entity recognition. So it basically generates an output that we have to compare with an predicted output. Though we can just consider this NUR output that we are getting 1, 0, and 1 over here, and we should get it for the word study also. Maybe we are getting 1 for study also. So this is for I, this is for love, and this is to, and this is study. So this is basically the output that we are expecting. So we'll just calculate and predicted output, that is y cap, and then we will compare that output with this NURB output. So it would be actual minus predicted whole square that we have seen in the above neural network while studying ANN. So we'll just try to calculate y predicted over here, y predicted over here, y predicted over here, and here. So we are basically calculating prediction for each word in a sentence, and then we are applying this formula to it. So we might be having losses also over here. So here can be loss 1, it can be a loss 2 over here, loss 3, and loss 4. To calculate the loss, we just sum all the losses together, loss 1 plus 2 plus 3 and 4. Then we get the total loss, and we just try to reduce it as of an error that we were doing the neural network. So like this, we train our model with different sort of sentences. For example, we have taken this sentence over here. It can be some other sentence, maybe 100 sentences. So after 100 sentences, it will complete one epoch. So it would be like one epoch to it. We'll just feed 100 sentences like I want to drink water, I like cooking. So we will just train our model with different sentences and try to reduce the loss over here. And we'll try to reach closer to the actual values. So this is how basically RNN works over here, by just getting trained on the sentences that we are just feeding to it. It is just looping it again and again, applying activation function to each word of the sentence and remembering the previous word itself and taking it as an input also. So the sequence of the sentence remains the same. So this is how basically RNN works. We just try to reduce this total loss and train our RNN model. Now that we understand how RNN actually works, let's look forward to the types of RNN. So the very first type is one-to-one. So one-to-one is basically the simplest form of RNN where we just take one input that correspond to one output. Basically, if we are taking one input over here, so it is generating only one output over here. After passing to the hidden layers, it is generating one output corresponding to one input. So this is the simplest form of RNN and it is basically used for binary classification tasks. For example, that email is a spam or not. The second type is one to many. You can see it over here also that we are taking only one input and after being processed, it is generating only one output. So this is basically the input and this is basically the output. So now we'll move forward to the second type. The second type is one to many. So basically a single input generates multiple output. For example, you can see over here that we are just passing one input over here and after passing to the hidden layers, it is generating multiple outputs. And it is basically used for generating a sequence of word from an image, like image captioning. And the third type is many to one. The many to one is like basically we are giving multiple inputs to our neural network and after processing it is generating only one output. So basically it is used for sentimental analysis where a sequence of the word is used to predict the single sentence, like it is a positive sentence or a negative sentence. And the fourth type is many to many. So we are just giving multiple inputs in the input layer and it is generating multiple outputs corresponding to it. It's like one to one only, but we are not giving just only one input, we are giving multiple inputs here and it is also generating multiple outputs here. Basically this is used for machine translation where a sentence in a one language is converted into another language. For example, if you're converting an English sentence to Hindi sentence, you might be having multiple words in English sentence. For example, I love to eat, so it will generate every Hindi word for a corresponding word. So it will basically generate a sentence over here in Hindi. So it is like multiple inputs and it will generate multiple output corresponding to each word. Now that we know that RNN is basically used for sequential analysis. Basically, if we have this sentence, so RN basically help us with the sequence of the sentence. But RNN has one drawback and one limitation that it has limited memory. What do you understand by this limited memory? For example, RNN is only able to remember two words at a time. For example, if we are at this current state, I, so we are just represented by xt. And now when we move forward to love and then we move forward to 2. So when we would be at 2, so it will only remember two words, I and love. But when we are at study, it will only remember love and 2. It will forget I. So this is a basic drawback of RNN that it has limited memory. And to resolve this memory issue, we have something called LSTM. So what is LSTM? So we will look forward to what LSTM is. So LSTM is basically long short-term memory that caters the limitations of RNN that struggles within capturing long-term dependencies due to vanishing gradient issue. And LSTM has something called gating mechanism. So what is gating mechanism? Gating mechanism basically consists of three things. The first is forget gate, the second one is input gate, and the third one is the output gate. So these are the three gates of LSTM that we are going to see that how they work, and the result basically from these three gates help us to retain the relevant context over the longer sequence. So the goal is to overcome the short-term memory limitations of RNN and the strength is to accurate modeling of the long range dependencies. And it also has some of the limitations that we are going to see at the later stages, that it has low training, scalability issue and long input sequences. So we will see the limitations later, but we will first understand how basically LSTM works. So we have basically taken an example of a sentence to see how LSTM basically works in the sequence of a sentence. So we have a sentence over here. Ravi plays football almost every day. It shouldn't be hard to guess that his favorite sports is soccer. So we'll just take sentence till here. So we have just taken the first word of the sentence as an input, Ravi. So we have just put it Ravi over here. So it will remember Ravi. So this is our basically LSTM pipeline, you can say. So you will understand how LSTM basically works with the sentences. So we have taken Ravi in the first node. Now we have play. So we will just write play over here. Now the third word is football. So we will just feed this word football in the network. But we want this word football to be remembered in order to guess that the favorite sports of Ravi is soccer. So basically, if you don't know that Ravi likes football, so you won't be able to guess that his favorite sports is soccer. So Ravi plays football, so you need to remember the word football. So basically, football is a relevant word in order to guess that his favorite sports might be soccer. So we are just moving forward with football itself, because almost every day it shouldn't be hard to guess that his favorite sports is soccer. So basically, in all of these words in the sentence, it doesn't add to the relevance to guess that Ravi's favorite sports is soccer. But the word football adds a relevance to guess that the favorite sports is soccer. So we will just keep this word football throughout the pipeline in order to guess his favorite sports is soccer. So we have this as an input, football. So we are just forgetting everything except football. For example, almost every day, it shouldn't be hard to guess. So we are just forgetting every word except football. So this is how basically forget gate works. It basically forgets all the words that don't add relevance to the output. In our case, the output is soccer. So we are just using football as an input, and we are forgetting every word except football, and we are trying to generate output as soccer. So in the second sentence, we have his friend Carlos. So his friend Carlos, however, is a fan of a baseball. So we will just ignore this, and we'll just add baseball. So he's a fan of a baseball. So it might be a relevant word. So we are just keeping baseball throughout. Now when we move forward in the sentence and we encounter word hot dog. So we are basically adding baseball and hot dog together, because hot dog might be of relevance while predicting the output. So we are just keeping hot dog and baseball all together. So now we will see the sentence further. That means Carlos favorite sports is American baseball. So our output is basically American baseball. So we are just keeping hot dog and baseball all together to predict that his favorite sports might be American baseball. So we are just adding an input to an baseball. So this is basically an part of an input gate, because we are just adding relevant word like baseball and hot dog all together to predict that his favorite sports is American baseball. So we can't just ignore hot dog also, and we can't ignore baseball also. So this is a function of our input gate that basically gives an input in order to predict the output. So this is basically how forget input and output gate works. So now we will see the architecture diagram of LSTM. So basically we are just representing long-term memory as C, and we are representing short-term memory as H. So you might be having an idea of what this state HT minus 1 means. So basically, if we are at this word Ravi plays football. So Ravi is our current state in the starting of the sentence. So we represent this current state as xt. And when this xt is passed to an activation function, let's say sigmoid, then it's generate ht after the activation function is being applied to the current state. But when we have the other word, let's say we have play over here. So when we pass play in the network, so RNN and LSTM both work on sequence. So they need to remember the sequence of the sentence. So play is coming after Ravi. So we have to remember Ravi also. So when we are here, so we are marking this as the current state, because we moved forward from Ravi to play. So this is our current state now. And we also pass this in the activation function, and it also generates an output. So when we are at this word, we represent the previous word state as ht minus 1, and the current state is being represented as ht and xt. So now we will move back to the architecture diagram, that how LSTM actually works. So basically we are representing long term as c and short term as h for avoiding the confusion. So we have this tan h function over here as an activation function. So tan h basically divides our outputs in the range of -1 to 1. As we have seen in the sigmoid case, it basically ranges our output between 0 to 1. So similarly, our tan h function basically represent our output in the range of -1 to 1. So we will move forward to the diagram, to the forget gate. That is our very first gate. So in the forget gate, basically the purpose we have already discussed, that is to decide which portion of the previous memory should be forgotten. like which part of the sentence, like almost every day, it shouldn't be hard to guess. It should be forgotten because it is of no relevance to the output. So we just forget it in the forget gate part. And the previous state is represented as ht minus 1 and the current state is represented xt. We have discussed all this. So this is basically how it works. Now we will see the operation of the forget gate over here. So operation is basically the sigmoid function. Why we are using sigmoid function over here when we have discussed the tanh function over here? Generally, we use tanh function in the case of RNN and LSTM. But the forget gate has to give the value between 0 to 1. 0 will basically represent that we don't have to keep that word, and 1 will represent that we have to keep that word in the sequence. So basically, we use sigmoid function in the forget gate part. We will use tanh function also, but in the later part while we are using the input gate. But in the case of forget gate, we use sigmoid function because we want value between 0 and 1. So we are using the sigmoid function over here. So basically we have sigmoid function, then we have the weights of the forget gate, then we have the previous state into the current state plus the bias. It is basically the same formula. Weights are basically like this only, but we have taken out the weights as a common value. So we have taken weights as a common value and we have represented w1 w2 and so on wx to be wf, because we are representing weights of forget gate. So we are just writing wf over here, then we are just writing the previous state and the current state over here. So we will just write the previous state. We have to take the previous and the current state both in the case of RNN and LSTM. These are the input values and this is the bias basically. This is the same formula that we have seen in the case of Z. So we have used the same formula in the case of ANN also. Now we'll move forward to our second gate, that is our input gate. We now know that which part of the value we don't have to keep from the forget gate and which value we have to keep. So basically we have done the weighted sum over here, from using this formula we have done the weighted sum and it has given the value that which value we have to keep in this long term memory, because this line over here, this C line over here is basically representing long term memory over here. So this line is basically representing long term memory, like we have kept word football over here in the long term memory. So we are just keeping the words in the long term memory, like football for example, like in this line we are just keeping football. So this is basically the long term memory that basically is going from the forget gate and we are just keeping the relevant word out of it. So after the forget gate we have this input gate over here. So we'll just take the weighted sum from ht minus 1 and xt and we'll pass the value to the sigmoid function over here, and we'll pass the xt also over here as a sigmoid function. So what basically happening in this input gate is we are just passing this ht minus 1 and xt, like this is the combined previous hidden states like ht minus 1 and this is the current state. So we are just passing this through the sigmoid function. Why we are passing through the sigmoid function? Again, because we want to know that we have to update the value or not. Like in this example that we have taken baseball and hot dog all together. So we have taken input of hot dog also, despite that we are having the baseball over here. So we have to decide in this input gate from the sigmoid function that we have to add hot dog or not. So basically we again pass it to the sigmoid function. So it just look like this. We add just the sigmoid function over here. So basically it is being represented like this. So we have the sigmoid function. We have this input weights. So it might be also having some weights over here. So we are just adding this input weights and we are just passing ht minus 1 and xt and we are just adding the bias to it. So whatever the output is, if it is near to 0, we are not adding anything. But if it is near to 1, like the hot dog, we are adding it to the existing input, that is our baseball. So basically this works like this. If it is closer to 0, we ignore it. But if it's closer to 1, we keep it. Then we pass the this hidden state and the current state to the tanh function also. Why we are passing it to the tanh function? Because we need to create new candidate. The new candidate in our case is hot dog. That we have to add this hot dog to the current state. Then we multiply the output of both and then we pass it to the input gate. and then it finally get added to the memory in the long term memory. Like here, previously we were just having baseball, but after passing to the segment and tanish function, we also have hot dog over here. Now it is in a permanent memory. So basically we have a tanish function over here, as you can see over here. The tanish function is being represented like this, tanish WC. So what is this WC? WC is basically the weights of the new candidate. Like the hot dog might be having some weight, and it is a new candidate that is being added to the long term memory. So it is the weight of the new candidate, and this is the previous state, this is the current state, and this B is basically the bias of our new candidate. So the C is basically representing the candidate. So the candidate is hot dog in a case. Now we will move forward to our third gate, that is our output gate. So output gate basically decide what part of the memory to give as an output as an hidden state. That is our HT. So like in this example, the output should be American baseball. When we have this baseball and hot dog together, the output gate decides that the favorite sports of a person might be an American baseball. So we have passed our previous state and the current state into the segment function. Then we get which part to keep and which part to forget. And then we have added the new inputs also. And this is our like long-term memory. And when finally we have our long-term memory, like we have baseball plus we have hot dog. So this is our long-term memory basically. That we have baseball also, we have hot dog also. So basically, after having all the input added to our long-term memory, so we apply tanish function on it, and then we pass it to the output gate. But before that, we have the sigmoid function again. So basically, the previous state and the current state is again passed to the sigmoid function, and the output from the sigmoid function is then added to the output gate also. So we'll just look how this happens. It basically passes the input to the sigmoid function gate that is being again represented like sigmoid. This W is basically representing the output gate, and then we have this previous state, then we have this current state, and we have the bias of the output gate. This basically decides which part of the output to keep. For example, we have multiple inputs in the output gate. Like we have might be having like baseball, we might be having a hot dog, we might be having some irrelevant inputs also in the output gate. For example, chips. From the long term memory, it came to the output gate. For example, chips. But we don't want these chips to be as an input to predict the output. We just want these two. So basically, the sigmoid function in the output gate basically help us to remove all the irrelevant inputs that are not required in order to predict the output. And we just remove it using the sigmoid function. As we know that it ranges between 0 and 1. 0 we have to remove and 1 we have to keep. For example, we have to remove chips, so it will come under 0, and the baseball will come under 1 and 1. The hot dog will also come under 1. So we are just keeping these two as an input and we are just ignoring this chips. So we just apply sigmoid function again over it, and then we apply the tanh function. This tanh function basically squashes the memory, the value between -1 to 1, and the final hidden state is being predicted using this tanh function only. And in the starting itself, I've told you that in RNN and LSTM, we generally use tanh function, as tanh gives us the value between -1 and 1, and it basically squashes the memory. Basically, it squashes the memory between this range. It basically shrinks the memory to this range, and we want to get an output between this range itself. So we have the hidden state formula over here. That is our output state. This OT is basically representing the activation function itself, and now we have this OT as an activation function. Then we apply tanh function to it, and then we plug this CT over here. This CT is nothing but the candidate value that we are getting from the sigmoid function as an input to the output gate. When we get the candidate value, like this chess is not required, so we get this candidate value to be 0. So we apply the tanh function to the updated CT that we have. We only apply tanh function to this baseball and the hot dog, and not on this chips. So we just need this baseball and hot dog to predict the output. So we are not applying any tanh function on this CT, that is this candidate chips. So we are just applying this tanh function over here to this final inputs that are baseball and hot dog. So we are just applying tanh function to these input that are being passed from the segment function itself also. So after doing all this, we get our output in the form of HT over here. that is our hidden state, and st is nothing but the output. Like we have some words over here, we apply activation function to it, and we get some output over here as an st. So we have our output over here. So after getting this st, we consider it as an output. We can also loop repeat. We can also just loop in this cell. So this is basically the cell of an LSTM. So this is a basic cell. We have seen cells like this is the hidden state. So we have just rotated our cell like this. So we are just trying to explain you how the working of a cell actually happens inside a neural network. So now we understand how LSTM actually works, from forget gate to the input gate to the output gate. So this is the basic structure. We can train our LSTM model with the n number of sentence, so it get trained well. We can just like train it over 100 plus sentence, so to improve the accuracy of the output that we are getting over here. So we can just train our model again and again over different sentences. We have just taken one sentence over here as an example over here. So we can just take like 100 plus sentences to train our model well. So this is how basically LSTM work. So we have one of the limitation over here that we can just discuss now. So just like RNN, so it was not able to remember much words. Like for example, if we are like at every day, so it will only remember previous two words like football and the almost, but it will forget Ravi and play. It will only remember two words like the previous two words, and it will forget every word before that. I'm just taking example over here that RNN will remember two words, but it's not the exact case. RNN might be able to remember more words. I'm just taking a small example over here to make you understand how RNN basically works. Now moving forward to the limitation of LSTM, it is basically slow training and scalability issue model. So basically LSTM is also a sequential model. Like if we have some sentence over here, I am a good boy. So it is also a sequential model. It might be able to remember much words in the relevance to generate the output well, but it can't read whole sentence at once. LSTM is unable to read whole sentence at once. It go word by word. So it is very slow training and scalability issue model. We can't scale it much because it is not able to read whole sentence at once, and it comes with long input sequences. So we have to give a long input. It will go sequence by sequence, word by word, and it is not able to read whole sentence at once. So this is basically the limitation of this LSTM, that it is not able to understand whole sequence, like whole sentence at once. It goes sequence by sequence. So it takes long input sequence. It is not very scalable, and it also takes a lot of time to get trained because it is going word by word, sequence by sequence. So this is how basically LSTM works over here. Now that we have seen the limitation of LSTM, that it processes only one word at a time, and it's hard to remember long sequences. So there is one more architecture called transformer that is behind ChatGPT, that is being used to address this problem. So basically, it processes all words simultaneously and uses self attention to access any token instantly. So we will look at the architecture of how transformers actually work and how data flows in this architecture. So it is much faster, and it do parallel processing. So it can analyze simultaneously all words of the sentence. So it don't go sequence by sequence in each word. So we will look at the architecture of this transformer now. So this is the architecture of the transformer that you can see over here. So it has three concepts. So the first one is positional encoding. So basically it adds positional information to the words. The second concept is attention. So basically it calculates the relevance between the words in the sentence. And the third one is self-attention. So we will understand all three and this architecture diagram in a simple way using an example over here. So let's take a sentence as an input to this architecture. The sentence can be the cat sat. So this is a sentence that we are using as an example over here. So as soon as this sentence enters the architecture of the transformer, it is being broken down. So this can be our step 0. So the sentence is first broken down into vectors. So it can be the cat sat. So we'll break down into vectors like this, we can assign some vectors like this to each word of the sentence. Now we will call them as x1, x2 and x3. Now moving forward, after assigning the vectors, we will just move forward to a step 1, that is input encoding. So what is input encoding? Input encoding is basically the x1 that we have encoded over here. So in real world models, basically our model go through this embedding layer. So this is our input embedding layer, which converts the words into high dimensional vectors. For example, it can be 512 something something, but we have taken this for but we have taken these as an input for the simpler calculation. Now we'll move forward to our step 2, that is our positional encoding. So basically in positional encoding, transformer don't understand the order. So we add positions to it. For example, the sentence that we took, the cat sat. For example, we'll assign 1 to the, 2 to cat and 3 to sat. So these are the position of the sentence. So this is the sequence that we have to follow. So we'll basically add the positions to it. So the positional encoding can be position 0 is 0.1, 0.1. Let's say we have broken down position 2 into this vector and position 3 for sat is 0.3 comma 0.3. So we have just taken these position vectors. So it is for the, it is for cat and it is for sat. So we have basically created 3 positional vectors over here, and now we will embed it with the words itself. So the words are the, cat, sat, and the final input should be x plus positional vectors that we have created over here. So it would be 1 plus 0.1, 0 plus 0.1. So it would be 1.1 comma 0.1. So we have taken the 0.1 from here, and the first was 1. So we are just combining these two over here. You can see that for x1 that we have created over here, it is for the, so this x1 and this x1. So we are just taking the x values for it. So it is 1 comma 0.1 and it should be 0 comma 0.1. So basically we are just adding positions to the vectors itself. So basically it is input the and it says position. So the position of the is 0.1 over here. Similarly, we'll calculate for cat. It's 0 and 0.2. So we will just do 0 plus 0.2 comma 1 plus 0.2. So it will come out to be 0.2 comma 1.2. So it is the positional vector over here for cat. Now we will do it for sat, 1 plus 0.3 comma 1 plus 0.3. So it would be 1.3 comma 1.3. Now that we have the positional vectors over here, so our step 3 is self attention. Self attention. So what is self attention basically? So each word look at all the words including itself. For example, the cat sat. So if we are at the, so the will look itself also, but it will associate it with cat and sat also. So basically self attention says that how much should I focus on each word. So this is done using something called QKV. So Q stands for query, K stands for key, and V stands for value. So we'll move forward to our step 4 over here, where we will calculate the vector value for q, k, v. So q, k and v will calculate the vector values. So we will use the weight matrix for WQ, that can be an identity matrix maybe. We will just take the identity matrix, so the calculation becomes easy. For WK it can be an identity itself, and we will take WV as identity itself. So we have taken these weight matrices over here, but you have to basically train your model and change these weights as we are doing from the ANN itself. So we have taken this random matrix over here as an identity, but we have to continuously update these weight matrices in order to improve the accuracy of the model. So to make you understand things well, so I've taken the identity matrix because it will make our calculation easier. So these are just the identity matrices for now. Now we will compute it with the q, that would be x into wq, the weight matrix of the query, and k would be x into wk, repeat, x into wk, and v would be x into wv. So for calculating x1, we can just say for the, that is our x1, we will do it like this. X1 can be this, that we have calculated over here. This is the value of x1, 1.1 comma 0.1. So 1.1 comma 0.1. So we'll just calculate the value of q1. We are calculating for x1 the value of q, so we are saying it q1 over here. So if we do x into wq, and wq is identity matrix, and wk and wv are also identity matrix. If we do a cross product over here between the matrices, so the answer would remain same. Similarly, k1 would be 1.1 comma 0.1, and v1 would be 1.1 comma 0.1 itself. And if we take the value of x2 over here, that is 0.2 and 1.2. So for cat, that is our x2, it would be x2 is equals to 0.2 comma 1.2. And if we do the cross product of 0.2 with 1.2 with these matrices, so the answer would be same. The q2 would be 0.2 comma 1.2, and k2 would be 0.2 comma 1.2, and v2 would be 0.2 comma 1.2. Similarly, we will do it for x3. For that, the x3 value is 1.3 comma 1.3. So q3 would be 1.3 comma 1.3, and k2 would be 1.3 comma 1.3, and v2 would be 1.3 comma 1.3 itself. Now we will calculate the attention score for it. So that becomes our step 5. We'll calculate the attention score. So what is attention score over here? So basically we'll compute attention scores between a query and all keys using. So basically a query and keys. We are going to use this for calculating the score. The formula is q dot product of kt divided by root d. So d is basically the vector size. That is 2 in our case. You can see over here the vector size is 2 in our case. We are having 2 value each. Repeat. We are having 2 value each, like 2 over here, 2 over here, and 2 over here. So our vector size become 2. So we'll just take the root of 2 over here. So it would be 1.41 somewhere. Now we will compute the value for Q1 first. So what would be the value of Q1 over here? The Q1 would be the key, that is K1 came to be 1.1 comma 0.1, and the dot product between Q1 and K would come out to be 1.1 into 1.1 plus 0.1 into 0.1, that is our 1.21 plus 0.01, that would be equals to 1.22. So this is our dot product. So our score would be, we will just move to this side. So our score would be, we will calculate the score like 1.22 divided by 1.41. That would come around maybe like 0.87. So this is our score over here. Similarly, we'll calculate for K2 and K3 also. So K2 would be 0.2 comma 1.2, and K3 would be 1.3 comma 1.3. So similarly, we are going to calculate it for K2 and K3 also. So the value for K2 would be 1.1 into 0.2. Okay, and it would be 0.1 into 1.2. We are doing the dot product between Q and K. So this is Q and we have K over here. So Q2 is 0.2. So basically we are calculating in respect to Q1. So value of Q1 is 1.1 and 0.1. So 1.1 and 0.1, and the value of K2 is 0.2 and 1.2. So we are just calculating a dot product for it. So it would be around 0.34. Similarly for K3, it would be 1.1 into 1.3 plus 0.1 into 1.3. It would be around 1.56. So the score would be like 0.34 divided by 1.41, that would be around 0.24, and similarly for this 1.56 divided by 1.41, that would be nearly 1.11. So we have these raw scores over here, that is 0.87, 0.24 and 1.11. Now we will move forward to a step 6, that is to calculate our softmax function. So what is a softmax function? So we convert scores into probabilities using this. We convert it into probabilities. So softmax function is being represented like this: z is equals to e to the power zi divided by summation of e to the power zj, and this is zi. So this is a formula for softmax function. So we will calculate the value of e to the power 0.87 first. So 0.87 is the value of the score that we have for x1. So it would be e to the power 0.87. So it would be 2.38. Similarly, we'll calculate the e value 0.24 over here, and it would be 1.27. Then e to the power 1.11, that would be nearly 3.03. We will sum all this up, that would come around 6.68. If we add them all together, it would be 6.68. Now we'll calculate the attention weights for the three words that we have, the card sat. So we'll calculate the attention weights, that is represented by P. So it would be P1 is equals to 2.38 divided by 6.68. So 2.38 is E1, 2 and 3. So it is the value of E1 and the sum is 6.68 over here. So we will just calculate it, and the attention would be 0.36. Similarly, for P2, that would be 1.27 divided by 6.68. So it would be 0.19. And similarly, for P3, that would be 3.03 divided by 6.68. That is 0.45. So these are the attention weights that we have for the three words that we have: the, cat, sat. Now that we have calculated the attention weights, it's time for our step 7, that is output vector. So what is the output vector for it? Now we will use these weight to calculate a v vector, that is our output vector. So we'll calculate v by summation of attention weights and into v. So the output would be 0.36 into 1.1 in, and we have 0.1 over here plus 0.19 into 0.2 comma 1.2 and plus 0.45 into 1.3 comma 1.3. So these are the initial values that we got, and 0.36 is the attention weight for P1, that is the. Now we have output for all the three words. So this is for the, this is for cat, and this is for sat. So we have output for the, cat and sat. So we will calculate it. So it will come out to be nearly 1.019 comma 0.8. So it will come out to be 1.019 comma 0.849. So the new vector for the is 1.019 and 0.849, as we have only taken for the itself. So we are just calculating in regard to Q1. So this is a dot product for the first word itself, that is the. So we have the value over here as an output, and this becomes a new vector for the word. And to repeat it again for cat and sat, we have to do it for Q2 and Q3, that we have done for Q1 over here. In respect to Q1, we have done the dot product. So for Q2 and Q3, we will repeat. So if you have to calculate for cat and sat, so you have to do dot product in respect to Q2 and Q3 respectively. So now we will go down over here. So we have our step 8 now, that is add and norms. So what is this add and norms? So it is basically a residual connection. Norm stands for normalization over here. So our connection stays stable. So we do the normalization over here. And add is to basically retain the original inputs, like the original input is for the is 1.1 comma 0.1. So the output came out to be 1.019 and 0.849. So the residual is 2.119 and 0.949. So we have the residual over here, that is 2.119, and we have from these two value we have 0.949. Basically we have just added the value. So we have calculated the residual over here. Now after this we have the layer of normalization. We have got the residual from the art, and we have the layer of normalization, where we do mean, median, basically we calculate the dividend also in order to normalize, to keep the network stable. So how do we do this? Let's say we are taking the example of the itself. We have x over here initially to be 1.1 comma 0.1. Now the self attention value that we calculated for x is 1.019 and 0.849. So these are the values for x and z. So now we will just simply add these both, x plus z, that is 1.1 plus 1.019 plus 0.1 plus 0.849. Then we have the value over here as 2.119 and 0.949. So these are the values of x plus z. So this is basically the calculation of residual connection. This is the calculation for residual connection. And we will now move forward to normalization. So normalization computes the mean as we have just discussed. So we'll just calculate the mean over here. This was our step 1 of residual connection. Now we have normalization. So for calculating mean, we can just say we have 2.119 plus 0.949 as an residual connection over here that we have just calculated. We are just taking it, and for calculating mean, we'll just divide it by 2. So so it would be 3.068 divided by 2. So it would be nearly the repeat. So it would be nearly 1.534. So we'll compute the variance also for this. We'll see how the variance is being calculated. So we'll just do it like 2.119 minus 1.534 whole square plus 0.949 minus 1.534 whole square, and this would be divided by 2. This is the formula for variance, where we are just taking values over here 2.119 and 0.949, and so this is the formula for variance. So we will just calculate it. So it will come out 0.684 divided by 2, that is 0.342. So this is how we calculate the variance. Now we will calculate the standard deviation also. And to calculate the standard deviation, we will just use the formula over here. So the standard deviation formula is under root 0.342. We'll just calculate the under root of this value. That would be nearly around 0.584. So we have standard deviation over here. So it would normalize each value now. So let's normalize each value. And to normalize, we will just do it value minus mean divided by standard deviation. So the first value is 2.119 minus 1.534 divided by 0.584, and it will come around 1.002. So this is for first value. So now we are going to calculate the second value, that is 0.949 minus 1.534, and that is it divided by 0.584. So that is minus 1.02. So the normalized output is 1.02. 002 to minus 1.002. So this is our range. So this is a normalized output. Now we have our next step, that is our step 9, that is feed forward network. We basically feed forward every sequence into a network, into a small 2-layer network, maybe 2-layer neural network. So we will apply this 2-layer neural network to each word vector individually. So it would be like forward neural network. We can take a max function over here, and then we can just pass input, weights and the biases into W2 plus B2. So this is our forward network that is taking input like 2.119 comma 0.949. Now the hidden layer will work on it. Maybe you can use a value function over here, and then you will have an output that is of linear propagation. Linear, and then you will have an output that might be an linear projection. So this is how basically you plug in small dummy weights to see the mass inside it. And first is that the input embedding, then have a positional encoding, then we have calculation of that QKV value, then we calculate attention score, Softman function, then we predict the output, use add and norms, use a feed forward neural network. These are basically transformers work. So this is the basic working of transformer, and we don't see the sequence. In this, we basically see the whole sequence of the sentence together, like the cat sat. We take the example of this, and now let's see the architecture diagram over here. We have seen the math behind it. So now let's understand the flow. So we have the first input embedding layer and the positional encoding, like we have done for like this, the card sat, we just place it 1 2 3 over here in the starting itself. So let's take some other example, like I love India, and we want to translate this into Hindi. So we have to translate it like मैं इंडिया से प्यार करता हूँ. So we have to just translate the sentence. So the very first step is input embedding, that is being done over here, where every word in this input embedding is being converted into vectors. And then the positional encoding is basically adding the position over it, like 1 2 3, as we have seen. Now this input embedding, like I plus position 0, then we have love plus position 1, and India as plus position 2. So we have these three as an input sentence. Then it goes into this encoder thing. So it repeats n time, like layer by layer. We have a lot of layers over it. So it keeps on repeating it. So we have first multi-head attention over here. So what this multi-head attention basically do is, the model now looks at all the words in a sentence at once. But what does I focus on? Like the model is looking at whole sentence one, but I is focusing on love and India over here. So I is connected to this love and India over here. Then we have this feed forward thing over here. This is like after attention, it passes through simple neural network to transform the representation. Then we have this add and norms over here. Then in the output thing, we have this output embedding and the positional encoding over here again. It also repeats n time over the layer. The first thing is that output embedding plus positional encoding over here basically does is, now let's say if you're generating a Hindi sentence, so we have like मैं इंडिया से प्यार करता हूँ. So what is happening over here is, uh, when the model generates मैं over here in the Hindi translation. So it basically writes मैं and adds a position to it, that it is as position 0 and it is being replaced from I. So the position remains 0. And then it comes to India over here. So what India, when it predicts India, so it adds मैं and India together in a sequence. So India might be also having a position. So मैं India plus position over here. So the translation goes like this. Then we had this decoder block over here, where we have first have this mass multi-head attention. So what mass multi-head attention basically do is, when you are at May, so the model should not go to India. It should focus on in May itself. So decoder only sees May over here, and at step 2 it sees India. So at very first it should not see India when it is decoding May over here. So this multi-mass head attention basically do is masking the next word, so it focuses on the current word. Then we have this multi-head over here. So in this multi-head attention, basically decoders look at the encoder's output. For example, like मैं should be associated with I, and India should be associated with India, and pyar should be associated to love. So multi-head basically understand how the translation is going on. Then we have this linear softmax function that we have seen. It is being used for like calculating the probabilities over here. It is being used to calculate the probability over here. So this is how the architecture diagram basically works. It also get passed to a neural network. So this neural network only basically helps to translate the things from like English to Hindi sentences, like we have seen over here. So this is how basically transformers also work. So we have seen from ANN to the transformer journey. So we can just write it over here. Like we first covered ANN, then we went to DNN, then we saw CNN was required for like image recognition, and then we saw RNN, but due to memory issue, we required something called LSTM, and due to sequential thing that it is slow and it go word by word, we saw something called transformer to resolve all the issues that were there in LSTM as well. So we went from ANN. So basically we went from ANN to transformer, and transformer is the only thing that is behind chat GPT and everything that you are seeing over here. That we have ANN for like text recognition. We have DNN as an advanced version of ANN. It has more hidden layers, like more than 3 maybe. So we have the CNN for image, RNN for sequential thing, LSTM for a bigger memory maybe than RNN. Then the problem that LSTM have, we have an architecture called transformer that is basically behind ChatGPT. Then when you ask it to do something, for example, if you want a cat and you are putting it as an input to it, but you want a creative variation of it, like cat seeing its own image or cat sleeping, generative AI is able to do it. For example, if you're feeding a person's image in a model and you want that generative AI to convert that person into a female, like if you have given a man's image to a generative AI, it can even convert that man into a woman. That is the power of generative AI just by just few prompts. Now let's understand the AI specialization. We'll just move to AI specializations over here. So what are AI specialization? We have artificial intelligence, machine learning, deep learning, and generative AI. So artificial intelligence is a broad field focused on building systems that performs human-like tasks. And what is machine learning? It is a system that learns from data instead of relying on fixed rules. But what do you understand by this? Machine learning basically understand the pattern, like 2, 4, 6, and what is the number next to it. For example, if you have a tabular data with two inputs, input 1, input 2, and one output, like if you are giving 2, 4, the output is coming out to be 6. And for the second data set, you are just using 3, 6, and output is coming to be 9. Now, if you have a third data that consists of 4, 8, and you want to predict the output, the machine learning model will analyze that it is a sequential data. So, it will give you an output of 12. Now, moving forward to deep learning. So, what is deep learning? Deep learning is a specialization within a machine learning using multi-layered neural network. So, what is generative AI? Generative AI is basically a specialized form of a deep learning that generates new content out of a previous content. Now, let's move forward and understand where Gen AI lies in the generative AI positioning. So, at the outermost layer, we have this artificial intelligence. This is a broad field focused on building systems that can perform tasks requiring human-like intelligence. Inside this artificial intelligence, then we have machine learning. It uses our data instead of relying on a fixed rule. As we have seen over here, it can learn from two input data and predict the output for the third unknown data. So, now inside the machine learning, we have this deep learning. Deep learning is basically like a complex architecture, like a neural network. You just pass input to it. It has a sequence of number inside it, and it basically just process it and gives you an output. So you just pass an input, it gets to a complex neural network and generates an output for you. Inside the deep learning, we have this generative AI thing that is a specialized form of deep learning. So that is able to create a innovative content out of things. Now moving forward to what are the limitations of this generative AI. The limitation of the generative AI is your imagination basically. You can imagine anything and it would be able to generate it. For example, if you want a code, it can generate it. If you want to write a poem, if you want to start a startup, it can guide you with everything from the very base level. And if you are ability to communicate effectively with the AI. For example, if you're writing a code, but you are not able to give the tech stack to it, like what tech stack you want to use while building a website, so it won't be able to generate as efficient as when you give the tech stack to it. That's where prompt engineering comes in. So you have to tell the AI exactly what tech stack to use to build a particular website. Now, while prompt engineering is a skill of writing a smart, clear instructions called prompts to get an accurate and a useful response from the AI tools like ChatGPT, Gemini, and etc.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI. Now that we have explored the fundamentals from ANN, CNN, and RNN to LSTMs and transformers, it's time to take things a step further. From here on, an industry expert will guide you through some of the most exciting advancements in the field, including OpenAI's GPT, LangChain, and the art of prompt engineering. I hope you guys are ready to dive in.
So, we'll be covering the following topics as far as my course is concerned. What are the topics that we're going to be covering? We will be, of course, be covering. I'll start with an introduction to generative AI, right? So we'll be doing that in our today's session. Will be very high-level, broad brushstrokes. We'll be discussing introduction to generative AI in our today's session. And then what we will also be doing is we will also be covering topics specifically around why do I see that folks are saying there's an echo? So introduction to Gen AI. So I'm going to be talking about all the different applications of Gen AI, right? So how the industry is perceiving an industry point of view. So we'll be covering these topics broadly in our today's session. More of a business point of view, right? So where is this area? Where is this field sort of headed towards, and stuff like that? That's what I'm going to be covering broadly in our today's session. Then from after the session, we'll be going into a lot of detail, right? So I will talk about the transformer architecture, right? I'll be talking about transformer architectures. I'll also be talking about how some of the most popular GPT models are trained, right? And then we will also be discussing, we'll also, then once we understand how the transformer architectures are, how they work, then we will go one level lower. We will actually start discussing about, we'll be doing a lot of hands-on, specifically on trying out some of these architectures. So I'll introduce you to firstly the OpenAI. I'll be focusing on the OpenAI models for a good chunk of this particular course. I'll also see if I can show you some open source models, right? So there are different types of different ways you can access some of these models. So I'll focus primarily on the OpenAI models, but also show you how you can access the other models that are available out there. So the OpenAI GPT models, it's how to access them. Then I'll introduce you to LangChain, which is a library that is very popular. It's an orchestration library that helps you access some of these models very efficiently. Then we will look at some prompting techniques, right? So I'll of prompt engineering to be specific, right? I'll discuss about some topics around prompt engineering, all the different prompting techniques that you would typically have. So chain of thought, right? I'll talk about React. We'll also talk about tree of thought, and so on and so forth. There's a bunch of other things. So we'll talk about all of those, few short learning and stuff like that, FSL and stuff like that. So we'll talk about all of that under prompt engineering. And then once that is done, we will then get into retrieval augmented generation, which is also popularly referred to as RAG. So we will talk about RAG. We will understand how RAG works, and then we'll do a lot of hands-on on RAG as well. And then after RAG, I will also show you some more complex, agentic architectures, or rather simply put, let's say agents using LangGraph and stuff like that. So I'll probably be closing out the sessions at the end using agents and concepts of agents in LangGraph. So broadly, this is how we will go about doing things. In the later parts of the session, or maybe actually here itself, when I discuss OpenAI, I will discuss, of course, the GPT models. I'll also discuss some of the image generation models here as well. So how you could access the DALL-E kind of models, how can you actually generate content using the DALL-E kind of models. I'll also be discussing that in that session. So broadly, these are the topics that I'm going to be covering. Again, I don't want to, while we are covering one of these topics, of course, we'll end up covering some of the ancillary topics as well, right? So topics around this space as well. I know this might not be, all of these topics that you're currently seeing on the screen may or may not necessarily resonate with a lot of you because you may not know what this space is, but trust me, this pretty much covers the 80% of, I would say, everything that's out there today, right? So a good 80 is, 75, 80% of all the happenings in this particular space is fairly covered in the topics that you see on the screen over here. Let's start with the introduction to GenAI. So all of this, by the way, is LLMs only. So when I say OpenAI, GPT models, these are large language models only. When I'm talking about transformers, those are large language models only. So I'll talk about all of that as we speak. So here's the thing, guys. So let's start with the first topic today, right? Let's talk about what is generative AI, why all this drama about Gen AI, why has this suddenly become so popular, right? Let me agenda introduction to Gen AI. Perfect. So while I bring this up, I also want to bring up some presentations. Give me a second. So one of the good advantages of being in the industry while you're doing this is that I also get a lot of content from a lot of these companies out there. Let me show you some interesting content that I had got very recently from Bain, from Microsoft, from Accenture. Some lot of very interesting presentations out there. I'll try to bring some of that up. Easy to understand kind of slide or easy to understand kind of content. So you all have, when we talk about Gen AI, or rather, if you kind of talk about what has changed over the last couple of months, couple of maybe 1.5 year or so, 1 year or so, I would say, you've suddenly seen these tools that you see on the screen suddenly pick up pace. All of us agree on this, right? Yeah, Bard has become Gemini. Chat GPT has become so popular. Google has also launched Palm kind of models. Anthropic has launched an interface called Claude. Um, Perplexity is another tool. You have OpenAI has launched DALI. Um, Microsoft has launched Copilots. Yeah, the point is, you suddenly saw something change in this space, right? So, cut to 2 years, 3 years ago, we were still talking about, all right, how can I build a deep learning model that can do question answering, right? Or how can I build a recurrent neural network based model that can do classification? How can I use some of the existing BERT models for doing sentence similarity or document similarity? How can I use word to vec to, let's say, do something very specific in this particular space, like maybe classifications or, let's say, document similarity, question answering, so on and so forth. This is what we were talking about 2 years ago. But suddenly things have changed. Suddenly you started, ChatGPT was launched. And we have to admit that ChatGPT's launch is a marquee event in the history of AI so far, right? ChatGPT launching is something that will get etched in the books of history, the AI history forever and ever, right? So the moment ChatGPT got launched, it just, it was a jaw-dropping moment for everyone. People suddenly started seeing some, and I still remember a lot of these posts coming up on LinkedIn, on Twitter, and everywhere where people started saying, this is revolutionary. This is going to change how we look at AI anymore. This is going to completely put people out of jobs, blah, blah, blah. That fear is still there even today. So this is what a outsider is looking at, right? So you're using the chat interface through Chat GPT. You're asking it questions. It's able to do an amazing job of answering some of these questions, right? It is able to create content. It is able to surprisingly create content with amazing levels of accuracy, um, levels of accuracy that are far beyond what, let's say, any human or decent, it would very easily beat a decently skilled human in some of these, some very, very specific tasks. You had seen these Gen AI models beat um, people in, or rather students in bar exams and SAT exams, right? Stuff like that. Question is, like, where did this suddenly come from? Like, was this something that happened all of a sudden? Does this have anything to do with anything that we've learned so far? Or is this completely new, right? The answer to it is a bit of both. It has a lot to do with what we have learned so far, yet it is completely new. Um, it has a lot of eerie similarities to stuff that we have discussed, that we may have spoken about so far. Yet this has structurally, fundamentally, even conceptually, this is very, very novel, very new in this particular area. Um, and that is why you suddenly saw this spike in the number of apps that started coming out, number of chat interfaces that started picking up, and so on and so forth. So, long story short, new field of AI has suddenly emerged. New tools came in, and suddenly it seems like AI has become a lot more easier than what you and I would have imagined so far. It suddenly feels like, man, why did we learn all that we've learned so far? And this seems super easy. right? You could just open a ChatGPT interface and get it to do things which you would have otherwise struggled quite a bit with traditional AI systems. So suddenly, even I went through this brief period saying, okay, am I going to go out of job because I spent a lot of time in AI, and am I going to go out of job? And I decided otherwise to kind of ride the wave rather than try and sit down and sob about it. That's a different story. We'll come to that later. But here is where we are. Okay. So now the question is, what is it about Gen AI? What is it? How is generative AI similar or new in whichever form or shape? Right. So let's talk about that. Um, so if you remember, we spoke about this prophecy, right? So this AI prophecy or this AI ambition, aspiration of being able to build something like a Jarvis, right? Something like Terminator, artificial general intelligence. You all must have heard about artificial general intelligence. So, what is artificial general intelligence? So, when you talk about AI, when you talk about artificial intelligence, AI can be nicely split into two parts: artificial narrow intelligence and artificial general intelligence. The key operative difference between the two being here: artificial narrow intelligence and artificial general intelligence. What is the difference between the two? See, the difference between artificial narrow intelligence versus artificial general intelligence um, is very simple. So far, we all have spoken about all of these different applications of AI, like whatever you see on the screen, right? Be it, let's say, your Cortana, your Apple Siri, your Google Now, your self-driving car, your recommendation systems on YouTube, your AI capabilities on, your machine learning AI capabilities on your Uber app, any kind of AI that we may have done so far, ADAS as well. ADAS is a very, very good example as well. Even ADAS, which has LiDAR, ultrasound capabilities to identify what things are around it, stuff like that. So all of these are great AI capabilities, but they are all artificial narrow intelligence. What do I mean by that? Each of these activities, so take for example, YouTube as a good example. If you take YouTube, YouTube has a lot of intelligence in it. One very good example is recommendation engine. So the recommendation engine that you have that is recommending the next video that you should watch on YouTube is only built to do just that piece of work. It can only do that part of it. It cannot, I cannot use that same piece of AI or that same model to do, let's say, to identify what maybe I cannot use that same AI to predict how long will you watch that particular video for, or I cannot use the same model to identify if you would purchase, let's say, the YouTube premium subscription or not. Right? I cannot let it do multiple things. It can only do one very, very specific activity. It'll do a fantastic job of that one activity, but it cannot do anything beyond that. It is just trained to do that one piece of work, and it'll just do that one. It cannot help you. That AI model which predicts if which video you will likely watch cannot tell me, cannot I cannot use that to generate subtitles. I cannot use that to summarize that complete video. I cannot use that same model to do other things. It can only do one piece of work for you. To do the others, you will have to build other models. You'll have to build separate solutions for it. And that's how we've been doing it so far. To solve a specific AI capability, you need to build one model for it. You cannot have one model that does everything, or one model that has a wider application. It is very narrow. It's not to say that it is bad, right? I don't want you all to misunderstand that this is bad. This is not at all bad. This is great. It's just that it is capable of doing one particular task at a time. What we are, but the objective of the field of AI is to try and get to build something like a Terminator, artificial general intelligence. I want to build, or rather, we intend to build I don't know if you watched Dennis the Menace. I want to probably build a robot that has got that kind of intelligence in Dennis the Menace, or maybe in Jetsons for that matter. We've all grown up seeing that kind of intelligence, right? So in science fiction, in movies, some form or the other, Skynets, Terminators, your Jetsons being another smaller silly example. The point is you want to kind of get there. Small wonder, not little wonder, small wonder. Yes. Um, Vicky from Small Wonder, one of my favorite shows right at that time. Um, right. So point is, how do you get there? So today we don't have any applications of artificial general intelligence, right? We are trying to get there. We are far away from it. We are a good few, maybe I would still assume like a full good few decades away from it. But that's where we want to get to. That's what we would want to really try and aim at, right? Artificial general intelligence. What you and I have is AGI, right? Um, we can do multiple things all at the same time. I can drive a car, I can cook food, I can teach my child, I can learn something, and I can also attend a session in parallel. I can do so many things in parallel with decent amount of accuracy across everything, right? That's what we're trying to get at. Artificial general intelligence is very human-like intelligence. Now, the thing about AI, my friends, is that AI is such a new space. Um, when you talk about artificial intelligence, we are more often than not always talking about artificial narrow intelligence capabilities. We're not talking about artificial general intelligence capabilities at all, right? Because we're a couple of decades away. But what generative AI has done is it has helped us make a huge leap towards AGI, but we're still far away. But it has gotten us far more closer to general intelligence than what we would have done had we progressed in the current phase. If we were to build the same kinds of pieces of technology like what we're currently doing, it would have taken us a very, very, very long time to get there. But at least we were able to make a massive stride in that direction. Why? What is it about generative AI which makes us believe that we've gotten closer to general intelligence? Remember, everyone, I am not saying we've made progress on AGI. We haven't. We are still talking about narrow intelligence, but we've been able to make much larger progress towards AGI using generative AI models. I'm not saying by any means that we've gotten closer or rather we've made progress on AGI itself. The objective of a company like OpenAI is to be able to build AGI. That's what Sam Altman has always talked about. He always keeps saying, we want to build AGI, we want to build artificial general intelligence. But I mean, who am I, right? I'm a small fish in the pond. But if you take, for example, the who's who of the industry out there, they all believe that we're far away from it, right? We're at least a good decade and a half away from it. We need more such wonders like ChatGPT to happen before we can get there. Right? So that's essentially, um, if you were to consider, let's say, colonizing, let's say, another planet as the end objective, our Chandrayaan 3 was a huge leap towards that. Consider ChatGPT or the generative AI as your Chandrayaan 3 success. Have we gotten closer to colonizing the planet? Maybe yes. But have we accomplished anything in that objective? Probably not. We made a huge leap towards that direction. So that's a fair analogy as far as how you should treat generative AI as. But the beauty of this space, my friends, is that with that small leap itself, we are seeing such huge changes in how the industry has started to use AI in their day-to-day basis. The good part is you and I, we have the opportunity to ride the wave and to kind of stay on top of it, right? So you are all kind of getting into the field of AI exactly at the time where this transition is happening. We've kind of made that leapfrog. It's that leapfrog moment. What is it about generative AI that makes us believe that we made that huge? Let me explain. Let me show you a couple of things. Why we say that. There are certain very interesting capabilities of generative AI that makes us believe something like this. Let me show you an interesting presentation from Microsoft. This is a Microsoft presentation. They had actually presented this to us it's a public presentation. So what is it about Gen AI that makes us believe that it does things differently? See, generative AI, right? And these are examples, right? It can do far more things than what we are currently seeing on the screen, of course. But for example, you all have used the chat interfaces, right? So this is a very, very good example of it. So if you take, for example, the prompts, so you can actually just ask it a question and it can simply respond back to you. You can follow up on those questions as well. You can sort of have a genuine human-like chat, and it'll actually respond back very, very much like a human being, right? So its understanding of language has significantly improved since the last time, right? So models now understand language very, very, very well, right? So than they would have done probably using any of the other regular AI models, right? That's number one. So understanding as language has significantly changed since since the time we know what has happened in this particular space. Or even if you take, for example, the um, your BERT models, you take any of your other models that you've learned that you may have learned about so far, these models are far better at understanding language. Not just that, these models are also very, very good at understanding code, right? They're not just good at understanding language, they also understand code very, very well, right? So they can actually write code for you. I cannot tell you how many times, right? So I'll tell you a good example. So today we built a capability in my own team. We built an app in my team, a product in my team, and then we've decided that we should do a complete code rehaul. So we've written a lot of stuff using object-oriented programming, and we decided, you know what, oops, in our setup makes no sense. Let's change it to functional programming. And we just took that complete code bit by bit. We put it on ChatGPT, asked it to convert this into functional code. 20,000 lines of code was rewritten by ChatGPT in a mere 3 days. 20,000 lines of code, we were able to just restructure our complete code base in 2 to 3 days. It's just amazing, just the kind of capabilities that we're starting to see something like a chat GPT could do. Those are the kinds of things. I can also talk about how content generation has changed, right? So one of the things about generative AI, because it is able to generate content, it is able to create new content. We can also get it to create images. I can tell it what image I want, and it actually creates that beautiful image for me, basis what I ask it to create. And not just this. Now you also have videos that you can create as well, right? So you can also get it to create some videos. I can also use Sora and stuff like that that I can also create too as well. I'll show examples. I'll show a lot of examples as we go along for the next couple of weeks. I'll just be showing a lot of hands-on examples itself. So don't worry. Again, I want you to understand that these are the kinds of some of the applications of generative AI. When I say content creation by API, API essentially is simply nothing but an endpoint. You could have a model that's sitting somewhere, and you can interact with it. Don't worry about this line over here. I'll exactly explain what I mean by it. Now, I want to show you something slightly more interesting here. So let me pull up another interesting presentation. This is another presentation by McKinsey. Again, I want to talk about a couple of slides on this. Lot of companies these days, right? They have been using traditional AI, right? So they've been doing pattern recognition, and stuff like that, like traditional AI capabilities. Now with Gen AI, you could do a lot of, you could do code generation, you could do image generation, you could do enhanced pattern recognition. Some of the capabilities that we would have probably wanted to have solved earlier, we would have to solve it much, we can solve it much faster right now. Why are these models so good, right? So why are these models that we speak about as far as Gen AI so damn good, right? Again, approximately what you see here is, and this is again a public presentation by McKinsey, you can actually download it from their website. So what they're saying is, these models are so good because they've been trained on massive volumes of data, right? So for example, one example here is, if you take any of the GPT models, GPT-3, for example, was trained on 45 terabytes of data, right? A complete crawl of the complete internet was used. Some lot of Reddit content, more than 250,000 books, the whole of Wikipedia. Man, that's almost all of the internet that you and I have access to. All of that data has been taken, and they have provided that to the model. The model has a very interesting way of learning. We'll talk about how these models learn. The way they learn is very much to predict the next word, right? So given a particular sentence, given a particular word, they try to predict the next word. So when I say the models have been trained, they've been trained for a classification problem to predict what the next word is. Given a set of sentence, given the first word, predict the next word. First two words, predict the third word. First three words, predict the fourth word, and so on and so forth. So you're sort of predicting always the next word in the sentence. So point is, that model is 175 billion parameters. When say 175 billion parameters, what do you mean by parameters here? Weights and biases. These are your weights and biases. A total of 175 billion weights and biases, not million, billion. Okay? Not features. They're not features. They are the weights and biases. They are your parameters inside the model, right? And had you trained this 45 billion terabytes of data with 175 billion parameters on one GPU, it would have taken you like 32 years to train that model. It would take you 32 years to train that model, right? So you can imagine, if you were to train it for 32 years, then you would never get the model. So what do? How do you accelerate that training? You either reduce the data, or reduce the model, or throw more compute at it, right? I'm kind of oversimplifying it here, but when I say throw more compute at it, basically get more GPUs. Now it's that part which is where a lot of AI wars are happening right now, right? Of course, to train such large volumes of data, such large models, you need more and more GPUs. But to get more GPUs, you need GPUs are not made randomly, right? So GPUs are very expensive. You need to make them. So who makes these GPUs? It's NVIDIA's of the world, it's the AMD's of the world. They are the ones that are making these. And NVIDIA is in such a beautiful spot here that they have really cashed this cow left, right, and center. Right, so they're doing a very good job with how they're positioning themselves. Anyway, we'll talk about that later. Point is again that it's because of that reason, because there is a need for compute. You started to see that you need more and more models, more and more compute. More and more GPUs to accelerate the training. But then even after that, right? So let's say you do all the training. What do you get? You get a model which is 800 GB inside. Very simple. GPT-3 is 800 GB. Can you imagine a model that's of the size of 800 GB? It's that big. It's not storing data. Data is 45 terabytes. The model is 800 GB. So it's just these 175 billion weights and biases that are being stored, and the size of that is approximately around 800 GB. Can you load an 800 GB model on your machine, on your personal machine? Of course no. You just cannot, right? Your machine has 16 GB RAM or 32 gig memory. Maybe if you're rich enough, you'll probably buy a 128 gig memory machine. How can you load a 800 GB machine? How GB model? That is where API is coming. So the model cannot sit on my machine. I cannot download the model. Unlike how you and I were building models earlier, where we took the data, we loaded the data in our local, we put it in a folder, we take the code and we actually build it in our machines. You install the libraries on your machine and you build the model. There is no more model building, my friends. Model is not even going to be built by you and me anymore. Model is built by Microsoft, by Amazon, by Google, by Metas. They are the ones that are going to be building the models. You and I are not building the models anymore. You'll be using the models that they've built. Model building, not so much any of our job anymore. When I say our job, of course, unless you choose to work in that space where you want to build models, that's a different story. My point is, as end users, you and I are not building the models. You and I are using these models. But where are these models? These models are going to be hosted somewhere else, in cloud, right? You can load these models, but you will have to set up a data center to host a 800 GB model. You need a data center. You need a huge data center that has 800 GB in terms of RAM. You need a racks and racks of RAMs to support an 800 GB model. What do you do otherwise? You put it on cloud. You let Microsoft manage this and say, you know what, I don't care how you manage it. This is the model. You manage it. OpenAI has said, Microsoft, you manage this model for me. You host this model. Provide an interface where I can access this model. Right? I want to access this model over internet. So I just give me a layer, just like how I access a website. I want an interface. I want an API layer. That's where APIs come in, where I can just simply query and I can get the response. I don't want to be in the business of actually loading this model my own self. So this is almost like a service, model as a service. Exactly. So what do you see here? See, Gen AI, my friends, is not new. Gen AI is new, is not at all new. Right? This is the part that I was talking about, right? If you remember, I spoke about, hey, is Gen AI completely new? Well, maybe not. It's actually not completely new. It has been there for a good 7-8 years now. So that this is a good view of all of that. The model, the foundation of this particular model was first published um, in the first published in 2017. That to December 2017, a paper called "Attention is All You Need" is the paper that was first published. What happened after that? This paper took the world by storm. Why? This paper is everything that kind of completely changed, right? This is a game changer. What happened here? So I'll talk about this in much more detail when we discuss the transformer architectures. This paper is the paper that introduced transformers to the world. So I'll give you one example. So far, you all have learned RNNs. I'm assuming, right? You all have learned RNNs, recurrent neural networks. In an RNN or LSTM for that matter, or any of your models. So if you take, for example, a sentence which has W1, W2, W3, W4, W5. So let's say 5 words or how many ever words that you have in an RNN or an LSTM, you're essentially passing the current word as an input, right? And then you could potentially predict the next word as an output, right? And then of course you have a bit of recurrence over here, which is, let's say, an RNN or an LSTM, so to say. You could pass the current word as an input and you can predict the next word as the output. Then you can take these 2 words as the input and then you can predict this one as the output. Then you can take these 3 words as the input, then you can predict this one as the output, and so on and so forth. So the training in this particular case, right? How did we learn the dependency between one word to another word? You of course you had to take the first word, predict the next word, take the next 2 words, predict the next word, take the next 3 words, predict the next word, and so on and so forth. So you had to learn it like a language where you had to move from left to right or whichever way, left to right, right to left, whatever. Point is that you had to sequentially learn the data. Language is a sequence, is a collection of words. There is an element of sequence associated with it. So you kind of learn from left to right. Now, in the process of learning from left to right, especially when you have large volumes of data, there are issues of losing dependencies, right? That's why LSTMs came in or GRUs came in to kind of address for those long-term dependencies and so on and so forth. But you still were learning sequentially. So when you learn sequentially, it is very slow. The learning process is super slow, but you still were able to do a decent job of the whole learning process. And what these new models did, firstly, what transformers did differently, right, is they completely took away this concept of learning sequentially. They said, no more learning sequentially. You don't need to learn sequentially anymore, right? Why do they say that? They say, look, given any particular word, this word has dependencies before this and after this. So that's where they introduced a concept called as attention. Attention is a new concept. What it tried to do is it tried to say, look, when you look at a sentence, when you read a sentence, if you take any one particular word in a sentence, so for example, if I say, I had an amazing day at the park, rather, an amazing, right? I had an amazing day at the park. If you take a sentence like this, every word in some form or the other has some kind of a dependency on the other words that you see over here. When I say I, I is of course partially dependent on some of the other words. If you take the word amazing, amazing is talking about the word day. Amazing is talking about the word I. Amazing is also somehow talking about, is also addressing the park, right? And if you take, for example, park, park is again dependent on the word amazing. Park is dependent on somehow the word day, and so on and so forth. My point is, when you take any sentence, every word in a particular sentence has some form or the other, some kind of a dependency with its surrounding words. So, and those dependencies, if you are able to capture it differently, rather than simply just trying to learn sequentially, if you capture those dependencies differently and you capture all of those dependencies to some kind of a numeric representation, like some kind of a more efficient embeddings, what you could possibly do is you can just take these embeddings and then simply pass it into the model. So you're eliminating, we'll discuss this in much more greater detail when we discuss transformers. So the point is you're eliminating this sequential learning aspect of models. When you eliminate the whole process of sequentially learning, you are accelerating learning. And the concept of this, exactly, you can learn parallelly. And when you can do parallel learning, you can do a lot more epochs. Your fine tuning, or rather your tuning, could be much faster. The complete math becomes so much more simpler. One of the problems with LSTMs and RNNs is because the math has become so complex that you cannot learn with large volumes of data. But what transformers were able to do is they kind of broke that complete sequential learning down into a very simple, uh, you know, simple learning process, like how you would learn any of the other convolutional neural networks, or even for that matter, a regular feed forward neural network. They just made the whole learning language a very simple exercise. Because of that, these models have become super. I mean, you were able to learn language very fast, and secondly, you could go into far more. You were able to also extract a lot more detail about these transformers as well. We'll talk about transformers in much greater detail, but the point that I want to make here is these transformer models, because of the introduction of these transformer models, it completely revolutionized the whole learning process of language. Learning language became so much more faster, so much more simpler, and that made it, that kind of added so much more ease with which how people could learn, or how these models could learn. That was one of the reasons why the 2017 paper is a massive leap. It's almost like somebody was saying, right? It's almost like I was reading about it somewhere, and somebody said it's almost like somebody from the future kind of came, because this architecture is so different from how we have learned neural networks so far, right? It's very radical. It's very different from how we have learned language so far, because all that we've learned RNNs, we've learned LSTMs, we've also learned encoder decoder sequence to sequence models. Point is, they're all learning sequences. And suddenly in 2017, somebody publishes this paper and says, all that you need is attention, forget about sequences. Sequences doesn't matter. You just need to know how to encode those dependencies very well at the beginning itself. If you encode those dependencies, everything is addressed. Which is why the paper says attention is all you need. All that you need to do is some time of attention. Everything else can be taken care of. So this paper was so radical. And somebody was also saying, right? I was listening to a podcast. It was almost like somebody from the future came in and kind of whispered this architecture in somebody's ears and then left. I'm currently watching Lord of the Rings, the Amazon show, that Rings of Power. Um, it's almost like how the rings were, formed, right? So you have Sauron coming in and whispering it in the ears of Celebrimbor on how to, forge the rings. It's exactly like that. It's almost like that. Like somebody just came in and whispered in the ears of Google and said, Sauron is the fallen angel, right? Exactly. So it's almost like somebody just came in and whispered how this architecture sort of be created. It's brilliant the way they've written the architecture. And the point is that once that's sort of created, um, once that architecture was published, you could see what followed after that. 6 years down the line, my friend, you have seen one of the most revolutionary products that came out from there on, right? So you have of course the OpenAI models coming up. You had llamas coming out by Meta. Um, Hugging Face launched their models. Uh, Anthropic launched their models, and so on and so forth. So many models got launched. So many models got launched. This was still very old. Sora came in. Lot of things happened in this particular space. So yeah, look, I mean, so many different people kind of building their own models right now. Even in as we speak today, and this was I think one of the recent posts by EY on how AI is evolving in India. I can actually show you that as well. Let me just show this to you. Yeah, this is the India outlook for Gen AI by Ernst& and Young. They very recently published this. Um, Fairly very cool on how they kind of published it. They're talking about how some specific areas where I think let me just go into this a little. Yeah, so a lot of people focusing in Indian organizations, a lot of the work that's happening right now, coding assistance, document intelligence, and so on and so forth. A lot of interesting work that's happening already. There are companies that are building these models itself. Somebody spoke about Bharat GPT. Yeah, there are a lot of companies building their own AI models as well, right? So again, super fast. By the way, these images are all created by OpenAI. Um, all the images that you're seeing here, they're all created by them. Here are some Indic LLMs, right? So Ambari, Kannada, Open Hathi, Bhashini. This is the government of India's capability called Bhashini. Yeah, so a lot of Bharat GPT. Somebody spoke about Bharat GPT. Yeah, here you go. These are all the different capabilities in the India space as we speak today. Um, Sarvam was actually the first company called Open Hathi. They actually did a fairly good job as well, and all of these companies are doing a very very good job right now. And in my opinion, they're doing a fantastic job as we speak of AI. All right, so I don't want to go into too much of the detail around how AI is working, but as you can see, there's a lot of Indian companies as well in this space, right? So that are doing that are doing a very good job, right? So there's a lot of Indian ventures, AI ventures that have been doing a fantastic job in this particular area as well. They've also secured a lot of funding by themselves. But yeah, okay, let's go back to what we were discussing. So huge advancements in the field of AI. That's what I wanted to talk about since 2017. Yeah, I don't want to get into this, but I just want to talk about this. This particular slide is again very interesting, in my opinion, because see, the point that I wanted to speak about, right? Who is building these models? Not everyone, right? Very few people are building these large language models, these large Gen AI models. The only few companies are building this. And if you see those names at the top, very few, these are all big names, right? So these are all big names that are being built. Of course, now you also have some of these Indian companies also building their own models by themselves. But point is, Some models on text, some models on code, some on image, some on audio, video, 3D, blah, blah, blah. So many different models that are now coming out, but all of these models in some shape or form are all built on large volumes of data. And these large volumes of data is exactly what we are talking about as far as, or rather, these large models is the size of these models is exactly the reason why we require different kinds of infrastructure to handle. So the way you deal with these models is going to be very different. The infrastructure requirements are different. The modeling requirements are different. So if you're not going to build the model, then how do you access these models? So what do you do with these models? How can you customize these models for your own requirements? Because you're not building the model, then how do you get the model to work on your data? How do you get it to do what you specifically want it to do? So those things we need to discuss, and there are some very new design patterns that have emerged over the years. RAG being one of the most very common, very popular design pattern that has emerged in how you can use some of these models. But we can discuss them into much greater detail. So let's go back to this. So what are we saying? We're saying, look, AI, massive uh, transformation in the space, um, huge leap towards general intelligence. Lot of very interesting things that have happened in this space since 2017. 2017, the paper Attention is All You Need was like the start of all of it. And then very interesting things followed. Now, let me talk about the value chain of this. So, who is making money? The value chain in this whole Gen AI space, right? Again, a business perspective, we'll get into the technical details, but a business point of view, very important for you to understand because, again, the space is super ripe. So, who are the ones that are actually making a lot of money here? So, let's talk about different personas here, right? Let's take a couple of examples. There are, sort of broadly speaking, there are 4 to 5 different personas here, or 4 to 5 different types of stakeholders involved in this whole thing. At the bottommost level, you have companies like these are your, um, these are sort of your cloud providers. So it can be companies like AWS, it can be companies like Azure, or Microsoft for that matter, and so on and so forth. So AWS, Azure, cloud providers. These companies are providing compute. Right? They are the ones that are providing the data center. Right? Why are they important? Because they are the companies that are going to be providing the actual compute for these companies to host the models. So it's these cloud providers where the models are actually hosted or trained at. But who is actually providing them these models? So who's actually helping them build these models? So of course, on top of this, they are the companies or these research companies that are building these models. The AI research companies like your OpenAI, your Metas, and so on and so forth. Of course, Microsoft and they also of course have their own um, um, they of course have their own AI research teams as well. My point is, it's these research companies that we are talking about over here. Um, so you have the AI research companies, you have the cloud providers. But under the cloud providers, there is one specific, another one specific piece that I'd want to call out here, which is the hardware provider, the OEM manufacturers, the hardware manufacturers, NVIDIA's exactly, Amir and Ali, right? So it's companies like NVIDIA, the hardware providers. So you have the hardware providers like your Intel, NVIDIA, AMD, and so on and so forth. Cloud providers like your Azure, AWS, right, GCP. Research companies like Meta, OpenAI, right? You have, of course, Microsoft has their own research company, research division. Amazon has their own research division, and so on and so forth. Of course, all of them. Google, yeah. So of course, Google Brain, and so on. DeepMind, which is their research division, so on and so forth. So again, these are three personas, very important personas. Clear so far, everyone? These are the three types of stakeholders in this. Then who else do we have here? So the models are built here, right? So necessary computers provided, models are built. Now what do you do with these models? Then comes, again, two cohorts, I would say, from here, two groups from here, right? On one side, these are companies that are no, not consulting companies. These are application, or rather, these are the product companies. These are AI product firms. They are all the AI product companies. And then you have developer tools or capabilities, right? So the AI development tools, development capabilities. What do I mean by this? So on one side, you have, you know, people building your co-pilots, right? Your chat GPTs. You have um, you have tools like, for example, your Adobe Firefly, Gemini, exactly. All of these, chat interfaces, your end consumer products are being built. Consumer B2B, B2C products that are being built. That is all available here for sure, right? And on the developer side, on the dev tools, you're talking about your LangChain, and this is majorly open source. LangChain, your Llama Index, and so on and so forth. So basically, these are open source developer tools. Again, because they are essentially going to be building them to build better capabilities themselves, right? So they are open source models, open source companies. They're building platforms. Some are closed source platforms, like your Langsmith. So you want to build some AI models or whatever. You want to do some monitoring. You would want to do some. So you want to, let's say, host a model in your environment. You want the security around it. You want application level access controls and stuff like that. All of those basically are going to be sitting here. And then on top of it, actually, these companies might also be using them, but I just want to put them here because there is like sort of an overlap between, because they are also directly working here. These are also working here, but these are also, of course, using developer tools and they're contributing back as well. So it's almost like a producer consumer. Prosumer is sort of a new word over here, but point is they're also interacting with each other. Then comes the topmost layer. And again, over here, there are probably, again, two boxes here, right? So B2B users or your final users. And then there are also, at times, somebody spoke about, consulting companies and so on and so forth. So you can, of course, add one more layer over here in between, which is the consulting layer. And then you have the B2B users as well that are sitting on top of it. So you might have users here, or you can also have users here, depending upon how you're building these models. The point that I'm trying to make is these users are users like you and me. It could also be companies like your company, my organization, where we are using GenAI to solve a specific problem, and stuff like that. Then when you are talking about this value chain today, so let's take a very simple example. So imagine I have to, let's say, build a small. So let's say today, one of the things that Gen AI can do a very good job of is generate new content, right? Generate new images for my marketing teams. So where are my marketing teams? My marketing teams are here. This is my marketing team that creates this content, right? So how are they going to be using it? They are probably going to be using, they're probably going to be sitting here. They're probably going to be using one of the tools that we have over here, like Adobe Firefly or something, or maybe a Chat GPT. They would probably just be simply using it. Those are built by either your Microsoft of the world or the Googles of the world or Adobe's of the world. They are built on top of your Azure or something or AWS, SaaS offering, and they require NVIDIA, Intel, AMD. So today, if you look at it, the companies that are making the most amount of money are here. It's actually this probably is the only company that's making a lot of money. None of the others are making any money. The cloud providers are not making any money. The cloud providers are in this race just to make sure they have a competitive advantage. Your Azure, AWS, they're not making any money out of this today. They're charging you, but the reality is they are not making any money by them for themselves. They're probably, in fact, even losing money in certain instances. It's these OpenAIs. Is OpenAI making money? Probably not. OpenAI is also probably not making any money. It's only the hardware companies that are probably making money in this case. Some AI product companies may be making some money, but very, very early days, right? Some AI companies, product companies might be making some money, very early days. And as far as the end business users is concerned, in specific areas, yes, the business users are making some money. I would not say a lot of it, but they are, of course, they are sort of making some money in specific areas. They are making money for sure. Again, from bottom to top, the folks at the bottom will make always the most amount of money. The consulting companies that make money anyways. These consulting companies will make money on your dead body as well. So these consulting companies, hopeless, these Bains and McKinseys of the world, they'll make money anyhow. Of course, they're making a lot of money. They just have a new thing to sell, so then they'll sell that thing, to you. And it's not my perspective. The point is, they of course will make money any which ways because that's their niche, right? How much ever we think they're useless, they're equally useful because you need them to sell something. They have a certain brand value. They do sell a lot of things, especially in an enterprise setup. As much as I hate to have them, they do a very good job of selling things within my company. So I do use them in my own company to sell things in my own company to my leadership, especially. But the point is, this is the value chain today, as far as generative AI is concerned. It's who's making money is the hardware providers that are making money. NVIDIA is making money. Nobody else is making any money here in this whole thing. Probably some of the end companies like your company, my company, is probably making a little bit of money, but otherwise, everybody's currently spending money on this. Everybody's investing. Cloud providers are investing. They're not making any money out of it today. Honestly, they just want to stay out there. But because if they've got a foot in the door, they can make themselves indispensable. Trust me, they'll make a ton of money here. Maybe not today, but eventually they'll make a lot of money. The other thing, my friends, is if you take a product like Chat GPT, right? Chat GPT is built by them. So in the case of Chat GPT, OpenAI is playing both of these roles. They're also giving you some developer tools as well, right? So for people to build some capabilities on top of GPT. So OpenAI has a play in both of these areas. If you take, for example, something like Microsoft Copilot, Microsoft is playing the role all the way till there, right? So they have their models, they of course have their research teams that's building the product, they have their product teams that's building the product, and then they're selling it directly over here. So they're sort of playing a much larger game. NVIDIA, interestingly, also has a play here all the way up until the top, almost here on this side. NVIDIA has got some play, but that integration is not very strong. But at least until the research company level, they do have a play. They are integrated until that particular point. So yeah, Microsoft, by the way, also has a consulting org over here. Microsoft also has a consulting org wherein they are also making a lot of money all the way up until there. So their consulting team is also probably making some money out of it. But yeah, when all of them are searching for gold, one become richer by selling a shovel. Yeah, I mean, they're not selling shovel right now. It's yeah, I mean, it's a modern day gold for them, right? GPUs are everything. They're just capitalizing on the demand at this point in time. It'll get commoditized very soon. It'll get commoditized. See, I think all of this will die down in the next, especially the cost factor, right? This will die down. But what will remain is adoption. So what I mean, if anything, the cloud provider should simply be playing the role of for adoption. The hardware providers, if they are trying to play the game of money here, they'll unfortunately lose in the longer run, because if not Nvidia, Intel will make money. Intel's playing catch up here in this case, because Intel doesn't really have a lot of footing in the AI space. They do have some of their systems, but it's very, very early for, I mean, I wouldn't say early, but they don't have a huge partnership in this particular space. Is AI more like a hype? Absolutely not. This is one thing I want to clear. This is not a hype by any means, because AI, unlike blockchain, is not something that has come in the last 2 years, 3 years, 5 years. AI has been there since 70 years now. It is a massive leap in this space, which is why you start to see a lot more progress happening suddenly out of nowhere. Otherwise, you would not necessarily observe this kind of uh, sudden discussions in this particular space. Yeah, it's been there for 70 years now. This is not by no means a hype. The current setup is a bit of a I would say the current situation that the market is in a bit of a, everybody's running like headless chickens to try and see what they can do in this. But the reality is, if you want to stay invested you need to kind of stay invested for long in this. Right? Don't make short-term investments, short-term gains. Don't try to optimize for that. That's the only thing. I read a very, very interesting quote the other day. There's a concept called Amara's law. Google it. What Amara's law says is, the industry has this tendency to overestimate the impact of a piece of technology in the short run, right? Industry has the tendency to overestimate the impact of a particular piece of technology in the short run and underestimate the impact of it in the longer run. So if you want to really make something out of this, if you really want your company to stay ahead, stay invested for long. Don't try to optimize for short-term gains. So the best way to do that is build good foundations, right? So build the right kind of skill set. So if you have an organization, if you're running a company, or if you are, let's say, in a leadership role, and if you are trying to, let's say, guide people on making the right kind of decisions, you need to sort of stay invested in that lane. I know not all of us over here are probably in that space, but you need to think of how do you gain in this game. You need to just stay invested, make the right kind of investments by building the right skill sets. That's the most important thing. Just know how the space is evolving. Some of these things will change over the years. Technology might change, but the core concept will not change. Transformer models have come in. So transformers will remain the same for the next few years, but how transformers are going to get used to build models and how those models will get hosted, that will all change. Hardware will become cheaper. Transformer architectures will still remain the same, but hardware will become cheaper. Cloud providers will make it easier for people to access these models. Fine tuning these models will become much faster. All of that developer community, all of that ecosystem around this piece of tech will change very, very rapidly. So long story short, my point is this is the current value chain. Here's how different players are sort of getting themselves invested in this. I can share more material on how some of the others have made more money. Where the data center lies. Data center is an underground facility in a lot of countries, where it's like a massive warehouse underground, temperature controlled, yeah, like crazy places, but yeah, in multiple areas. Now let's talk a little bit about some of the more technical aspects of this. I think we've spoken about a lot of these business sort of concepts, but let's go one level lower. Let's get into the technical detail. So we said generative AI can do all of these things, right? So or Gen AI models, can do any kind of, let's be more specific here, right? So it can do text generation, code generation, image or image generation. And here I'm also going to say question answering, video generation, and so on and so forth, right? So these are some of the very, very popular applications of generative AI. And we said generative AI or the Gen AI models, the foundation of the generative AI models is the transformer architectures. So let's start with some very simplistic applications, right? So I'll show you how you can use or how you can do some of these tasks, right? Very simple examples to start with. And then what I'm going to do is then I'm going to go towards the technical, we'll go slowly into the more conceptual technical detail of the transformer architecture itself. Okay. So what I'm going to talk about is when we talk about Gen AI, I said these are some of the applications. So let's actually see how you could do it. Let's cut to the chase, right? Without actually spending too much time on the technical detail. Let's get to some of these examples. Let me show you some examples here. So I'm going to set you up for a couple of pieces here. I'm going to introduce you all to. I'm going to be using for this example. I'm going to be using the OpenAI models, right? So the OpenAI models is the Gen AI models is what I'm going to be using. Specifically, any of the GPT family of models is what I'll be using. As I said, there are many, 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 many different models that are available out there. OpenAI's GPT-4 or GPT-4 are by and large the most popular models that are out there today, one of the most effective models that are out there as well. So I'm going to be using one of these models for the moment, number one. Number two, how do you use these models? There are different ways of accessing these models. What are the ways of accessing these models? As a vanilla user, right, meaning like an end consumer, right? If you are, let's say, bearing the hat of a user, then you can access these models through the ChatGPT interface. So the ChatGPT interface is essentially like a chat box, right, where you can ask any question you want and it will generate a response back. But you are wearing, let's say, the hat of a developer, right, where you want to build applications, AI applications, right? So you're not just trying to just chat with an AI, but you would want to also, use this to maybe automate some things behind the scenes. You want to embed some level of AI capabilities into your existing application, existing code, or whatever. Then what you will get access to is the OpenAI APIs. So you have an API layer. OpenAI has hosted this model. If you go back here, so the model that has been built by OpenAI has been hosted on Azure. The model is available on Azure for people to use. So I will just go to the OpenAI website and I will create an instance of this. I will share that with you as well. For this, if you want to try out some things, you can try it out, but just be a little judicious. I'm going to be sharing my key with all of you. So be a little judicious, my request. Let me show it to you right quickly how you could do it. Go back the OpenAI API. Let's start with the OpenAI interface itself. OpenAI. So you will have to, of course, go to platform.openai.com. So this is the OpenAI platform. I'm just going to quickly log in. So I have the platform.openai.com over here. Let me go to playground. Let's go to the dashboard. In here, if you see, I have something called as API keys, right? I can quickly create a new key. I might already have a project. Yeah. So I have an API key here. I can also look at my usage for the keys that I currently have. So far, the total usage is 0.26, right? This is the total amount of usage that this thing has gone through so far. And let me just go back here. I can actually quickly create a key. I'm going to delete the older one. I'm going to revoke this. Create a new key. Let's create a Intellipaat GenAI test. Perfect. So this is the key that I now have access to. So I have this interface. Let me just ensure I'm not perfect. Okay, cool. So now I have my key. I got the key from here. I have stored my key in a .env file. I've created a file called .env, and I've stored this particular key in this particular file over here called .env. Now, what am I going to do? So how do I access the model? So the models are available here. In the OpenAI website, the models are accessible. I have the key to access the model as well. But how do I access these models? The beautiful part of this is if you go here, if you go into API reference, and if you see how you can access these models, the interesting thing, to install the official Python binding, run the following command. So you need to install this library called pip install OpenAI. So OpenAI has also created a Python library for all of us to access. They also have a Node library as well. If you want, if you're a Node.js, if you use Node.js, you could also install it through Node.js. But we use Python. So all that you need to do is just have to install the OpenAI library. So let's actually go back here. Exclamation pip install OpenAI, and that should immediately install the OpenAI library for me. So why is the OpenAI library important? The OpenAI library is important because the OpenAI library will give me some functions that I can interact with the model that is hosted on OpenAI's platform. But who will give me the keys, right? Can anyone access the model? Well, anybody can access the model, but you need the key to access that model, and the key is what I have given you here. See, remember, OpenAI models are not free to use. OpenAI models are closed source, which means they will charge you for accessing these models. It's not for free. It is expensive, meaning rather they charge you, but it's not very expensive. It is cheap. I wouldn't use the word cheap, but they are reasonable in terms of their cost. For the purposes of this particular session, I can give you the code, and I can give you the key. You can try it out. So the cost is here. You can actually look at the costing of it somewhere available. That should be available here. Let me actually show it to you. Models. Oh, so this is the API interface for your docs. Models. So yeah, here is all. There's the pricing. Yeah. So here is the pricing of these models. So for example, if you take any of the models and then you say, this is the images, of course. If you take any of these models, GPT-4o, $5 per 1 million tokens, right? So if you have 1 million words or tokens, the cost is 5 million. If you take, for example, an older model, if you take the GPT-4o mini model, the cost is half what it is. Like it's 0.15. The GPT-4o is a slightly smaller model, most cost-efficient small model that is smarter and cheaper than GPT 3.5. So 4o mini is actually pretty cheap, fairly cheap for us to use for sure. So when I actually show you the examples, I'm actually going to, this is like 0.15 per 1 million tokens. What is a token? You all have must have discussed about tokenization when you might have discussed text. Yeah, tokenization is what? Tokenization is the process of breaking a piece of text down into individual words, or not necessarily root words, but they're parts of the words. A good way to think of it is, what a good approximation is, consider around 75 words as 100 tokens, right? 75 actual English words would be 100 tokens. That's very much that's how you would possibly use it. I mean, like, so that's like a good. So if you were to kind of convert this into 1,000 tokens, what you're saying is approximately around 700 words. 700 words is like a Word document, right? A simple Word document. If you were to create a Word document using GPT-4o Mini, it would cost you so much. That's fairly cheap. 0.00015 tokens, which is very, very cheap. So we know that you can use the GPT-4o Mini models, but the question is, okay, how do you actually access it? So let's go to quick start. So here you go. You want to generate some text. What do? Import OpenAI. Well, this is Node, I would assume. Let's go Python. Yeah, that's it. So import OpenAI. You create a client, and then you just simply use this to fire a question. Client.chat.completions.create whatever model you want, and then you can simply fire a question. You will have to just tell it what you want it to. So let me show you exactly how you could do it. Let me just copy the 4o Mini model. Let me go back here. Perfect. So here you go. So I am just going to load the environment. So when I call the dot load environment, what will happen is this dot env file that you have, this variable OpenAI key will be loaded into my memory. Now all that I need to do is I just have to fire this question. So client.chat.completions. I'm creating an object here. This is VS Code, Visual Studio Code. You can do it in Jupyter Notebook as well. This is a Jupyter Notebook in Visual Studio. So you can do it in Colab, you can do it in Jupyter, you can do it in whatever you want. It's the Python interface. Doesn't matter, wherever you want, you can do it. So model equal to GPT-4o Mini. Okay, and I'm saying role. So remember, whenever you're accessing some of these models, right, you have to tell it, saying, hey, look, I'm giving it two roles here. There's always two people, or rather three people, or three entities over here that are at play. One is system. So when I say system, a system instruction is like I'm giving it a persona. I'm saying, hey, here's who you are. Whatever you do, you will have to do it with this persona. So what is the persona that I'm saying? You're a writer at a tech blog. Keep the responses short and engaging. Include very contemporary examples for the questions asked. Right? So I'm saying you're a writer at a tech blog. Keep the responses short and engaging. Include quirky comments in the response. Okay, and I'm saying include very contemporary examples in the question. Examples of for the okay, perfect, cool. The user is I am, let's say, asking it a question. So the user is me. I am the user, or rather, this client is the user. So for example, I am asking it a question. I'm saying, hey, what are the differences between AI and Gen AI? That's the question that I'm asking. And this particular client right now is bearing this persona. The persona is you are a writer at a tech blog. You have to write it with a certain fashion. So whenever I ask this question, it'll bear this particular persona while it's responding back. So take a look at this. What went wrong? Incorrect API key provided. Yes. Perfect. There you go. So that's the response that it came up with when I asked it to do it. So what did it do? Let me just go step by step again. I made a small mistake, so apologies for that. So of course I have my user key here, and then I have loaded the environment. as you can see. And then now here I'm trying to, of course, access the underlying GPT-4o mini model. And then I'm saying role user, system. Always remember there are 2 to 3 roles. The third role is that of an AI, but for the moment, let's forget that. The system role is to provide some kind of a persona for the OpenAI model. So the model is bearing this persona. It is saying, look, and I'm telling it, you are a writer at a tech blog. Keep the responses short and engaging, include quirky comments in the response, and blah, blah, blah. And then what I'm also saying is now I'm asking the question as a user. So let me actually reorganize this a little so that it looks logical, because it might seem like I'm asking the question and then. So here you go. So that's the role, the system role, and then the role, as a user, I'm asking this particular question. And then I'm asking it to generate the response. And the response, as you can see, is here. Absolutely. Let's dive into the exciting world of AI and GenAI. Here is what it's saying. AI, artificial intelligence, is the broad umbrella under which all kinds of smart technology fall. Think of it as a wizard that can do many tricks. Everything from recognizing your face on Instagram to analyzing stock market trends. Basically, it's like a super intelligent friend who can ace trivia night but might struggle with creative writing, right? No shade. Gen AI, on the other hand, is cool cousin of the AI family. So why is it kind of coming up with stuff like this? Saying is a cool cousin of the AI family who's not just smart but artistic too. It's designed to create new content like generating images, music, blah blah blah. Picture Chat GPT and Dolly as your artsy friends who at a party would doodle the wildest designs and web poetic sonnets while sharing memes. So it's actually able to write something like this specifically because I've asked it to include quirky comments and I've asked it to include contemporary examples. Exactly. This response is completely generated by Gen AI. Now, if you look at the examples, if an AI can analyze, recommend your next Netflix binge, thanks algorithms, Gen AI can actually imagine the whole new movie script and invent an entirely new character to spice things up. Why settle for another rom-com when Gen AI can throw in time traveling cat as a protagonist? So you see and it actually added these memes as well. It added a cat. It added a rock, sort of a rocket meme over here, kind of just to say a time traveling cat protagonist. Um, in short, while AI is your reliable assistant, Gen AI is an imaginative storyteller. Both have their perks, but definitely one has more flair. Um, keep an eye for both of these techno wizards who know that they'll conjure up what they'll conjure up next. So again, a super cool way of explaining what AI Gen AI is. All of it just because I've given it this kind of a persona. Now let's change this up a little. Huh? Let's say you're a writer at now I'm going to say you're a writer at Economic Times responses. Your responses formal and professional, include contemporary. I'll just put that, right? Now I ask it to do this. Let's see what it comes up with. I would expect something super boring. But there you go. Artificial intelligence refers to the broader field of computer science focused on creating systems that can perform tasks typically requiring human intelligence, such as reasoning, learning, and problem solving. Gen AI, on the other hand, is a subset of AI specifically designed to generate new content or data, such as text, blah, 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 based on your input and whatever. And then let's say, in summary, all Gen AI is AI, but not all AI is Gen AI. Yeah, I mean, that's the job. The thing is, this doesn't have a persona. As it said, it's got a lot of flair because it actually is created by AI with a specific, it has its own persona. It's kind of spicing it up a little. It's talking to, let's say, a teenage, a teenage individual. As you can imagine, it kind of resonates with that particular person. So you can kind of give it these personas, and that is what you mean by system, messaging over here. Now let's go one step further. What else can it do, right? If it has generated content, what else do you do using ChatGPT? What else do you do using ChatGPT? You of course ask it to write code. Of course, sure. Well, let's look at code as well. Let's come to code in a minute. I actually asked it to write a poem here. I'm saying, write me a small poem or rhyme about Gen AI, and then the system prompt is you're a school teacher for a fifth grade student. And then I asked it to write a poem. Let's go. Here's the poem. In the world of tech so bright and grand, generative AI leads a helping hand. It crafts new stories, draws with flair, creates new worlds from pixels and air. It learns from data young and old. A mind of circuits truly bold. Like kick-ass. I mean, this is very good. I think it's also kind of leaving in a little bit of thing here, right? So dream with tech, but don't forget the world needs your passion yet. Generative AI is here to stay, but it's you who leads the way. I think this is amazing. It's also kind of leaving that thing in, right? It's also telling you not to fear. Now, what I could also get it to do, and this is the part that I was talking about with the others, is I can also get it to write code for me. Of course, you could do the same using ChatGPT as an interface as well. But again, here is where I want you to think of an interface within your organization where you just build. And this is, by the way, one of the products that I'm building within my company, right? Where for developers, for business analysts, my business analysts, they spend a lot of time trying to analyze structured data. So how do I then provide an interface for all of my analysts in my company where they can simply say, give me, summarize the sales in so and so particular market, or summarize the sentiment of so and so particular market, and so on and so forth. Then that's what I'm asking it to do here. So write a SQL query. So how, if I say summarize the sales, remember that Gen AI is a language model, or these are large language models. They understand language. They will not understand numbers just by themselves. So what you need to do is you need to somehow get them to understand language or get them to understand these numbers. But one way to do it is you say, okay, keep the data where it is. What OpenAI or GenAI models are very good at is generating code. So I say, you know what, you generate the code and then you use that code to query against the database, extract the response and summarize it. So that's what I'm asking you to do. So one atomic action in that whole exercise is to write a SQL query. I'm saying you're a data analyst in a technology company, you're at high quality bug-free code, and your expertise is in Python and SQL. And then I say, ensure that you only return the SQL query or a Python code and nothing else. The response can be as a string or a JSON. So this is one of the many activities over here, right? Imagine there are multiple other such activities that I can create multiple such agents that could do multiple such actions. So when I ask a question, hey, summarize the sales for me, what I'm asking it to basically do, one of the actions that I'm asking it to do is saying, write a SQL query to analyze sales of each of the stores in Europe. You have access to sales database and customer demographics. So when I execute this, look what it does. It goes ahead and actually creates the SQL query for me over here. Then I can use the SQL query to go ahead and query it against the actual database, get the response, then pass that response back again to ChatGPT, and I say, you know what, go ahead and summarize this information from me. And then it summarizes it. How does it know what table it contains? So then what I can do is I can provide that information also over here. Currently, I just mentioned you have access to sales database and customer demographics. But what you could possibly do is you could also pass the table descriptions, column descriptions, all of that into this, and you can generate a response. So you could actually pass that as additional context over here, and you can get it to generate the response. Yeah, it can be different in each system, but there is always a way for you to extract it, right? So you can always, in a given DB, you will know all the tables, you will know all the columns, the table description, column descriptions will all be available for you. So you should be able to simply query against it. If it's not there, you will have to fix that. But here's another piece of thing that you could also do with the OpenAI, which is this OpenAI model. I'm saying clients.images.generate. Now I'm actually generating an image here. A coder underwater sipping a coffee, and I'm asking it to generate this image for me. And I'm saying I want a 1024 by 1024 HD quality image. And it's going to return a URL for me. And once I click on that particular URL, I should be able to access that particular image as well. Let me just click the URL. There you go. If you see blob.core.windows.net, which is essentially like a Azure capability. So there you go. Let's return the coder underwater sipping a coffee. There's a coder underwater sipping a coffee. What I could do is I can do this. This as well. Create a fun ad for my cola beverage brand. It's a party environment in the background. I can say it's a party environment in the background. Focus on condensed droplets on the can, and I can say I don't know. The can is blue in color, or rather, let's go is teal in color, and a portion of the can is also transparent with blue with pink liquid inside. I don't know, man. I'm just coming up with something. Let's see. I'm being creative here. Let's see if this is going to be equally creative or not. GenAI is the concept. OpenAI is the company that's behind it, which is true. And GPT is the model that is enabling it. Almost there, but yeah, it kind of added the teal and the pink, but it didn't kind of make it a transparent bottle. But it did the other stuff, as you can see. It did the other stuff. But I can ask it to create a realistic image, right? So I can ask it to create the image as realistic as possible. So it will hopefully create a realistic image, not that kind of a looks like a very cartoony kind of image. Let's see if it creates any different. Kinda. Again, I'm not very happy with this, but it does have the droplets that it is focusing on. I could actually provide um, ah, I can try to give it copy copy image link. Let's see if it takes us to that image. Very good. Let's see if it creates something like this. Let's ask it to create it something like this. I'm just gonna remove all of this. Can we ask for regenerate if you don't? Yeah, just re-execute it, regenerate. That's it. Can it generate 3D images? Yes, you can get it to generate 3D images. Use glass bottle in the prompt. Yeah, I mean, let's see if it. Yeah, it did bring the Coca-Cola thing, but of course it doesn't use the actual branding itself, as you can imagine. But it did bring the Coca-Cola kind of bottle design, as you can see here. It has taken some inspiration from this. But the thing is, it will not use, of course, the absolute branding of Coca-Cola straight away. You will have to force it to do it. But cool, awesome. So guys, I hope you get the idea of this, right? So this is, let me just see, accessing the Sora model. I'm not sure if the Sora models are available for public consumption. But let's go here. Where are the models? API reference. There's audio. Yeah, the video models are not available, from what I know. You need to access it through the interface, if I'm not wrong, but let me check. By the way, you could do this as well, right? Create some image variation. So you can pass an original image and you can ask it to create variations of it. You can pass any of the existing image and you can create variations of it as well. It's kind of kick-ass because you could essentially ask it to create multiple types of the same image in some sense. It's fun though, right? And then, yeah, the Sora models are not available here. Access Sora through API. There is currently no way to access Sora from a website or an API. So there's no way to do that. Sora is not available. The video is not available. You can access it through the front end if you want to. You can get ChatGPT Plus, and then you can do it from the front end if you wish to do that. Okay, cool. Let's actually try this last one, which is the variation. I'm keen on understanding how that works. OpenAI, and let's try one of the existing. By the way, just to let you know, just in case you're interested. So this, my friends, Bex is one of the brands that that my company is built. Okay. So what we were able to do is we kind of launched this product called Bex Autonomous. And this was built on top using Midjourney. So this product called Bex Autonomous, by the way, it's in the market right now. It has actually launched in the, people, it is actually now available for people to actually consume. The product itself is available for people to kind of consume or whatever. The point is, from the recipe to ads to bottling to everything of this product has been made using GenAI. Completely. That's the product. It's Bex Autonomous. Everything's been made by GenAI. By the way, it's sold out right now. It's not available, but they've only launched like a few versions of it. This is something that was created by the company that I work for. Let's go for this images. Let me find one of the, yeah, let's look at this. Image link. Let's see how this goes. It needs access from the local machine. Yeah. So that, that's not. So I can ask it to actually create variations of this. Go back here. And like, what happened? It has to be a PNG. Okay, it's mandatory for it to be a PNG. Okay. Okay. Let's see. Part PNG. Let's see what it does now. I can, of course, provide it more prompts. Yeah, so I see some question points here. Advertising agencies should be clearing their lives now. You're a responder, right? Like a ton of agencies can hire fresh face modeling. Yeah. So I'll tell you how advertising companies are. Well, yeah, kind of boring though, but it kind of created a version of it. Uh, yeah, not very pleasing, so to say. But I can of course write a prompt, and I can ask it to specifically operate a certain way, of course, over here. I can guide it in a specific direction, of course. I can add a certain prompt, and I can get it to do a few things, stuff like that. But anyways, point is, I see a point there about how agencies are using this. Guys, this is where agencies are, of course, not going to be using this through coding interfaces. But what's happening with marketing agencies, your Adobe Photoshop, or let's say Figma and stuff like that. And what's happening right now is these capabilities are now coming as a part of that, right? So these integrations are coming as a part of Adobe. So Adobe, right, Adobe Photoshop, if you take a premium version, Adobe Photoshop has launched something called as Adobe Firefly. And Adobe Firefly is exactly the same thing as what you're currently seeing on the screen. So Adobe Firefly is essentially the same thing. It's generative AI for creatives. So you could kind of do exactly what we just did. So you could do generative fill, image generator, blah blah blah. You can do like a bunch of different things online with stuff like this. Super cool, very fast. So as you can see, like seems like a Pokemon only this one. I don't know what that is. So yeah. So point is, they're already using this extensively in their work. Code. I'm not sure if you all have heard of GitHub Copilot. It is already a part of, these tools have already come in. GitHub Copilot is already a capability that kind of provides you an interface where you could automatically start writing code. With writing, I don't know if you've heard of Microsoft Copilot. Microsoft Copilot is a capability that gets integrated straight into your Word documents, your PowerPoints. So you can actually ask it to write content for you, write a document for you, write an email for you for that matter, summarize emails for you, important. Something that I do use quite extensively. I actually use Microsoft Copilot very, very extensively for rephrasing emails, right? So yesterday I was asked to write a business case to explain why I should continue hiring in my team. I just wrote two lines on chat on Microsoft Copilot, and I said like, hey, go ahead and write this email for me. It actually ended up writing it in 2 minutes, and I'm done. Otherwise, I would have had to spend like half an hour writing that complete business case. It would have been an absolute waste of my time. So stuff like this, super easy to do with capabilities like GenAI. I don't write one email without rephrasing using Microsoft Copilot. I don't write one memo or a document without using Microsoft Copilot or for that matter, even ChatGPT, so to say. So these are how it can impact you on a regular basis with your work. But then what you can do, my friends, is you can take this power of these capabilities, not just use it for personal productivity, but actually take it one notch up. Right? You can combine these capabilities multiple ways and then create agents that can automate workflows, that you can combine these capabilities together to, let's say, scrape from internet, extract from SQL database, read from a PDF document, combine all of it, summarize and write a report out or send out email. All of this in a single shot, which would have been super complex earlier. You would not have been able to do something like this. And all of this without you having to tell it what to do. You can just provide it those capabilities. You can simply write a question and it would automatically do that for you one after the other. Be super capable when things like these start happening. I'm going to touch upon things specifically around how the transformers models work, or some of these generative AI models actually work, right? So if you remember, we spoke about how generative AI models are based on these core concept called as the transformer architecture. So I'm going to touch upon the transformer architecture a little. This was not discussed with all of you. So I'm happy to redo it. So we can touch upon transformer architectures a little, and that would already should set us up well. Now, it's going to be a bit of an intense piece of next few minutes, or next maybe half an hour, 45 minutes, everyone, wherein we're going to delve into fair amount of detail with regards to the transformer architectures. One thing I want you all to know is that this is a bit of a complex setup. It is a complex architecture, but we will discuss it anyways, nevertheless. And then from there, once we at least understand, 1,000 feet high, if you're able to understand how this works, then we can get into the actual detail itself. Then we can at least move on, and then we can talk about some of the other concepts about this. Okay. So for the first part of our today's session, we're going to focus as much as possible on the architecture of the high-level architecture of these models of the transformer architecture. With that context, let me go straight in. Sorry. Again, if there's one thing that you must have, that we all should have learned by now, is that look, this space is evolving. Fundamentally, I'm assuming you all have used ChatGPT. If you can do things like ChatGPT, if you can do what ChatGPT is doing through the interface, if you know what it could do, potentially you all can build those kind of capabilities behind the scenes as well, right? So using the APIs, you could also do all of that. But if you want to build a PPT, if you want to build marketing content, certain things are easy, certain things are not very easy. Certain things are slightly more simpler to do. Certain things will require a lot more software engineering because you might have to interact with PowerPoint. You would need connectivity with Outlook. You might need connectivity with O365 Suite. You might need connectivity with a bunch of other things, and stuff like that. So my point is, so all of that is possible. I think what we will be focused on to start with is to understand, and I'll tell you something as well, right? So the pieces of example that you're talking about, everyone, the pieces of examples that you are talking about, like using it for PowerPoint, see, these things will get automated, right? Somebody or the other will come and they will try and make it, like Microsoft will just do it. Today they might charge it, tomorrow they might make it free. So point is that it'll become super obvious. I'll give you one example, right? Biometrics, right? So let's say face recognition, face ID on your mobile phones, or let's say your fingerprint scanners. That's all AI. That's all computer vision. But nobody calls them as AI today, right? Because it's just there. It's so commoditized that everybody has access to it, and these companies are just using that piece of technology and they're just embedding that into the products. So the PowerPoint thing is exactly going to become that. What we should sort of be looking at is not the whole, how can I use it for PowerPoint? How can I use it for Word documents? Instead of looking at that, you should look at, okay, how can I use this piece for, let's say, maybe automating workflows? How can I automate, how can I use generative AI or generative AI models to, let's say, respond back to queries, customer service your question? How can I use this generative AI models to, let's say, automatically, how can I build agents that can automate workflows? So I think you should sort of look slightly more broader, not just with those smaller quick wins. But again, we'll get there. I think we'll slowly, once you start doing a couple of examples, you'll also get there. Super easy to do all of that. I'll just show you what I'm going to show you is I'm going to talk about a couple of tooling, and then some of it will become super easy for you to do. For some, there are tools that are already available, just letting you know. So let's get into a little bit of detail on the transformer architecture itself, right? As I said, the most fundamental part of, let's say, any of these GPT models, if you take for example the word GPT, right? So when we talk about the word GPT, GPT stands for, GPT is just one of the many models, generative pre-trained transformer. That is what GPT stands for. That is where the G, P, and the T sort of come from, right? Generative pre-trained transformer. That is what we mean by GPT, right? Now, these GPT models are the sort of models are, again, there are many kinds of models, but I'm taking GPT as one example. So when you talk about GPT-3, GPT-4, Chat GPT, they're all of the family of, they're all from the family of transformer models, right? So what are these transformer models? What are transformer architectures, right? Uh, Now, to be very specific, right? So the transformer architectures, just a second. So the transformer models have sort of been introduced by this paper called as Attention is All You Need. Now, this was the paper that was first published in 2000, I would say, approximately in 2017 is when it was first published. And since 2017, this paper sort of went through a couple of revisions, of course. But this paper is the paper that kind of made that sort of made so much, that kind of transformed. It was like a game changer. This particular paper, right? What is it about this particular paper? So if you look at the abstract on this paper, right, I'm not going to go into too much detail. I'll start with here, right? So the dominant sequence transduction models are based on complex recurrent or convolutional neural networks that include an encoder and a decoder. Okay. Now, I'm not sure where did you all discuss sequence to sequence models, or if you have learned LSTMs, you would have also discussed the encoder decoder models. If not, that's okay. I'll just briefly touch upon it. The point is that the state of the art, let's say, translation models, you take translation, transliteration, or any of these state of the art models. Now, this was in 2017 that I'm talking about. They involve either a very complex recurrent neural network or an LSTM, so to say. The best performing models also connect the encoder and decoder through an attention mechanism. So there was a mechanism called as an attention mechanism, which was introduced well before 2017. Now, there is a new simple network architecture called the transformer based solely on attention mechanisms, dispensing with recurrence and cause, basically getting rid of the whole idea of recurrence and convolutions entirely. So, again, if you remember yesterday, I spoke about the fact that when you learn about recurrent neural networks, the reason recurrent neural networks are firstly, the way recurrent neural networks work is you recursively pass, let's say, one word after the other, and then you try to predict the next word. In this process, you are sort of trying to learn the probability of the next word basis the current word, and then there is one weight matrix that you have which you're trying to recursively learn over time, right? So you're saying your sentence is a sequence of numbers or a sequence of words, and one way to capture the dependency of one word to another word is by going from right to left, and thereby capturing, trying to use the first word to try and predict the next one, and so on and so forth. So that's how the whole recurrent neural network sort of works. But as I said, it's super slow. So experiments and what they are saying is we've gotten rid of these network architectures that have to do with recurrence or even convolutions for that matter. We've introduced a new model called as transformer architecture. And this transformer architecture is solely based on the concept of attention. So we have to somewhere learn what attention is to start with. We have to understand what is attention. So We'll discuss about attention in a few minutes. And this attention mechanism gives us a very, very good understanding of, firstly, we'll learn about the attention mechanism, then we will learn about the transformer architecture itself. Okay. So what this paper is saying is, look, so far, all of the state-of-the-art models have been built using any of the um, have been built sort of using any of the recurrent neural networks or convolutional neural networks. We're introducing the concept of attention. Along with the concept of attention, we're also proposing this idea of transformer architectures. These transformer architectures have nothing to do with, they're basically chucking the whole idea of recurrent neural networks or convolutional neural networks. They said these are great, but these are useless. Let's simply get rid of them. We will talk about something completely new, and these are now going to collectively help us build this architecture called as transformer architecture. Okay. And this transformer architecture, our model achieves 28.4 blue with a WMT. Yeah, so these are some scores. Blue score is very, very good score for content creation, content generation. And they say that this particular model has sort of far outperformed some of the other models. They will also talk about, if you look at this, and I'll specifically go into the more, I'm not going to walk you through the paper, but I just want to touch upon some of these concepts here. Recurrent neural networks, LSTMs, and gated recurrent neural networks in particular have been firmly established as the state-of-the-art approaches in sequence modeling and transduction problems such as language modeling and machine translation. What do you mean by language models? Language models are models that are always trying to predict the next word. You have a sentence, you pass the first word into the model, it tries to predict the next word. Those models are basically referred to as language models. So again, the sentence says it for itself. NLP, exactly. This is all natural language processing only, Dhruv. All of this is NLP. We're talking about text. We're talking about natural language processing. We're talking about text itself, right? Numerous efforts have since continued to push the boundaries of recurrent language models and encoder-decoder architectures. Again, a lot of stuff has gone into this. In 2017, almost until very recently also, right? Lot of the machine translation, when you talk about machine translation, we're talking about language translation models that you see. They've all been predominantly based on the recurrent neural networks transform, and also more specifically these encoder decoder models, sequence to sequence models. But unfortunately, recurrent models typically factor computation along the symbol positions of the input and output sequences. So there is basically aligning the positions to steps in computation time. They generate a sequence of hidden states. Yeah, again, we don't need to get into too much detail, but the point is this inherently sequential nature precludes parallelization. So it kind of it doesn't help us with parallelization, which becomes critical at longer sequence length. So when you have large sentences, it becomes very, very complex as memory constraints limit batching across examples. So it's like you cannot have large sentences to deal with. LSTMs try to handle for it, but again, computationally, they become very, very challenging. Recent work has achieved significant improvements in computational efficiencies through factorization tricks and conditional computation. There are like some specific tricks that have been put in place, but still the fundamental problem still remains, right? It's improved, but it's still not the best solution. Attention mechanisms have become an integral part of compelling sequence modeling and transduction models in various tasks, allowing modeling of dependencies without regard of their distance in the input or output sequence. Again, long story short, attention mechanisms were brought in. Attention mechanism was very good. We don't know what attention mechanism is. We'll learn about it. But again, this is the premise. Attention mechanism by this paper was already introduced. But they were saying that these attention mechanisms were always used in collaboration with recurrent networks, the RNNs. So we have to understand what attention mechanism is. Somewhere we need to talk about it. We'll talk about it in a few minutes. But then they're saying Even though you bring in attention, that did not solve the problem, because they're still working with RNNs, and RNNs fundamentally have the problem of time. You cannot parallelize it beyond a certain point. In this work, we propose the transformer, a model architecture, eschewing recurrence, basically getting rid of recurrence and instead relying entirely on an attention mechanism to draw global dependencies between input and output. So somehow they've gotten rid of the idea of learning the language sequentially, and just treating it as some way to extract all of this information together, right? You're not learning it anymore sequentially. There's like one very interesting way now to capture all of this, or in parallel, and getting rid of the whole idea of sequence. Transformer allows for significantly more parallelization, and can reach new state of the art in translation quality after being trained for as little as 12 hours on 8 P100 GPUs. So just training it for 8 hours on and just 8 GPUs was able to outperform some of the other models that were state of the art at that point. And now your GPT models, my friends, are really, really big, right? So this is far bigger than what this is. So that's the background. Okay, so that's the background, guys. I mean, I'm not going to go into the paper itself, but do you understand some of the challenges here? Like broadly, of course, there's some things that we probably don't fully understand, but that's okay. But broadly, do you understand the setup here? Like why this architecture was brought in to start with, and what is the biggest advantage of a transformer architecture as opposed to, let's say, any of the existing state-of-the-art architecture? Now let's delve into a little more detail. So there are things that have been spoken about over here in these 4 paragraphs. Now, my friend, here is the thing, and I should not sound very preachy here, but without sounding too preachy, my ask with all of you is, see if you can spend some time in reading such papers. Try to. I would not say I am reading it myself. Probably I try to read it, but see, the moment you read such papers, it opens up a complete Pandora's box, because now you're like, okay, there's so many things that I've been talking about in a couple of lines that you probably have not even heard of. And remember, you've been learning and training on AI for the last 2-3 months, or maybe even more than that, some of you. So thing is, there are so many topics that have been discussed in these 3-4 paragraphs that you probably haven't even heard of so far. So again, or most of them you have, there's some that you haven't even heard of. A good um, a good way to keep your understanding in check. Just letting you know that these are some of the areas where you could possibly get lost a little. Anyways, it's important to read papers. That's all that I'm trying to let you know. Any website or yeah, so there are a lot of websites, my friends. One of the most popular website is this website called Papers with Code. It's sort of the latest and greatest as far as machine learning is concerned. You typically see on this. You have the papers, you have the the code. There's like long form articles as well. You can read about it and stuff like that. So a lot of interesting research that happens in this particular. It's just an aggregation. It's just an aggregation of a lot of these areas. All right, let's go back. So now let's talk about the concepts that have been just briefly touched upon here. So let's talk about, firstly, this idea of, let's look at how the transformer architecture looks like. Yeah, so this is, my friends, a transformer model architecture. If you see, there are 2 parts to the transformer architecture. Right? On one side, everything that you see on the left is referred to as an encoder, and everything that you see on the right is referred to as a decoder. So there are some, as I said, there are a couple of things that has been spoken about here that you may not have heard of. So we'll try to go one by one here, right? We'll try to understand each of this one by one. There are things like when we looked at that paper, right? there were things, for example, like so when we read that paper, there were these three relevant topics that were discussed, right? So they said when you talk about sequence to sequence models, encoder decoder architectures have sort of become the most popular ones. And within this, the encoder decoder models, there was something very interesting with that they have been primarily based on RNNs or LSTMs or even GRUs for that matter. They're typically based on these models. Let's understand firstly what is an encoder decoder model. I'm going to briefly touch upon the encoder decoder model and how it fundamentally works, and then we can get into the detail a little. So, what is an encoder decoder architecture? Historically, when you talk about tasks like, for example, let's take the tasks like, let's say, uh, machine translation task. What do you mean by machine translation? Let's say you're trying to translate from English to Spanish or English to Hindi, whatever that language is, right? So if you take a sentence like this from English to Hindi, um, the machine translation is essentially a neural network or machine learning algorithm that tries to convert any input that is in English to Hindi. So how do you train a model like this? So the most popular architecture that was used and that is still used, that was previously used as well, that is still used, is this architecture called an encoder decoder architecture. How does the encoder decoder architecture work? So the encoder decoder architecture has two parts to it. The first part, sorry, so here you go. Let me explain how an encoder decoder architecture works, or encoder decoder model fundamentally works. So this is a very good example of an encoder decoder model. Let me just try to find a simple example. So let's take, for example, so let's say the sentence that you would want to translate is, the sentence here is, how are you doing? Let's say there's a sentence like this. And now in your encoder, what you're typically going to have is you're going to have the first part. All that you're simply going to have is you're going to have 4 RNN blocks, right? This is RNNs. Now, this can be RNN, this can be LSTM, this can be GRU, doesn't matter. 4 RNN blocks. The input into each of this is essentially one of the words. So the input can be how are you doing? Now remember, when I say this is the word, what I'm essentially meaning is not the word itself, but it's essentially the embedding of that particular word, right? It is the embedding of this particular word that is going to go as an input here. You pass this as an input here. And once you pass this as an input, what's going to happen is, of course, right? Once you pass this as an input, what's going to happen is the or rather these inputs will then combine themselves. Right? These inputs will then sort of combine themselves in some form or shape. By the way, there is a recurrence here. This is the same RNN. So there is, at time t equal to 0, t equal to 1, t equal to 2, t equal to 3. Essentially, you're essentially going sequentially here. There is that recurrence over here, or you're going sequentially from left to right. And then what you're trying to produce is, as an outcome from here, you're trying to produce a vector. You're essentially trying to produce a vector over here called a state vector or an embedding vector or an encoded vector, whatever the vector is. So this input that you have here, that is essentially converted into a vector V. Now this vector, you call it a state vector or you call it a embedded vector, whatever. Essentially, it's an embedding of the original input sentence that has sort of been created as an outcome from the RNN. Now this vector is now passed as an input into another RNN. So this part is the encoder. So the encoder over here has taken the original sentence and it has converted that into a input vector, right? It has combined the complete context over here and it has created one vector as an output. That vector is now passed as an input into another RNN. So this is RNN1, right? And this is passed into another RNN where this RNN's only job, right? This RNN's only job is to take this vector as one of the inputs along with this vector. What it also takes, it takes another input from here, right? So like for example, you sort of simply give a simple token called start. And what this tries to do is, given this particular vector and given this start token, it now tries to predict the next word or the word in Hindi that should come out. So this tries to predict the word up. And then after this, it goes further. Now it goes for the next time step. The same RNN now takes the word up as an input, or it takes actually both the words as the input. It takes this state vector. This state vector is of course going to be there, but along with this, it takes start and it also takes the word up, and then it tries to predict the next word, which is probably kaise. And then the same RNN again takes these three words as input, right? It takes all the three words as an input. So it says start and kaise, and then it predicts the next word, which is probably ho. And then it continues to do this until it predicts a token called end of sentence. It continues to do this until it predicts a token called end of sentence. The moment it predicts this as the token, it stops generating. It stops generating. So point is that this piece over here is essentially taking an encoder, right? Taking a piece of sentence as input, see word by word, it is taking one by one word and then converting this into an embedding. And then this embedded vector is now being passed as an input. Just to let you know, this embedded vector is passed as an input like this, actually. This is essentially passed across all of the, across all of the decoder part. Now, the objective of doing something like this, yeah, so every sentence, wherever we look at the sentences, right? What we typically do with these sentences is we always start of the sentence and end of the sentence. We typically add these additional tokens over here. We typically pass the SOS and EOD, end of the sentence as additional tokens on either side, just to indicate that this is the start and this is the end. So technically speaking, even here as well, the first word will be embedding of SOS. That should be the first RNN, and the last one over here would be embedding of EOS, end of sentence. So you sort of pass all of those as inputs, and then you're expecting the other words to be generated as an output. And then you're trying to predict continuously until it predicts SOS, EOS as the output. Embedded vector is the only input that is considered in the decoder. That is absolutely right, Ajay. The embedded vector is the only vector. The vector V is the only input vector that is being considered in the output, along with, of course, whatever you have predicted in the previous time step. The only two vectors that are being considered here are this vector, vector V, and whatever words that have been predicted. All of that is being considered as an input. Only these two are being considered as an input. Now, why are these? Now, remember, this has nothing to do with the transformer architecture. This is a very, very popular architecture for doing any kind of translation, for doing any sequence to sequence. Why is this useful? Why do I need to have something like this? I could simply have an RNN, like this. I could simply say, I could have a sentence like, how are you? And aap kaise ho? Right? I could simply do a word by word translation. Right? I could simply do a word by word translation. I could just have one RNN. I can pass how as the input and I can predict another word. Similarly, I can pass another word into the same RNN, predict another word, and so on and so forth. I could do word by word translation. Why do I need this kind of a setup? Well, the problem is, especially in languages like Hindi, whatever words you pass as an input, the translation is not always in the same order. Number one. Second thing, the output translation doesn't have to have the same number of words either. So you cannot simply make a word by word translation. You cannot just have one RNN predicting one word after the other. Right? Which is why, to be able to overcome that kind of a setup, we say, okay, let me take the complete input sentence, let me embed that complete sentence, and then convert that into one vectorized representation, one long vector. After that vector has been created, I pass that vector, and then I train another decoder, which then word by word tries to predict my outcome, my output. Right? This is the first word, this is the next word, this is the next word, and so on and so forth. Right? So that way, I am not forcing my model to always predict word by word, but rather I'm not forcing it to exactly predict the translated word from English to Hindi, but rather I'm saying, you know what, it doesn't matter how many words are there in the input, the output can have as many as words it can, and it can be in whichever order it can be. That way, the sequence to sequence models have become a lot more preferred choice of translation than your regular, RNN classification, simple classification based models. Now that you understand the encoder decoder setup, the encoder, broadly, what does it do? So I can simply summarize an encoder like this. The encoder decoder architecture can be very easily summarized this way. Encoder, decoder, an encoder would take the input, right? And this encoder would generate a vector V, and there is the decoder, which takes this vector as an input and then predicts the output. Right? This is a embedding. There are multiple names to this. People call it an encoder, encoded vector. Okay, let me not call it an embedding. I'll simply call it as an encoded vector rather. A context vector, yeah, whatever, doesn't matter. Yeah, whatever that term is. That is an encoder decoder architecture, everyone. Now, so you pass an input, you have an encoder. This encoder typically is an RNN model, was an RNN model. Then you have a decoder. A decoder is also another RNN model, which takes this vector as an input and generates the output. Now, once you have this setup, what was being spoken about is the fact that you have these models as some kind of an RNN model is very restrictive. Why? RNNs are time taking, RNNs will only operate sequentially, a lot of problems with RNNs. Hence, introducing transformer architectures, introducing something. So, two things. One is the problem with the RNN itself, right? RNNs are slow, cannot be parallelized. The solution to that is the transformer model, the transformer architecture. The second is this encoded representation is also at times not very rich, right? So this encoded representation vector is not rich enough, doesn't capture enough detail of the sentence. Hence, the solution to that is attention. There is a technique called attention, which we will discuss right now. Yeah, parallelized means you cannot pass all the words at the same time. You'll have to go one word after the other, right? Because that's how language works. You'll have to pass the first word, then the next word, then the next word, then the next word, and then create the embedded vector. Then after that, the prediction has to be sequential, of course. But even the encoding part of it has to happen sequentially. Pass the first word, then the next word, then the next word, and then the next word. So you have to go sequentially, which is why you cannot simply go all observations at the same time or all the words at the same time. You cannot do everything at the same time. That is what we mean by it cannot be parallelized. So the two challenges, one is RNNs are slow and cannot be parallelized. Hence the answer to that is transformer architecture. The encoded vectors are at times not rich enough, and hence the outcome or the change that was brought in is the attention architecture. So this, my friends, is the answer to this. Now we'll of course have to get into a lot of detail here, but broadly, to start with, whatever you are seeing here, forget about everything else. Stick with me for a couple of minutes. Right? Whatever you are seeing here, forget about everything that you're seeing here. This is input. This part that you're seeing here is encoded. This is your encoder, right? So if you were to just simply look at it, what we are saying is we're saying you have a block being passed into an encoder, and this encoder is generating a certain output. This encoder is generating a certain output or some kind of a vector. It is generating a vector over here. Now this part, my friends, don't read too much into what's there inside it for the moment. This one, whatever you are seeing here, is simply nothing but the vector that has been generated is being passed as an input. This is your decoder. This vector is being passed as an input. And then there is output embeddings, which is nothing but the words that you have predicted, like start of sequence and stuff like that. So the outputs, and then this is essentially going to predict the output over here. So this is also, what do you think? This transformer model is also an encoder decoder architecture. It is very similar to that of your, this kind of a model. Your transformer model is also an encoder decoder architecture. You take an input, you encode it into some kind of a numeric representation. You take that numeric vector, pass it into a decoder, and then one by one you generate outputs. So your decoder is also, or rather your transformer is also an encoder decoder architecture. The only difference is that the stuff inside this, it's not an RNN anymore. This is not an RNN anymore. This is something that is based on top of attention. RNNs are completely thrown out of the window. This detail that you see here, this is not an RNN anymore, or a recurrent neural network for that matter. It's based on something called as attention. Now, what is attention? We need to understand what attention is. That is what we will learn for the next few minutes. We'll understand what attention is. Why do we need a vector here? Okay, Deepak, here's the thing. I'll give you a simple example. Okay, I'll give you a very simple example. So imagine you are in, so you traveled, let's say, to China. And now for you, you don't understand Mandarin or Cantonese or any of the Chinese dialects. You don't understand the languages in China, let's say. Somebody is speaking to you in Chinese. You need to understand it. You understand Hindi very well. What do? You put a translator in between. What is this translator doing? This guy in between is taking Chinese as an input. In his head, this guy translator, taking Chinese as an input, converting that into some kind of a common language or common understanding of this Chinese language, converting that into some kind of a numeric representation. Numbers are universal, right? It has nothing to do with language. So you're taking this Chinese input, converting that into some kind of a, in his brain or her brain, the person is converting that into some kind of a commonly spoken language or commonly understood language. And then you're taking that commonly understood output or that language and then passing it and then converting that into English, right? So all that you need to do is you don't need to always build a Chinese to English translation. All that you need is, okay, can I have a model that converts this Chinese language into these numbers? And then can I have another model which take these numbers and then converts it into English? So that way I can put both of these together and I can always do translation very efficiently. So exactly, vector, this vector is simply nothing but numbers. So it's a numeric representation. That's the common grounds that you're bringing these two, distinct languages to, because models understand numbers very, very well. So I take Chinese, I convert it into numbers through some kind of an encoder, and then I take a decoder, I take these numbers and then convert that into English or whatever language I want. So that is the idea of the vector. So that is what this vector is doing. This common vector over here has multiple things embedded in it. It embeds the complete understanding of the inputs. The understanding of the input sentence is very, very nicely packaged in that vector. Okay, that's the idea of having that vector over there. Now, more technically speaking, this vector is of a, one of the other advantages having this vector is of a fixed size output. Your input can have how many ever words you want. Your output can have as many words as it wants. But what you're doing with this encoder over here is you're taking the input of how many ever words, and then you're always converting that into a fixed size vector. Right? And the fixed size vector can be, let's say, 1,000 dimensions vector. At all moments, this input is getting converted into a 1,000 dimension vector. So that way you will always know that you can always map any size input into 1,000 dimension vector. The understanding of all of that can be always converted into 1,000 dimension vector. Then the input into this model is always this 1,000 dimension vector. And then you're going to predict one word after the other from it. So that way, your decoder also has a very, very standardized input. And your encoder always has a standardized output in terms of size, at least. That's the other advantage of it. So I think so far, we all understand the fact that this encoded vectorized representation is exactly what we're sort of trying to accomplish, right? So all the models that you may have heard of so far, right? Any kind of large language models that you may have heard of so far, they all broadly follow the same concept, right? They all follow the same exact concept. This is broadly the structure of those, right? There's an input, there is an encoder, you're generating features or embeddings. Those embeddings are passed into the decoder is generating the outputs. Just one more point here, I mean, just for completion's sake, there is also outputs that are being passed as inputs here. What do I mean by that? Outputs from the previous time step are being passed as inputs here, but fundamentally it's the same. So nx is n times. There are multiple n encoder blocks, n decoder blocks. So that's kind of stacked one on top of the other. That's what you mean by n. What is below output with red font? Okay, so yeah, it's the same thing. Yeah. I mean, okay. So if you take, for example, a sentence, right? So let's take the input sentence. Start of the sentence. How are you? End of the sentence. You pass this as an input. You've created this into a feature, a vector. Now this vector is being passed into the decoder. Along with this, there's the first output that is going to be passed. This is the output, final output. Huh? What's the first word going to be? First token here going to be? What's the first token going to be? Start of the sentence, SOS. So SOS is going to be the first token. So I pass SOS over here along with this vector V. This vector V and SOS is going to go in. And what is it going to predict? This is going to predict in Hindi, right? So it's going to predict the first word as up. No, the first one is going to be up. Okay. Then, now I've come to the next time step. So what's going to be my input now? What do I pass here? So I'm going to pass these two as an input now. SOS and up and the vector V. SOS and up and the same vector V will be passed to the decoder, and I'm saying predict the next word. So I'll predict the next word. What's the next word that it's going to predict? Kaise. Right. So now I have my next word. So the third time step, I'm going to pass these three as the input along with the same vector V as the input. Right? Then it's probably going to predict the word ho. Again, my Hindi is not the best. So don't trust me on this, right? So you're going to predict the word ho. For the next time step, what do? You pass ho as the input. You will continue to do this until what? Until what time? You're hoping that it stops here, or maybe it might predict a question mark. So I probably will put a question mark here, and then I take the question mark here, and then I might simply put a question mark over here and pass it back, and this might probably predict end of sentence. So I'll keep predicting until that particular point. So I'll keep predicting continuously until I hit end of sequence. Now remember one thing, everyone. It's not always only going to predict one word. When a neural network predicts words, it'll always predict it with a probability distribution. It's never going to be one word. It'll predict words and probabilities. The last layer is going to be here a softmax. There's going to be a softmax here. So you're going to be predicting words with probabilities. So you're never only going to predict one word. It'll be that word plus its and along with its probability. So you always pick the one that has the highest probability over there. So it's not always just predicting one word. Does that make sense? And in this sentence, the end of sentence will probably have 0.95, but you'll also have the other words with lower probabilities over here. Your output generally is always going to be a probability distribution. At every time step, it might not always predict the same word. It will predict the word along with its probability. So you will have to pick the one that has the highest probability. The reason why I put aap over here is probably because aap would have been the word with the highest. That's why I put the word aap here. But if you have a bad model, it might get a very, very bad score over there. And thereby, this word would probably be incorrect. It might end up predicting it something incorrectly then in that case. Now let's go one step further. Let's talk about the attention architecture here itself, right? So the attention component here itself, which is what makes this model very, very good, right? So if you actually look at this detail here, if you now go into the details of this, you see something called as multi-head attention. Right? There are other feed-forward neural networks and everything is like pretty simple, straightforward stuff. But the thing that I want us to understand the most is this concept called multi-head attention. Now we need to understand what this multi-head attention really is. I think that's where all of the magic really lies. The concept of attention, we all have learned about word embeddings. What are the different algorithms you may have learned? You would have learned skipgram, SIBO, or you would have also learned word2vec. They're all basically algorithms. But the point is, when you have a sentence, right, W1, W2, W3, W4, W5, you have 5 words. What you're saying is, given a particular sentence, you can take a particular word, right? You can take a particular word, and then you can kind of try to predict that particular word given its neighbors. Right? Given the neighbors, you can predict, given the context, a window of 5 words, 10 words, whatever that word is, you can predict the word of choice over here. And we said in the process of predicting that particular word, you will end up building some understanding of that particular word in the presence of the other words, and that hidden vector becomes your word embedding. So you are essentially saying, look, if I were to represent all of these words in very large dimensions, then words with the same kind of theme will always come together. A good example is, for example, if you take the word milligram, kilogram, and stuff like that, they'll all probably come together because they're all measures. In one dimension, they might all be together. In another dimension, they might be slightly far away from each other because kilogram and milligram are also measures. Milligram is small, kilogram is large. So they also might be far away from each other in a slightly different direction. In this direction, they might be close. In this direction, they might be far away from each other. So again, the point is you're trying to represent each of these different words in a very, very large dimension. That is what the concept of an embedding really is. What attention tries to do his attention tries to take this concept of word embeddings a notch further, right? Like what? What does it exactly do? So if you take any piece of text, right? Let's take a Wikipedia document, right? Let's take the Wikipedia article of this. Let's take any of this article. Forget about the images and everything for the moment. But let's just take this raw text that you see here. The September 11 attacks, commonly known as 9/11, were four coordinated Islamist terrorist suicide attacks carried out by Al Qaeda. Blah blah blah. So you see the complete piece of text here. Ringleader Mohammed Atta and American Airlines Flight 11 into the North Tower of the World Trade Center, complex in Lower Manhattan at 8:46. Blah blah blah. So you have all the piece of information that you see here. The thing is, when you look at, let's say, the concept of the word, in this case, let's say September 11, when somebody says the word September 11, you know that this reference to the word September 11 is the same as 9/11. The word September 11 is typically being spoken about in the context of the word 9/11 as well. Now, this reference to the word September 11 as 9/11 was mentioned at the beginning of the sentence, somewhere else in the sentence as well, in the article as well. And when you look at this sentence itself, right, the September 11 attacks killed 2,977 people, making it the deadliest terrorist attack in history. So if you take each of these words, let's actually copy this sentence. If you take, for example, this particular sentence here, you go one word by one, word by word over here. The September 11 attacks killed 2,977 people, making it the deadliest terrorist attack in history. So if you just take the sentence like this, the interesting part of a sentence like this is that if you take the word people, this word people has some kind of, is qualified by this number 2,977. This word people in the context of this sentence is also qualified by the word killed, right? And the word killed is sort of qualified by the word attack. So the word people might have a certain meaning in regular English. But in this particular sentence, the word people is qualified by a bunch of other information that has been spoken about before this. So the word people in this sentence might mean something that is slightly different. So the way that you need to attend to the word people in this sentence has to be adjusted a little. The way when you read a particular sentence, when you look at a particular word, you don't look at its dictionary meaning. You look at the meaning of that particular word in the context of the words that have been spoken about earlier. So you need to sort of adjust your understanding of that particular word to the words that have either been spoken about or the concepts of the words that have been spoken about before it. It's not necessarily only sentiment, right? It's not necessarily the word sentiment. I'll give you another example. You take the word, for example, mole, right? A mole will have very, very different meanings in different concepts. The word mole can refer to, in chemistry, can refer to 6.023 into 10 to the power of 23, which is the Avogadro's number. Basically, a mole can refer to those many number of atoms, or I would assume that's what it is. The word mole in the context of, let's say, crime, or let's say in the context of, let's say, judiciary and crime and that kind of stuff, can refer to somebody who's a spy, right? A mole in the system can also be referred to as a spy. A mole can also be referred to in the context of, let's say, physiology. The word mole can also be referred to some kind of a thing on your body, right? It can also be referred to something that's a mole on your body as well. Point again being that the word mole could have very different meanings. The word mole can also be an animal. Yeah, absolutely, yes. Can also be an animal. So it depends very, very much on the sentence that it is being spoken about in. right? Again, you need to attend to the word mole very differently in this particular context within this particular sentence. Earlier, when you learned, let's say, word embeddings, I mean, again, I'm not, we should not be fitting into our own plate, right? I mean, this is a lot of work, hard work that has gone in. And I'm talking about how we've improved upon the work that we've done so far, right? We've started from the time where you did not even have words being represented as numbers, right? Words were simply just being represented as numbers using these large, wide matrices. Remember document term matrix, where every row simply just has presence or absence of that particular word in that sentence, right? It was a sparse, wide matrix. Words were being represented as very, very large matrices, as sparse vectors. From there, we went into something called as word embeddings. Word embeddings where, you know, you pass large pieces of text into a model and then you try to learn these dependencies through, by building that particular model itself. Now, the problem or one of the drawbacks of word embeddings was that word embeddings learned global dependency. If you look at glove as the model, those are global vectors. They were learning global dependencies. So the word mole would have all these meanings, might also somehow be represented using word embeddings. But what it might not represent is, but what it might not adjust itself to is, if let's say I have a sentence which says I have, or rather this solution has a mole of, let's say, I don't know, calcium in it. I'm just making it up here. I have no clue that that's even a valid sentence. Completely forgot my chemistry sessions from school, but I'm just making it up. So if you take for example a sentence like this, the solution has a mole of calcium. Now the word mole here might be referring to, if I were to just simply go with word embeddings, it would give me a vector for sure. But this vector is a generic learning, a generic representation of the word mole from everything that we may have learned from a large corpus of data. But in this particular sentence, the word mole, remember, is referring to calcium, is referring to solution. So I'm probably referring to the word mole in the context of chemistry. So I would want to adjust this particular word embedding to a slightly different version of the same embedding. I would want to maybe add some numbers, remove some numbers, basically slightly adjust it to a different representation of the same word. That is what we mean by attention. So I would like to attend to this particular word and its embedding in the context of, or in the presence of, its surrounding words. So the way we need to attend to this particular word in its surroundings will have to slightly adjust, slightly change. Now, how do you make that change? How do you make this adjustment? That is what we will discuss on the other side, where we discuss about something called as the attention mechanism itself. Who does the job of attention? I mean adjustment. There is a model for it, right? That attention is exactly that's exactly happening inside this. Whatever you see here, that's exactly what's happening. You pass raw embeddings and those attentions are computed inside this. Those adjustments are happening inside the model itself. But we'll exactly understand how that works. The model also doesn't predict the context, it understands the exact context. It does a fantastic job of extracting that context and adjusting that particular word to its context. As per the subject, the word meaning will output, the word meaning will change. The numeric representation of that word will get adjusted. Yeah. We broadly understand the idea of attention. Now let's get into the actual math of it, right? Like, how does attention really work? The underlying core math of it itself. I'm going to switch screens because I just want to switch to one of the one of the topics where, yeah, so I think this is your, the encoder decoder architecture. I think we broadly spoke about this: input, the encoder, decoder with the output sequence, and then that generates the probabilities as the output. So that's pretty straightforward. Let's actually take a sentence like this, or else let me actually write it here. It's easier for me to then. All right, let's take a sentence, any sentence for that matter. Um, let's take let's take a sentence like this, right? So if you take, for example, a sentence like this, as I said, the obvious way to go forward, if you were to deal with this with RNNs, would have been you would use any of the embedding models. You would have created, let's say, the embedding vectors out of this, or train custom embeddings, from each of these, and then use that to take it forward. That would have been the most obvious way, to go forward. However, in the case of attention, how are we going to do it? We're going to do it slightly differently. So let's take each of these words. Okay. So I'm going to use x1, x2, x3, 4, x5, x6. These are all different words, right? The convenience that I'm assuming here, and this is a convenient lie rather, is I'm assuming that this sentence is fundamentally getting broken down by words, which may not necessarily be true at all times, right? So when you talk about breaking a particular word down, you would always try to tokenize it, meaning break it down to some of its root forms. Like for example, the word amazing would have become amaze plus ing, would have actually been two tokens instead of one token. But I'm just for the explanation sake, I'm assuming this to be like a very simple. Um, I'm assuming this to be sort of a very simplistic representation here in this case, right? So let's take, for example, day as an example. If you take the word day, x5 for that matter, as I said, the word day would have had a default embedding, right? Whatever that embedding is. Let's consider x5, x6, x7. These are the default embedding. These are the right. These are the default embeddings, right? So this is understanding attention. These would have been the default embeddings, and these are embeddings that you would have generated through, let's say, any of your traditional embedding algorithm, or you can actually train those algorithms, train those embeddings as well. Doesn't matter. The question is, how do you adjust this particular word day? I'm taking day as an example here. If you take, for example, this particular word day, x5, this word day is not in its best shape here. We would probably have to adjust the word day to ensure that it also gets adjusted to the word embedding. Amazing here, because the word day is being qualified by the word amazing, or if the word amazing is qualifying the word day. Amazing is the adjective, day is the noun itself. So this particular noun is being qualified by the word amazing. Similarly, the word day is also dependent somehow on Dave, because Dave has, Dave is the one that has actually had an amazing day. So the word day is also dependent on the word Dave in some shape or form, and so on and so forth. You can think of how some of the other words are also dependent on the others. So how do you adjust these embeddings? So to adjust these embeddings, right, one of the most simplest ways to do this is, we say, you could essentially take these words, um, and you can think of trying to somehow multiply these embeddings that you see here, right? Somehow, and take these embeddings. So for example, if you take x5, I'm going to create something called as y5, which is an adjusted embedding of x5. or of the word day, and I'm going to say Wi-Fi is somehow a numeric representation of W1 X1. So it is a combination of the embeddings of all the other words. W2 X2, W3 X3, plus all the way until W8 X8. What am I saying here? All that I'm saying, look, this word Wi-Fi or this word day has a new embedding representation. This embedding representation is not the same as the older representation. This representation is a linear combination of all the other embeddings that I have here. Meaning, in some shape, if let's say the word day is heavily dependent on the word amazing, then X4 or W4 would have been a very, very large number, and W4 would have contributed to X4. So W4 would contribute more to the word X5, and thereby the summation would have been much larger in this particular case, right? W1 would probably also be very large. Maybe the word W2, W3 might be actually much smaller. W8 or W7 might also be very, very small, because these words may not necessarily contribute a lot to the word over here, which is W5 or X5. My point being that the new adjusted embedding could be created as a linear combination of the original embeddings itself. So this way, you could potentially get all of your new embeddings. Right? You could potentially get all of your new embeddings as a linear combination of your original embedding. But the question is, from where will you get the W's? So your final embeddings are over here going to be, instead of X1, X2, X3, X4, the final embeddings that you would probably be working with is probably going to be Y1, Y2, Y3, Y4, and so on all the way until Y8. These are going to be the final embeddings that you'll probably be working with. But the question is, how will you get these W's? Where will you get these W's from? Who's going to give us these W's? Where are you going to get these W's from? And that's what we'll discuss. Again, it's those W's that will tell us in what form or what combination do you need to combine these existing embeddings of these sentences to create a better embedding or a better representation of that particular word in this context. Shubharam, it can be any of your existing embedding models. It can be a Word2Vec model, it can be a skipgram model, it can be any of the models, or it can be a fresh embedding itself, right? You can just train a fresh embedding itself for all you know. Every new embedding now, which is Y1, Y2, Y3, all the way until Y8, in this context, these W's are to be identified, and we need to understand where these W's will come from. These W's are nothing but the relevance of a particular word in the context of this particular setup. In this sentence, it's the context of the word that is associated with the others. But what you need to understand is these words or these weights are specifically these weights over here that you see. You know, when you create Wi-Fi, these weights are specifically for Wi-Fi. Similarly, you will have other weights for X1, you will have similar weights for X2, similar weights for X3, similar weights for X4, for X6, X7, and X8 respectively. My point is, you will have different sets of weights that will combine for each of these individual vectors, and thereby creating the final output. That's one thing that you need to visualize. That's one thing you need to understand. Now let's go one step further. So how do you get these weights? Where will you get these weights from? So as I said, these weights are essentially, I mean, it's not very straightforward. There are some very simplistic ways of thinking about it, but I'll tell you the most, for a lack of a better word, I'll tell you the most, the actual technical way of getting to the final weights itself. So the way we will get to these final weights is, remember, these weights have to be trained, right? There is no rule of thumb. You cannot just randomly get to these weights right away. So to get to these weights, you will of course have to go step by step. There are other sub weights that are sort of created. Let me give you a simple example here. So to get to, let's stick with any of these. Let's stick with Wi-Fi or whatever. As I said, we will have different sets of weights that we'll introduce to compute W1, W2, W3, all the way until W8. But how will you compute them? If you take, for example, so we will be introducing two sets of new matrices called the query vector or the query matrix Q and the key vectors. Now, what is the query and the key vector respectively? So, for example, if you take the query vector, what does the query vector here mean? If you remember, what did I tell you? The word day, right, is being qualified by this particular word amazing. Amazing is the adjective, day is the noun. So one of the ways to think about it is, okay, what are the words that are qualifying the word day? You somehow need to find what words in this particular sentence are qualifying the word day. Once you know what those words are, then you can use the respective vectors and then somehow combine it. But how will you know what those words really are? You would of course not know it. We will have to learn those using these vectors. So I'm going to be introducing something called as Q5, which is nothing but a query vector, which is going to try and query for, okay, what are the words that are qualifying the word day? What are the words that have the dependency of this particular word day? So that will be WQ multiplied by X5. Right? This is specifically for the word day, right? So Q5 is WQ multiplied by X5. That's the first one. Then you would also have a key vector for each of the other words. So K1, K2, K3, and so on and so forth. Now, what are these key vectors? These key vectors are simply nothing but they are essentially going to carry the value. These key vectors are going to be the actual values of these inputs itself. So K1 is simply nothing but WK times X1. Similarly, K2 is WK times X2 all the way up until K8 is WK times X8. So now what's going to happen is we are now going to try and multiply the query and the key vectors over here. So the way for you to understand this is like a large matrix. So you have the key vectors K1, K2, K3 all the way until K8. And then you have the query vectors Q1, Q2, Q3, Q8. So you have Q5 here. So you're essentially going to take, the values of Q5 multiplied with K1. You're going to multiply Q5 with multiplied with K1, Q5 multiplied with K2, Q5 multiplied with K3, all the way until Q8 multiplied with Q5 multiplied with K8. So the query and the key vectors essentially going to multiply themselves. And wherever you see that the value is very large, meaning the inner product, the multiplication of both of these vectors, if you think is very large, that's an indication to say that, look, this particular vector, right, this particular vector, which is word 5, this input vector, or rather, sorry, not W5, this input vector X5 has a large, so for example, if this number is very large and this number is very large, it's a way to tell you that, hey, you know what, looks like X5 has a lot of dependence on QK2 or the other W2 and also on W8. It's a way to identify that the inner product is very large. It's a way to identify that these two vectors have a lot of dependency between each other. That's what we are sort of trying to get at. In a way, we're trying to find dependency. In a way, we're trying to find some level of overlap between both of these vectors, right? X5 and, or rather, each of the words, so to say. I just want to keep the notation the same here. I don't want to confuse you all. X1, X2, X3, all the way until X8. and so on and so forth. So in a way, you're sort of trying to combine the overlap. Okay, so I'll simplify this. Take any two vectors, take any two words. Okay, so let's actually go back here. Let me explain the concept and then we'll get into the math a little. The concept here is, the intuition here is, if you take any two words, these two words, if they are similar, the concept here is that if you take, for example, any two words, right? Like for example, in this case, the word day and let's say the word amazing, if they have something in common between each other, when you combine the two of them, or when you take an inner product of both of these vectors, it would typically yield a large value. If there is anything in common between both of these, the dot product between any of these two vectors should ideally yield a large value. Do we agree with that? If there are two vectors which are similar, if you multiply both the vectors, any bit of commonality between the two would yield a large value. So in theory, that is what we are trying to understand. That is what we are trying to do here. We are facilitating that multiplication. We are creating one query vector, which is the vector that we are trying to find similarity for. This is the word x5 that we're trying to find similarity for, right? And then there are these other candidate vectors, which are other words, which we're trying to find similarity against, right? So we are trying to basically find similarity for x5 with x1, x2, x3, and so on and so forth. We don't want to take the raw vectors themselves, because the raw vectors themselves, because again, these are vectors that are coming out of an embedding vector. They, you might want to, let's say, multiply them with other, you might want to, let's say, either shrink these vectors down, you want to reduce them in terms of dimensions. That is why you're providing these other word, WQ and WK, to ensure that you're not, again, this is more for computation as well, and to also sort of control, to also adjust for what kind of information you want to pass into it and what you don't want to pass into it. These are tunable parameters. So for that reason, you just multiply them with another vector, just to kind of make sure that you're passing the right, or you're extracting the right information out of it. Those are like regulators. Think of these as regulators, right? But fundamentally, what you're doing is you're essentially multiplying each of these vectors against each other to see if there are, let's say, 10 vectors, 8 vectors here. So x5 is multiplied with all the 8 vectors to see where the similarity is going to be the highest. If the inner product, if the dot product across both of these is very, very high anywhere, right? If Q5 multiplied by K2 is very large, what that means is somewhere Q5 and K2 have some commonality with each other. In a way, you're trying to compute some kind of a correlation, not exactly correlation, some kind of a correlation you're trying to understand. So you have the query and then you have the key vectors. The query vectors are the vectors that you're trying to find similarity for. So these are, whatever you see at the top, these are query vectors. These are your key vectors. And you're trying to find similarity against each other. Then, once this multiplication is done, you're of course going to perform this multiplication against every, every word, against every every query vector, against every key vector. Okay. And after that multiplication is done, you're going to get, by the way, this value that you see here, that multiplication, we will simply refer to it as Z, or the new vector. We simply represent it with a small z here. So Z1 is simply going to be, in this particular context, Z1 is simply going to be K1 multiplied by Q5, or in a way, simply put, Z1 phi. Now this is K1 multiplied by Q5. This is Z1 phi. Similarly, Z2 phi is going to be what? K2 multiplied by Q5. These are essentially these values. This is Z1 phi, Z2 phi, Z3 phi, Z8 phi, so to say. That's essentially what these values really are over here. And then if you then how do you get the dependency out of this? Then how do you get the dependency out of this? So after you get all the values of Z here, after that, you simply apply the final weights are going to be what? So the weights W1, W2, W3 all the way until W8 for the vector phi or for the word phi are going to be a softmax of Z1 phi, Z2 phi, all the way up until Z8 phi. So you're essentially simply normalizing all of these values that you see here. You're simply normalizing all of these values here. How many values will you have here, by the way? You'll have a total of 8 values. So that will give you all the vectors, all the weights. So when you do a softmax, what are you going to get? So you will normalize the values. You're not picking the values with high probability, you're normalizing it. Argmax will pick the one with the high probability. This will convert everything into probabilities or normalize the whole thing to 1. It'll basically normalize the values to 1. Does that make sense? Because these are simply dot products. So it can vary from negative infinity to positive infinity. So this will simply give you values like, W1 all the way up until W8 for the vector 5 will be something like 0.1, 0.8, 0.2, or rather, sorry, 0.02, 0.06, 0.01, and so on and so forth. You'll have values like that. That way, you will get the weights. But this is specifically for 5. No, there's no average. This is for W5, sorry, for X5. So what is the final Wi-Fi? Whatever weights that you've got here, W1 times X1 plus W2 times X2 plus W3 times X3 plus all the way until W8 times X8. This is the new vector Wi-Fi. Remember, these weights over here are these weights that you got from here. Is this clear, everyone? This is only for Wi-Fi, my friends. Artificial intelligence is transforming the human. So if you look at the word artificial intelligence, look what happened. Artificial intelligence is transforming the has actually been broken down into um, artificial is broken down into art, and efficial intelligence is transforming. This is how it's got tokenized, by the way. There's an algorithm that is used to tokenize it. Then there is a token embedding, basically just a number. Every token has its own embedding, right? So if you think of it, there is some kind of an embedding that is created over here. 768 long vector embedding converts tokens into semantically meaningful numeric representation. How does it come? It comes from any of your word-to-vec models, or it can be a simple numeric representation. What's the size of the input vector here, and everyone? This embedding is of what size? Each word is of the size 786 or 768. Each word, so this is x1, x2, x3, x4, x5. Each vector is of size 768 here. After that, there is something called positional encoding. We'll come to positional encoding in a minute. Let's not worry about positional encoding. It'll be too much for us to worry about for the moment. Let's just ignore positional encoding for the moment. It's just a way for it to embed the size of the positional encoding. Now let's get into some of the detail here. So the QKV computation. So let's go one by one. By the way, here are the attention weights that are coming out. Okay, let's understand one by one. You forget about the value over here. You forget about this particular value here for a minute. Just focus on the Q and the K vectors. Right, the Q and the K vectors. The query and the key vectors over here, each are of the size. Let's take any of these. Let's take one of these. Just a second. I'm trying to get into a little bit of detail. Yeah. This is residual. That's fine. Yeah. So here's the here's the computation that you see here. What is exactly happening in this particular process is, if you see this word art has its own embedding. This is getting multiplied by, as you see here, yeah, this is getting multiplied by the query vector. Similarly, this query vector over here is available. The problem with this is that it doesn't hold for a second. This query vector is getting created here. So E11, so whatever you are observing here is Q times K dot V, but you forget about the V for a second. Q dot K is what is getting computed here. Now, whatever you're observing here, Q dot K is what is getting computed here in this particular setup, in this particular step. And that is being combined. So whatever you get out of the key is getting multiplied by what is coming out of the query. Both of these are getting multiplied, and then the way both that dot product is being computed here. So this is Z for you. This is the values in terms of Z for you, whatever you're seeing. And these Zs, you're applying a softmax over here. These Zs are essentially going through softmax over here, right? That softmax. So if you see here, if you look at that computation over here, Q dot K transpose, or rather Q dot K, your query and the key vectors are both getting multiplied. And then there is a softmax being applied around it. It is divided by root of under root dk, and there's some mathematical nuance over there that is for smoothing and those kind of purposes. Don't worry about that for the moment. Again, minor detail. But as you can see, the output that you're getting out of here is a softmax output that ranges from -1 to -1 to +1. It'll typically be only 0 to 1 in most cases. It'll just sum up to 1. As you can see here, all of these values are simply going to sum up to 1. That's it. So those are your retention weights. These are your W1, W2, W3, W4, W5, and so on and so forth. You're taking the output from the key, output from the query, multiplying both of it, and then you're trying to get to a certain number. Now, what's interesting here is as you see, there is a part of scaling masking that happens here. What do you mean by masking? See, when you're computing something for this particular word, right? If you take, for example, the word art, the word art cannot be dependent on any of its future words. Art cannot be dependent on facial intelligence is transforming because art is being spoken first, right? Similarly here, if you take the word artificial is not dependent on any of the other future spoken words. The vice versa is possible. If you take, for example, any of this, if you take the word this word can be dependent on any of its past words, which is why all of the upper triangular matrix that you see here, they've all been forced to sort of a zero. If you see here, they've all been forced to zeros. Those do not contribute to your attention at all. This upper triangular matrix over here, that will never contribute to your to your attention values itself. Exactly. Most of the words dependent on the past words. They don't depend on the future words, which is why you simply just get rid of those values. That's the reason they will actually be made negative infinities. The reason, Ashish, they're made negative infinities is because when you apply softmax, they'll be made zeros. So technically, in the process, they're actually made negative infinity. So you force them to negative infinity. That way, you can ensure that the softmax will push it to zeros. Because you again want the summation to become 1, right? So softmax of negative infinity is 0. But anyways, that's essentially the output, guys. That's how this thing works. This, my friends, is the attention part of it. That's the first step. The other thing that I want to talk about is, if you look at by the way, the QKV weight matrices are all off. If you look at here, the QKV computation that you see here, if you look at we'll come to the V matrix in a minute. But if you look at the Q and the K matrices, they are square matrices, 768 by 768. Why 768? Because the input matrix is of size 6 by 768. Each word is 768 vectors in long, size in long. So when you have a query matrix which is of size 768 by 768, when you multiply, you will get when you take, for example, when you multiply this 6 by 768 with 768 by 768, you will of course get a matrix that is going to look like this. Um, you will of course get each of this is essentially going to become a size that big, 6 by 768 again in terms of rows. And all of those are essentially stacked against each other, and then you simply summed up, multiply. You of course take a dot product against each of those. That's how you get, two parts. That's how you get the summation of here. But again, don't worry about the underlying too much detail. So this, by the way, is first head. This is one computation of QKV, Q and K. Similarly, the same thing will happen across 12 different such processes. Whatever we are seeing here, the same thing will happen. Multi-computing attention will happen across multiple heads. Heads meaning simply multiple blocks. The same thing will happen across multiple blocks, which is why this is referred to as this is referred to as self-attention. Why is it called self-attention? Because you are computing the attention of a particular word with its own self. Then multi-head self-attention, because you're computing the self-attention across multiple, this process is repeated multiple times. This process of computing this attention is repeated multiple times. And you're also applying masking. 12 is just a hyperparameter Vani. It's like how you have in a VGG 16, why do you decide to have 16 layers? Same thing here. It's just that it's a parameter, you can change it. And then you have, of course, multiple heads, so which is called multi-head self-attention. But more importantly, there's also some level of masking that's happening here. So in a way, it's also referred to as masked multi-head self-attention, or self-attention with masking. It's also, the term masking is also used because this forcing the upper triangular matrix to zeros, that's referred to as masking. So you just mask the values that are going to have any future dependence. So which is why it's referred as masked multi-head self-attention, or self-attention with multi-head self-attention with masking. Then comes the last part, which is the value. So we looked at the query matrix, we looked at the key matrix. There's also one more vector matrix over here called the value matrix, which is then multiplied with the output of the attention. Whatever output comes out of the attention is further multiplied with this value matrix. Whatever value matrix is also a 768 by 768, same sized matrix again. Whatever you see here, that value matrix is again further multiplied with the, if you look at this, again, the same matrix is sort of multiplied here again. So when we actually go back here, the only difference is that all of the computation remains exactly the same. The only thing is here, after all of this computation is done, this Wi-Fi that you see here, which is nothing but summation of Wixj, right? This is also multiplied by Vj, which is nothing but a value matrix, right? You just don't leave it here. You also multiply it with another matrix over here, another value matrix. Again, another form of a regulator. It's another regulator here in this case. So that's where the value vectors sort of, I think 2 million now. So maybe I might have gotten it wrong. Gemini Pro is probably 2 million, like what Ashish is saying. So that's the query key and value vectors. So once the query key and value vectors, as you can see, the output, whatever you get out of query and key, so you multiply query and key. This is a simplified computation, so it might look simplistic, but whatever you get out of query and key, you further multiply it with the value. Whatever you get as an output, as you see here, the output each of it is size 64 in terms of size. That is sent out for the subsequent steps. What are the subsequent steps here? Just the way we saw. By the way, this is for one block. Similarly, there could be other blocks as well over here. There are other aspects that we will talk about, right? So there is things like, for example, from here, there is a simple multi-layer perceptron. Very, very simple block that you see here. Just, let's go in here. a regular MLP. Hope I can zoom into this. So whatever, the point is whatever output that you get for each of, so this is so the only thing that we've been able to accomplish, you started with a 768 long vector. After the attention, you get a 768 long vector again. Nothing changes. Started with 768, ended with 768. So what happened here? In the process, you've adjusted the vectors for each of these individual input tokens. That is what has happened. So this whole block that you see here, this whole drama, is just to adjust the input vectors of each of the input token into a newer representation. That is what has happened here. After that, we then put it through a bunch of other things, right? So the first step here is you put it through a simple multi-layer perceptron. A multi-layer perceptron over here, and this multi-layer perceptron is like with dropout, you can have multiple. Again, these are, consider these as multiple inputs. Each input can be passed into a regular neural network. Multi-layer perceptron, regular neural network with a regular feed-forward neural network. There are residual connections here. If you've learned ResNet, you would know what that means. But simple residual connections, again, not very complex, simple residual connections. And then last but not the least, you get the output from here. Again, the output also, as you can see here, each of the outputs is again 768 long vector, right? Then all that you do is whatever outputs that you get here, whatever softmax outputs that you're getting here, by the way, so let's go back here once. Whatever output that you're getting here, you will average that across 11 other transformer blocks. So whatever block that you're seeing here, whatever block that is getting highlighted in blue, there are 11 other blocks because there are a total of 12 blocks. All of those blocks are getting summed up here. So if you just look at, yeah, so this, whatever output that you're seeing here for the word field, you're essentially summing up or averaging the output across all the other transformer blocks and then passing it into a simple feed forward neural network, or rather into a simple softmax layer, and predicting what the word would be next, whatever is the word in this particular case. So artificial intelligence is transforming the human. Human is the input word and the output is human field. Should it be field? Should it be the output for the word with the largest is way? So the output here is going to be taken as way in this particular case. The output word here is the human way, transforming the human way. That is the word with the largest probability. So that might be picked up over here. This is a transformer encode, or rather, this is a simple transformer model. Whatever you're looking at over here, this is the process of converting an input into an encoded representation. That is then further passed into, you can either use that to pass it into a softmax and generate an output, or you could pass it into a decoder and generate further output. We'll talk about the rest later. What we saw is you passed an input, passed it into a multi-head attention, passed it into a feed-forward neural network, and you got a numeric representation as an output. You got a vector as an output from the encoder block. You got this vector as an output. If you know how the encoder works, then it's the same piece of stuff on the other side as well. What we saw here is a far more simplified representation of it, of course. What we are seeing here is a far more simplified transformer block. But what you could potentially do is you can take that output, you can take that particular output, right? And then you combine that with your output embedding, whatever words that have come out so far. You compute the multi-head attention for those. You merge all of them, you concatenate all of them over here through attention. So whatever input you're getting, plus the word that you're getting output over here, plus the output words, you combine all of it, and then pass it into a feed-forward neural network, into a softmax layer, generate the output. Simple. The add and normalize is simply, these are add and normalize is layer, is batch normalization. Layer normalization, batch normalization. That's what's happening. This is sort of layer normalization in a way. And the outputs of that particular layer are simply getting normalized. That's what's happening here, nothing else. Right? This is very simple. And these connections that you see here, they are residual connections. So broadly speaking, whatever you are seeing here, so this part is whatever is highlighted is your encoder. Whatever is highlighted is encoder. This part is sort of the decoder part. Now, how you want to use the decoder is totally up to you. Either you can just have an existing decoder, or you can, because you are also going to pass new words as inputs over here, you can use that for decoder, especially if you're doing it for sequence to sequence sort of output. Where is the parallelizing happening in transformer block? So this QKV, so what we have completely eliminated here is we are not treating language anymore as a sequence of words. I mean, it is still a sequence of words, but you're not treating it like a function of time. We're not saying, hey, you know what, you need to treat the first word, then go to the second word, then go to the third word, then go to the fourth word. You completely took that concept of recurrence out of the equation. All that you're doing here with attention is you're treating every word all at the same time. Exactly. All the words are treated at the same time. And because all the words are treated at the same time, everything can be simply matrix, everything is matrix multiplication now. Does that make sense? So you suddenly started to treat sequence of words as just a simple matrix, which is fantastic because you kind of took the whole idea of sequence, context, and everything, and you somehow packed it into this idea of attention. And because of the beauty of attention, you took that concept of recurrence out of the equation. And now all that you're doing is just using attention to, to capture all of that, sequential dependencies. And you're sort of using masking a little smartly here. Because the way you're using masking, you're sort of also capturing that sequence in some form or shape. Because of this concept of masking, you're able to capture that dependency very, very well.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
We're going to discuss the applications of the transformer architecture, right? So as I said, there are many applications of the transformer architecture. One of the most popular ones these days are the GPT models, of course. But before the GPT models came up, right, the GPT family of models came up, there was another family of transformer architectures which was actually fairly popular. So Google had launched this model called the BERT model, which kind of became super popular. Yeah, let me pull this up. Trying to find the right their homepage, but okay, let's look at this. Yeah, this is the paper. So the BERT, pre-training of deep bidirectional transformers for language understanding. This was exactly the model that was launched by Google. Again, a very revolutionary paper at that time. The idea of the BERT model was exactly to improve the language understanding capabilities of from a natural language processing standpoint. And of course, transformer models are really good, and this architecture actually was doing very well, right? So the BERT model was actually one of the first models that had really shaken things up a little. Uh, it's very similar to your it's very similar to your traditional encoder decoder architecture that we just learned. Let's actually go to the paper itself. This was published, as you can see, in 2019. The original model was published in 2017, whereas this model was published in 2019. And then, yeah, the BERT model is actually very similar to that of your regular any of your other transformer models that we may have discussed so far. It's not very different. It's just that this particular model was used for a bunch of others, specific tasks, so to say. So I I'm not going to go into too much detail here, but I'm just going to talk about specific concepts around the BERT model itself, right? So we'll actually look at how a BERT model can be implemented. Let's actually start with a very, very simple. Let's start with how one could use, let's say, some of these transformer models. Interestingly enough, as I had said, a lot of these transformer models were launched over the last few years, right? So last 2 to 3 years, what we observed is a lot of transformer models were launched. They were all based on the same concept that we had discussed, right? They're all based on the same exact architecture, but making some minor changes here and there, different languages. Some of them are being used for classification, some of them being used for some of them being used for specific natural language processing tasks, some of them for embedding creations, and so on and so forth. So what has happened is, as an outcome of this, so on one side, the model architecture is very popular. On the other side, what was also being discussed, what was also being introduced, is a lot of variants of these transformer models. The idea now is for us to go one step further and to see if we could combine all of these, and if you could create like a simple interface where you could access all of these different models. So the interface that sort of came out to be one of the most popular interfaces in this particular case is the Hugging Face architecture. Let's go here. We'll be taking this one step further. We'll of course be trying to understand how the transformers library can be accessed using this library called Hugging Face, right? So there's a very, very popular library called Hugging Face that sort of came out to be, or rather a group that had launched a library called the Transformers Library. The primary purpose of the Transformers Library was just to make all of the Transformers model available through a very, very simple interface, right? To a very simple library like interface. Let me actually quickly show you how this looks like. So here you go. There you go. So here's the Transformers library. So the Transformers library, as I said, is very much like your scikit-learn. In your sklearn, you just have access to all of the traditional machine learning models, whereas the Transformers library here provides you access to all of these models that we spoke about, right? Be it BERT, or let's say any of those other variants that you may think of. All of those models are nicely available for all of us to access. So you could do all of these different tasks, for example, like natural language processing, computer vision, audio, any of the other multimodal tasks as well. You could use the Transformers library to kind of go through each one of those. So let's exactly understand how one could access any of these different models. By the way, as I said, there are a bunch of different models that are available. So for example, if you want to access a model called BERT, this BERT model can be accessed through PyTorch, can be accessed through the Transformers library via TensorFlow. You can also access it through Flax. Flax is another modeling software. You could use that as well. So a bunch of different models can be accessed through all of these different these different programming languages. The default, as you can see here, is PyTorch. PyTorch is of course the default model or a framework that can be used to access all of these different all of that can be used to access all of these different models. Let me actually quickly give you a let me give you a very, very quick introduction to Hugging Face, and then we can take it from there. Okay, so let me quickly show you how you could access all of this. Let me Perfect. So I'm not going to get into like a lot of detail here, but I'm just going to briefly touch upon this. So what is Hugging Face? Hugging Face is this is sort of a tricky question because Hugging Face today, the modern day setup has a lot of offerings, right? So Hugging Face is also it has libraries, it has a platform where it is also like a community. It is like an open source repository of models, data sets, and so on and so forth. So it could do like a bunch of different things. Um, Here are some examples, right? So the core offerings of Hugging Face, they provide you a repository of models, open source models. They provide you a repository of data sets. They provide you something called as spaces, which is like for you to simply go and execute stuff, right? And of course, you have documentation, libraries, and a bunch of different things, right? So you have a community and all of that. Um, so what we're going to be doing is I'll just quickly show you how you could access some of these models, right? Hugging Face today hosts a bunch of different models, right? So you have the large language models, your diffusion models, text to image models, so on and so forth. So all of these base transformer models, as well as the more complex large language models, diffusion models, all of those are completely available for someone to access using the platform called as Hugging Face, or using this library called as Hugging Face. Let me quickly show you an example of how one could do this, right? So if you take, for example, here, let me go to the website itself. I don't want to, let's go all the way up here. So if you go to models, right? So if you just go to the models tab here, right? In the models tab, you see all of these different models that are available, right? So you could simply click on any of these models and you can pick up, and then you can understand, okay, what is this particular model? So this is a reflection llama model. Let's actually look for a simple BERT model. I don't want to overcomplicate this. Let's go text classification. Okay, let's look at this model called distal BERT. I'm trying to find a BERT model itself. Okay, so there you go. This is the BERT model. This is the older BERT model. BERT large uncased whole word masking fine-tuned squad. This is essentially saying the BERT large model. Uncased meaning it is trained on uncased dataset. Whole word, the complete word is being used as a token. Masking, so there was some kind of a masking that was taken place, and it was fine-tuned for squad. There's a dataset called squad, and it was fine-tuned for that particular dataset called squad. So you can actually read about this. You see something called as a model card here. Pre-trained model on English language using masked language modeling objective. It was introduced in this particular paper. Uh, Firstly released in this repository, blah, blah, blah. So there's all of that information that's available for you. Let's actually take one example of the BERT model itself. This model has the following configuration. It's a 24 layer model, 1024 hidden dimensions, 16 attention heads, 336 million parameters. So 16 attention heads. What does that mean? Spoke about multi-head attention. Remember multi-head attention? We spoke about multi-head attention in a previous session. Exactly. So what we're saying is 16 attention heads are there. In the example that we may have seen, it would have had, if you remember, that should have had around, it would have had 12 attention heads. They would have spoken about 12 attention heads here. However, the Google BERT model has 16 attention heads. That's how they have fine-tuned this particular model too. Okay. So this model should be used as a question answering model. You could use this particular model for doing any kind of Q&A, any kind of question answering. And you can use this for performing specific, question answering setup. Given a certain corpus, you can use this particular model for doing any kind of question answering. So let's exactly understand how you could use any of these pre-trained models. Remember, these are all pre-trained models, right? So what you could do using this model is you could use, you can pass a paragraph like this. You can ask a question like this, and it would try to answer from this particular paragraph. It would try to answer this particular question from this particular context. So given a piece of context and of question, this model tries to answer that from this particular model itself. That's essentially how this model works. As you can see here, which name is also used to describe the Amazon rainforest. And you have like a complete paragraph that has all of the context here. You can simply say compute. I need to log in here. Perfect. Compute, and it would execute and it would return an answer saying Amazonia, which name is also used to describe the Amazon rainforest in English. Amazonia, the Amazon rainforest. and all of these names, also known as in English as Amazonia. As you can see here, that is the response, and it has come back with that particular response over here. So that kind of question answering can be done using a model like this. Remember, this model is the same as the one that was published here, right? So it is exactly the same sort of a model that was discussed earlier as well. This particular model is the same transformer architecture only that was used, but given a piece of context, it tries to do question answering. Instead of generating new content, it does question answering. That's the only difference. So there are different tasks that this particular bird model has been trained on, right? There is no left to right or right to left language models to pre-train BERT. Instead, we pre-train BERT using two unsupervised tasks. There are two specific tasks that they've taken to train the BERT model. They don't just do word prediction. Instead, they use something slightly different. They don't try to predict the next word. In the case of the BERT model, they've trained it using a slightly different technique. What are the different techniques? Something called as masked language modeling. The idea of a masked language modeling is, given a particular sentence, they kind of mask a particular word. It's like fill in the blanks, right? So you take a sentence, you try to make one word, you mask one word, and you try to populate that particular word, and that empty word is at random, right? So intuitively, it is reasonable to believe that deep bidirectional models is strictly more powerful than either a left to right or right to left model, because you bidirectional, your learning flow from left to right as well as right to left. Unfortunately, standard conditional models can only be trained left to right or right to left. Hence, we train it using something called as masked language model. How does it work? We simply mask some percentage of the input tokens at random and then predict those masked tokens. So it's like fill in the blanks. You take a sentence, try to make one word empty, and then you try to predict what that particular word is. And this procedure is referred to as masked language modeling. This is exactly how this particular model has been trained. So in this particular case, around 15% of the tokens have been masked at random, given any particular sentence, and they try to populate it. Now, this is a way to learn the relationships between words given any particular sentence. That's how they learn the relationships. There's another task also that they use called next sentence prediction. Many important downstream tasks such as question answering and natural language inferencing are based on understanding the relationship between any two sentences. The other task that this model has also been trained on is to be able to predict the next sentence. Given a bunch of sentences, it also tries to predict that next sentence. So this is how the BERT model has been trained. It is slightly different from your regular transformer architecture itself. That's one point that I want you all to understand. But anyways, going back here to the case of your BERT, sorry, to going back to the case of your, to the BERT model itself, um, let's quickly understand how you could use, firstly, the transformers, the Hugging Face interface, and then, or rather, the Hugging Face library. And then, secondly, what we'll also do is we'll try to perform some kind of a quick. We'll also try to perform like a quick question answering sort of a setup using the BERT model, one of these BERT models. There you go. Let's go. So, tag exclamation pip install transformers. So you will have to run the pip install transformers. So in this particular example, all right, here you go. So this is the transformers library. So what I'm doing here is look at this. So from transformers import pipeline. Pipeline is like a default default object that is available. And I'm saying, hey, in pipeline, I want to do something called as a sentiment analysis. And what it's doing is it is fetching a default model for this pipeline exercise over here, and it is trying to perform the classification over here. So it is trying to do sentiment analysis. So as you can see, please install the backward compatible TF-Keras package with pip install TF-Keras. Let's do that. Let's do that. let me switch, or else let me just go to PyTorch. This should be able to execute it otherwise. Yeah, there's a version mismatch of the libraries. Yeah, so it's using this model called Distilbert base uncased fine tune SST2. So it is using this particular model. It's going to this particular model. This is the default model that is being utilized to perform this particular classification. So what am I doing? I'm saying, hey, pipeline. And in this particular pipeline, what we are saying is it's a factory method in the case of Hugging Face. So it takes two aspects as inputs. It takes one called as a tokenizer and the second called as a model. It takes both of these as input. It is not mandatory for me to provide it. There is also a default that is available for this, which is what is currently being utilized. And then after that, it is able to perform the classification itself. So the classifier takes this particular sentence as an input and it performs the classification. It's saying, hey, the classification for this particular model is negative with a score of 0.99. The experience with the Apple customer care has been horrible. And as you can imagine, this is a negative sentiment and it has returned a negative score for this particular sentence. In this case, what's happening is it is taking this model and performing a simple sentiment analysis exercise on top of this. Now, I have not trained the model here. It is using an existing model. It is using an existing model that is already available on Hugging Face, downloading that particular model and simply performing a classification using that particular model. I have not supplied any model, but as you can see, it has defaulted to this particular model. So the default of this pipeline model is, of this pipeline class is this particular model, Distilbert base uncased fine-tuned SST2 English. So this model is the default model that is available. It has simply performed that classification for us over here right now. I'm only doing inferencing here. I'm not doing anything else. I'm just taking the model, taking my sentence and performing this classification here. I'm not building the model. This is using a pre-trained model in this particular case. Now I'm going to perform something called as a zero-shot classification. This is the score of this prediction, probability score. Let's do a zero-shot classification. What do you mean by zero-shot classification? See, there are multiple ways of performing this particular classification. So to perform a typical classification, you would take a data set, 10,000 observations, pass it into a model, train the model to perform the binary class classification or three class classification or multi-class classification. That's the regular approach to perform a classification problem. But what you can also do using some of these models, and that's the beauty of how these models are, is you can just pass a sentence and you can say, hey, look, I need to classify this particular sentence into one of these three categories. I tell it nothing else. I pass a model, I pass a sentence, and I say, hey, take this particular sentence and classify it into one of these three categories. And that's it. That's what it does. It takes this sentence and performs the classification for me. And in this case, it's using Facebook BART Large MNLI, which is another model that is being used for performing this particular classification. Who has decided what model to use for what, for what task? Did you decide? Did I decide? No. The Hugging Face guys who built this particular model decided that for us. Can you also choose which model to use? Absolutely, yes. In this pipeline model, you can change this model to any of the other models. And I'll also show you that. Like, how can you pass your own model for a specific task? You can definitely do that. You can change the model and you can perform your own classification as well. But do you get that? This is the beauty of a model like this, a library like this, like transformers. You're still working with code, but they've completely abstracted all of the open source models that are available right now. Text generation. This one seems familiar. Text generation. So I'm using this model and I'm asking it to generate text. So the moment I say text generation, it is defaulting to the GPT-2 model. The GPT-2 model was an open source model back in the day. It was actually available for everybody to use. The GPT and the GPT-2 models, both of these models were free, were open source for everybody to use. Only from GPT-3, 3.5, things started to change. because a lot of people, ChatGPT then came in. So things started to become very, very complex. That's when they decided they're not going to open source the models anymore. Hugging Face only stores it as a repository, Vani. That's exactly what I was showing you here. So if you actually go up here, if you go to models, Hugging Face has all of these models available with them on their cloud infrastructure. So if you want any of these models, you can just go in here, you can download this model, or you could just use some of this code and you can also execute it. Remember, I spoke about masked language modeling? Like, of course, I should also be able to do that, right? Just the way text generation, I should also be able to fill a mask. This course will teach you all about mask models in the AI space. And I try to fill what the mask is. And I've asked it to make the top 2 predictions. So it has used Distill Roberta, which is another model, which is again, Hugging Face has chosen this model for us. You can switch to any other model you want, but it has predicted this as, instead of mask, it has predicted this as predictive models, or it also made a prediction of something called as role models, which kind of is ridiculous. All about role models in the AI space, which sounds right, but that's probably not we intended. This course will teach you all about role models in the AI space. Well, role models in the AI space is not a bad sentence. Grammatically, it's all right, but it's just that that's not what I am referring to, at least in this context. Maybe predictive models is still not a bad. Yeah, just for it to predict the top 2, it has predicted top 2 here. This is what I wanted to show you all. I don't know if I'd already shown this to you all, but so what do you observe here? It's a very interesting visualization, by the way. So if you see here, 2017 was when the transformer models was published, right? It was around 2017 or so the paper was published. And then from here, what do you observe? You see 2019 BERT was published. BERT started to become very, very popular, right? Encoder models, right? So for generating any kind of embeddings, using them for some specific tasks, all of that started to become very, very popular here. So you see BERT, Distilbert, Roberta. Exactly, those are the examples that we're all using, that I'm all showing you, by the way. Those tasks in the Hugging Face model, they were all using the same models. Suddenly, it also used the GPT-2 model. When the moment I spoke about text generation, it went here. I said generate text generation, and it went to the GPT-2 model, right? It also actually went for the BART model. It also picked up the BART model when I wanted it to do like mask language modeling. It went to the BART model as well. So my point is, everything that you just saw is basically this space. Everything in this area is what I just showed you. Everything here you have done in the past. Word embeddings, word to vec, glove, all of that. All of that you had already done, right? So the glove models, the word to vec models, I think we did, you might have done this using GenSim or some other libraries in your sessions. This, I'm showing you how to use all of this through Hugging Face, right? How use some of these models through Hugging Face. Then comes the next level, which is this part. Then people suddenly realized that, you know what, these transformer models are doing very, very well, but they suddenly started to realize, man, if we actually pump more data into it, these models have a lot of capacity, a lot of capability. And that's when they started to create larger models. And thereby, these large language models became more popular. That's how the LLMs then came into existence. The Hugging Face models, or the models that we are trying to access through Hugging Face, they were all open source at a point. The foundations of everything that has become so popular now, the foundations of all of that was open source, was free for everybody to use, right? It was basically active research. Companies like your Hugging Face, the companies like your Hugging Face and stuff like that, that is just that is providing all of these models for people to access. But suddenly, what has happened is we've suddenly progressed from here to here. And the reason for that is because these transformer models are so powerful that suddenly in 2021, in 22, later half of 22 and early parts of 23, people started to create more and more and more and more models, right? If I actually create the same timeline for 2024, you would not believe how long this thing would be, because there's so many models. That place is now so cluttered. It's so hard for people to keep a track of. So the number of models that got published much later are so many more, and becomes very complex for people to start working with. Long story short, that these language models that we are trying to access, you could have earlier also done them through Hugging Face. The thing is, Hugging Face has also still kept itself very relevant, right? Hugging Face has also still kept itself very relevant. So what it has also done is, even in this particular space, all the models that are open source, right, like the Llama 2, Llama models, and so on and so forth, it has provided all of that through the Hugging Face platform itself. And it has provided all of those models through the Hugging Face platform itself. So I'll quickly show you how you could maybe use one of the models for a specific task, like a classification or like a question answering. I'll just show you how you could do it, and then that would already give you like a good idea of how you could use the same for some of the other models. What is the difference between the left branch and the right branch? We'll discuss that. Raghav will discuss that, not right away, but we'll definitely discuss that. All right, let's go back to the Hugging Face tutorial. So by now we know how to perform all of these classifications, text generation, mask filling, question answering. All of that is available. Um, there are a bunch of encoder models, right? The kind of tasks that you can do with encoder model is things like these. Here you go, Raghava. Encoder models can perform things like these, like sentence classification, named entity recognition, question answering, extractive question answering, right? Extractive question answering can be done using the encoder models, right? Your BERT and stuff like that. Your decoder models can do text generation. They're only for text generation. You remember in the encoder decoder setup, you have on the left side, you have the encoder, on the right side, you have the decoder. If you just use the left part, if you pass a piece of text as an input, you generate numbers as an output, right? So you could use those embeddings for doing any kind of classification, for predicting any kind of words, for predicting the next word, for question answering and stuff like that. So you could do it for all of that. But if you just use the right part, right? If you just use the right part, you could do it for text generation. Meaning, if I just give you an initial word, if I just tell you what the first word is, you can automatically start generating text. You can just take the second part and then you can start generating one word after the other after that. That's basically text generation. Encoder, decoder, you require both an encoder as well as a decoder if you want to do something more, right? So if you want to do things like summarization, if you want to do translation, of course, you need a encoder as well as a decoder. If you want to do generative question answering, which I'll explain in a minute, there also you will require an encoder and a decoder. So fundamentally, that's how these three things are split. And that's why you see this tree as well, taking a split like that. So encoder only, encoder, decoder, decoder only. That's how this is split. Some of the more nuance of how each one can be used for the others, I will explain in a few moments, because you also will have to naturally grow into it. I'll explain that in a few minutes. See, here's an example, right, of loading a new model, right? So for example, if you want to load any of the existing model, right? Let's take, for example, this particular model, right? Distill, BERT, base, uncased, fine-tuned, SST, English. Let's actually go take a look at this particular model on the Hugging Face library. Okay, so this is the model that I just spoke about. So model description, this model is a fine-tuned checkpoint of Distill, BERT, base, uncased, fine-tuned on SST2, which is a dataset, by the way. This model reaches an accuracy of 91.3. What are the tasks you can use this particular model for? You can do some kind of a classification using a model like this. Right? You could perform any kind of a classification using a model like this. So the question is, how can you do that? So here's the piece of code that they've provided for all of us to access, right? Let me actually go back here. Let me show you how you could do it. So I'm loading something called as auto model, which is like a wrapper, right? And I'm saying, hey, I want this model. And then I'm saying model is equal to auto model dot from pre-trained. So I'm saying, hey, fetch this particular model for me. Fetch this as a pre-trained model for me. Some weights of the model checkpoint were not used while initializing distal BERT. This is expected if you're initializing distal BERT model to checkpoint of a model from another task. This is not expected if you're initializing distal BERT from the checkpoint of a model that you expect to be exactly identical. Doesn't matter. This is a warning more than anything else. But I've loaded this model. Now this model is available. Similarly, just the way I load a model, right? So whenever you are dealing with any kind of these models, right? What you need to understand is you require two things. You read a tokenizer and you require something called as a model. What is a tokenizer? It basically takes a piece of raw text and converts that into input IDs. So the raw text goes into the tokenizer, and the tokenizer token breaks the sentence down and it creates that into a bunch of input IDs, bunch of numbers, right? It's like label encoding. Think of it as label encoding. That's essentially what happens from here to here. Then these input IDs are passed into the model. Internally, embeddings are generated, and it generates predictions for you. It, of course, does not generate the prediction itself. It generates logits, which is basically the output from your, before you pass it into a softmax or a sigmoid, so to say. Right? It generates the predictions. You do some kind of basic post processing, and it generates the predictions for you. So you need three fundamental steps. Step number one is a tokenizer. Step number two is a model. Step number three is post processing, right? If you just look at tokenization itself, if you fundamentally look at token, and this is all, by the way, for any kind of this is all applicable for accessing any model using your Hugging Face transformers, right? You access any model using it, the process is still the same. So this is a good, so this course is amazing, right? You pass that as a raw text. Yeah. So logits is this. So imagine you have a neural network, okay? And the last layer, let's say you're performing some kind of a classification or whatever, right? So you have a lot of inputs, and then finally you're doing classification. In the last layer, typically if you're doing a multi-class classification, what is the activation function that you have on this? What activation would you have if you're doing a multi-class classification? If you're doing a multi-class classification, it is never a sigmoid. It is always a softmax. So if you're doing a binary class classification, you would apply a sigmoid. How does sigmoid work? You take sigmoid as an example, 1 by 1 plus e to the power of minus whatever is the input that comes from here. I'm going to put h2, right? So the whatever input that you get from the previous layer, that's h2, right? Before applying the sigmoid, whatever output you get, this h2, that's a logit, right? So the output before the sigmoid is referred to as a logit. It's the raw output. Then you pass it through some kind of it's a weighted sum from the previous layer. Your activation of the last layer is referred to, not the activation function, but the activated output from the previous layer is essentially referred to as a logit. You put it through a classifier, and you put it through some kind of an activation function and get the probability itself. Just that part is referred to as a logit. Yeah, and so just double clicking a little bit into this tokenization, right? How does this tokenization exactly happen? So you take this sentence, right? This course is amazing. This sentence is broken down. This course is amazing. And then what they do is, you remember when we spoke about encoder decoder, I said, you know what, we add like a start sequence and end sequence tokens. So you see this? This is like a start sequence and this is like an end sequence token, CLS and SEP. I don't know what the CLS is supposed to even stand for. I think it's a carriage line return, that kind of a thing or whatever. I don't even know what that is. SEP is a separation, like some kind of a separator. Exactly. It is like EOS and SOS and EOS. start of the sentence and end of sentence tokens. So 2 extra tokens are added. Of course, these tokens also have a default ID. So 102, this is 101, and this is 102, and all the other numbers get the token ID. Right? These IDs are static IDs that are being maintained at the back. Right? These IDs, all of these IDs that you're seeing, they are static IDs. So these static IDs, of course, have their own associated embeddings. These IDs have their own associated embeddings. That embeddings will come later, right? So then once you get these IDs, those embeddings will be created against each of these. All of that put together is then going to be passed into the model itself. Every ID is unique to that particular word. Every word has a specific ID, and every ID has its own embedding. So what are we doing here? Let's go back here. Let's see exactly how this works. So let's say we want to perform a simple, by the way, this particular model is trained on for the sentiment classification. I can pass it for any kind of a base. The default use of this particular model is for a sentiment classification, right? So I'm using this default model for a simple straightforward sentiment classification kind of a setup. Okay, but let's exactly understand what happens inside. So here are 2 sentences that I'm passing. I've been waiting for the Hugging Face course the whole life. I hate this so much. Right? There are 2 sentences. I pass these raw inputs into the tokenizer. Right, the tokenizer I've also loaded. As I said, I need 2 things. I need the model. I need the tokenizer. So I'm also loading the tokenizer here, but I'm using the auto tokenizer class. To load the model, I'm using the auto model class. To load the tokenizer, I'm using the auto tokenizer class. I'm just passing this as the key checkpoint, and it is loading the respective tokenizer and the respective model for me behind the scenes. It has loaded it and it has kept it in memory for me right now. Now, what I'm asking it to do is I'm saying, look, take these sentences. Let's actually put it through the tokenization and let's see what happens, what comes out as an output. So if you observe, it has taken this sentence, it has broken it down, it has taken this sentence and it has also broken it down. Let's take the second sentence. Let's take this sentence. And it has also padded it for me, right? And wherever the sentence size is large, it would also truncate it, right? And it returns it as a PyTorch tensor. In this case, it returns it as a PyTorch tensor. PT is PyTorch. So wherever the length of the sentence is not enough, it will pad it with zeros. Remember padding from computer vision? Same concept here as well. It will pad it with zeros. Wherever the sentence length is larger, it will also truncate it wherever required. So this sentence is a large sentence, which is why it did not have to truncate. The first one is 101, the last one is 102. Here as well. First one 101, this is 102, and all of these are zeros, basically indicating that this is padding. And then I also have something called as an attention mask here, basically saying on what should it actually compute the attention. Yeah, so there is a default length. The tokenizer has a default length, right? So if the length of the sentence is large, then it will truncate. If the length of the sentence is short, then it will pad. If the expected sentence length is, let's say, 15, so whatever the length of the sentence is here in this case, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think it is only 15, if I'm not wrong. I don't know why it's 16. But if the expected length of the sentence is 15 tokens, then it's 16. If it is 16 tokens, then after adding all the special characters, if it is 16, then it will keep it. If it is less than 16, it will remove the additional characters. If it is more than 16, it will remove the characters. If it is less than 16, then it will add zeros, because I want both the sentences to have the same length. No, I don't want the sentences to have different lengths as inputs. Else I cannot club them as matrices. That's it. So I take these inputs, whatever inputs I get, I pass them into the model, I get these out, I get these as the final inputs. I get these input IDs and I get the mask. The mask is just to say on which word should I compute the attention. These are paddings, no? It makes no sense for me to compute any kind of attention on top of these words. I should just compute it on these words and these. So which is why for the first one, I have ones for everything. For the second one, I just have ones on until wherever the words are there. For everything else, it is 0. Basically to say that don't use these words to compute attention. Computing attention on padding makes no sense. That's why. Okay. And what I simply do is I take these inputs and I simply pass it into the output, into the model. The model generates the output for me. It's saying it generated the output for me in this particular case. This is, of course, for the last hidden state, but it has generated the output for me in this particular case. The vector output for the transformer model is usually large. It generally has 3 dimensions, as you can see here. Batch size, as you can see here, 2 units. Sequence length, the length of the numerical representation of the sequence, 16 in our example. In this particular case, it is 16. And hidden size, the vector dimension of each model input. So the model has generated the attention output for each input. For each of these input words, it has generated an output. So 768 dimensions is what it has generated. So 2 by 16 by 768 is what it has generated as an output. So this is high dimensional. It's a high dimensional vector, but it is a rich attention output is what it has. What we can then use is we can use that for any of the other downstream classification models or any of the steps that I want. Like in this case, right? I can use that model. As you can see here, auto model for sequence classification. I'm specifically saying, hey, I want to do sequence classification here. And then I'm passing this model, passing these inputs, and it is simply generating an output for me. And I can simply pre-process it, post-process it rather. I'm applying a simple softmax on top of it. Model, pass the model into the, use the model, generated the predictions. You see these predictions here. I passed it into a softmax layer. Once I get the softmax layer, first one is for 0.004 and the second one is 0.99. So here's the thing. I have the sentence, right? I have 2 sentences. Probability of class 0, probability of class 1. Probability of class 0, probability of class 1. 2 sentences. For each sentence, I have probability of class 0, 1, 0, 1. So what I'm going to show you right now is, I don't want to go here, but what I actually want to show you is the second part, which is the output logic values. Can I explain? Okay, great. So take a look at this. So the model has been generated. So remember, so I have 2 input sentences. So here's what's happening, guys. So let me try and make it very super simple for all of you to understand. So I have an input sentence, sentence 1 and sentence 2, 2 sentences. These sentences, raw sentences, step 2, they've been tokenized, right? And they've been, when they go through a tokenizer, they actually become proper outputs, right? So that will generate an output matrix of 2 by 16 by 768. It'll generate a matrix of size 2 by 16 by 768. This is output from tokenization. Tokenization and embeddings. Actually, let me just make a small change here. This 2 by 16 is the output from tokenization. Then these 2 by 16, essentially meaning 2 rows and 16 input IDs each, right, is essentially passed as an input into the model. Once you pass it into the model, what does the model do? The model generates 768 embeddings, or each embedding for each of these units is essentially generated as an output, right? The model has generated. So if you take one sentence, right, word 1, word 2, word 1, word 2, word 3, all the way up until word 7, word 16. For each one, you now have a 768 long vector. Exactly. You have a word embedding for each of these different words. That's essentially what you have that's coming out as a model. Now, what do? You take these embeddings, right? You take this particular embedding, you put it through one more layer, right? You put it through one specific layer. Now, you typically call that as a task specific layer. You take this particular thing. Now, what is this task specific layer? So for example, you want to perform, let's say, a binary class classification. So what do? You take this and then you add basically one more you add one more layer over here, which then performs the binary class classification. So when you do a binary class classification, this 16 by 768 will return what? For each one, you will return two predictions as the output. Probability of class 0, probability of class 1. By default, it does not generate a softmax or a probability, right? So for that, you need to add a last layer, which is of a softmax, which will basically again give you a size of 2 by 2, but that will then finally give you probabilities. That's the difference, guys. That's step by step for you. These are the four substeps over here. If you choose when you go with this auto model for sequence classification, you're not loading a default auto model, but you're loading that model for sequence classification. So you don't need to apply any specific last layer computations here. You don't need to do any kind of you don't need to take the embeddings and again further pass it into another layer. The output itself will be directly logits because it is already performing against a particular task itself for you. That's the only difference here. But if you load the default model, which is the default auto tokenizer, just the default auto model, then in that case, you will get the raw outputs and then you'll have to take these raw outputs and then perform further one more layer of classification. This is the default model, which will retrieve the hidden states. But if you want to do for sequence classification, for token classification, for question answering, you have the same auto model for sequence classification, auto model for token classification, and so on and so forth. So instead of if you simply use auto model for token classification, it will not generate embeddings for you as an output, but it will generate the classification output itself as the final output. That's the only difference, my friends. Suppose instead of sentiment, if I want the prediction to say red, amber, green, can the pre-trained BERT model still work, or will I have to be trained on specific data? You can use for zero-shot classification, Suraj. You could do zero-shot classification here, or you could also do few-shot. The point is, you could do this. Take a sentence and predict it as this. Either you could do this, or if you want to train, you can fine-tune the model. You have a few examples, you can fine-tune it, right? You can take this particular model and you can fine-tune it. You can say auto model for sequence classification. You can take this model and then you can fine-tune it. There is a fine-tuning class that is available and you can fine-tune that particular model as well for your specific data set. You could do that too. Let me show you one more example, guys. One last example, but in this particular case, I want to show you a question answering model. Actually, let's create it. No, what's the big deal about it? File, new file, Jupyter Notebook, PyTorch. So what we're going to be doing right now is let's take one of these models. Let's actually go here. Let's go to models. Okay. My task here is I want to create a question answering model, right? Where is question answering? Computer vision, sorry, this is here. Natural language processing, question answering, fantastic. So I want to use any of these models. Let's actually use the BERT model itself. Let's use this model itself. My objective is to be able to create a model which can take a piece of context like this as an input, which takes this particular text as an input or question as an input and answers this question from this particular question from this particular piece of context. That's my objective here. Okay. So the question is, how can I create a model like this? How do I access, or rather, how do I create a simple model like this particular thing? Now, for me to be able to do that, of course, I would of course require to load this model, right? Whatever that particular model is. What I want to quickly also show you all here, let me just come back here. What I also want to quickly show you all in this case is this particular model. By the way, this kind of an approach, there's a data set called Squad dataset, right? The Stanford question answering dataset. So this is, by the way, the BERT model was fine-tuned on this Squad dataset. What is the Squad dataset? Let's quickly take a look at it. The Squad dataset is basically like a reading comprehension dataset, right? So you all must be familiar with the reading comprehension example, right? So reading comprehension is simply nothing but You have reading comprehension is simply nothing but you, let's say, let's take any of this packet switching as a piece of text. So you have a paragraph, and then you have somebody asking a question, and actually humans responding back to this particular question. This ground truth is nothing but somebody, there was a crowdsourced. So somebody was actually manually trying to respond back to these questions here. And then you also have something called as a prediction, which is essentially a prediction from this model, the NL net. So somebody actually made a prediction, and that prediction is what we are seeing. So you see, these are all different models: BiDAF, self-attention, BERT, single model. So if you go to packet switching, so these are the predictions from the BERT model, and so on and so forth. Right? Some of them it got right, some of them it partially got right, some of them it did not get right, and so on and so forth. So as you can see, this is how the dataset looks like. So the task is for you to use, or whoever is building this kind of a model, their task is to basically take any of the existing transformer models and then fine tune it on this, so that you could do tasks like these, where you pass a piece of context or a passage, you ask a question, and you ask it to answer that particular question given that particular context. That process is referred to as question answering. That is the whole idea of question answering, or this is also shortly referred to as machine comprehension. Instead of reading comprehension, you could also refer to this as machine comprehension. That's how this whole thing works, right? Now, what we're going to be doing is we're going to be using one of these fine-tuned models, and then we'll try and create an inferencing layer in our notebooks, right? At our end, we'll try to quickly see if we can create a small inferencing piece of function using one of these models in our notebooks, right? So that is essentially what we'll be doing. So that now what we will be able to do is we can pass any context, any piece of text, and we'll be able to generate our own response from this particular context. That is what we'll be setting up in our notebooks for in the next few minutes. So we'll be discussing as I said, we'll sort of be doing a question answering example here, using some of the stuff that we just saw. Right, I think a lot of these things are pretty straightforward. We could use some of these different topics that we just learned. Right, we can try to do question answering using the question answering pipeline, or we could also do it using this auto model uh, for question answering sort of a setup as well. You could do either of these. Let's quickly do it using the pipeline object, right? So from transformers import pipeline, and we simply say pipeline is equal to pipeline of the task is question answering. I hope it's with the hyphen or with an underscore hyphen. And then here, I would also want to provide the model. And the model here is, in this particular case, what is the name of the model? Let's go back to the model itself. Okay, not this. This is the Google BERT, right? So question answering, we wanted to do this one. So let's copy the name. All right. And once that gets loaded, which should basically be any moment, what we could then do is we could simply say PPL, which is nothing but the sorry. Let's actually take a look at what are the inputs that need to go into this. So the inputs that are essentially being passed here are, just trying to find the exact piece. Right. So the two things that should ideally go as an input into both of these are, let's go back here once again, is the context. It's the question and the context. There are two parameters that need to go in. Let me go back here again. So the inputs that need to go into this are, let's say, the question and the context. So the inputs that need to go into this are, let's say, the question and the context. There are two parameters that need to go in. Let me go back here again. So let me go back here again. So So there has to be a question, and then there has to be a context. The context is essentially a piece of text that I will be using to answer that particular question itself. Right? And the question is the actual question that I want to respond back. So let's pick any Wikipedia article. Right? Let's go. Let's look at I don't know, guys. Let's pick anyone. Let's go. Let's pick any article. All right, from today's featured article. Let's read about it. I have no clue what this is. Jersey Act was introduced to prevent registration of most American-bred thoroughbred horses in the British General Stud Book. There's a lot of information here. And the loss of breeding records during the American Civil War. Actually, let's go here. Let's add it. I have no clue what this is even supposed to mean, but I'm going to ask, what is Jersey Act? That's my simple question. And I'm going to say PPL of question is equal to question, context is equal to context, and I'm going to say result. Let's execute. Let's see what happens with this. What I'm expecting is this particular model tries to answer that particular question from the context that I shared here. And let's look at the result itself. Yeah, here you go. The answer is to prevent the registration of most American-bred thoroughbred horses. That's not bad. That's a decent answer. I mean, I wouldn't consider that to be a perfect answer, but it's a decent answer, I would say. Here's the point where I want to call out one specific aspect, right? What do I mean by it? So there are two kinds of question answering that happen. So when you talk about question answering, there are two kinds of question answering. First one is called as extractive question answering, and the second category is generative question answering. What is the difference between the two? In the case of an extractive question answering, what you're simply doing is you're basically taking a piece of text and you're trying to answer that particular piece of text from the existing context that is available only by extracting the relevant words, right? So what do we mean by it? In the case of extractive question answering, you essentially try to find a piece of the answer in the existing sentence, right? It would say, as you can see here, it has predicted the start and the end. So it says the start is the 31st character and the end is the 100th character. So you go from left to right, you find the 31st character, you start there and you go all the way up until the 100th character, and then you simply stop there. That's essentially what you mean by extractive question answering. So you're essentially extracting a part of the existing context that you have provided. There is the other category of question answering, which is called generative question answering, wherein you are not trying to respond back from a particular question by respond back to a particular question by extracting the response, but rather by looking at the complete question, looking at the complete piece of text and coming up with your own version of the answer. It may or may not exactly be present in the context, but you're essentially actually creating an answer in that particular case. That is referred to as a generative question answering. Now, what does that translate to? In our world, what it should translate to is what sort of goes into an extractive question answering and a generative question answering. In an extractive question answering, you are just, as I said, just trying to find the start and the end of a particular set of that response, right? Or other ways put, you try to find the start and then you try to predict all the way up until the end. That's how basically question answering works. You try to predict where the answer might start and then go all the way till the end. So in a lot of ways, you're simply predicting the start and the end. That's all that you're predicting for. You're predicting the start token and the end token. That's what you're predicting for in the case of extractive question answering. However, in the case of generative question answering, you actually use the complete encoder decoder architecture You use the complete encoder decoder architecture. You pass the question, you pass the context, both of them together as an input, right? Generate the embedding, pass the embedding, and then you pass start of sequence as a token. And now you start emitting one word after the other, one word after the other, until you actually create the final response. So here in this particular case, you're actually going through the complete encoder decoder setup. However, in the case of extractive question answering, you don't need the decoder. You just need the encoder. You just need the encoder part of the transformer. Why? You just pass a piece of text and the context is an input, and all that you're predicting here, you're not predicting words. You're just predicting the start token and the end token. That's all that you're predicting for. You're predicting for the start token and the end token. So in this case, just an encoder is enough. You don't need a decoder. In the case of a generative question answering, you need the encoder and the decoder both, which is why it is a lot more like the way you solve it is very different, which is why the kind of quality of the response is also very, very different. This is referred to as whatever we just did is an extractive question answering sort of an example. All right, which is why also if you see here the encoder model here, if you see the encoder model, it says extractive question answering. Encoder, decoder together can do generative question answering for you. Right. So back again, let's go back to this. So now at least you know, given a particular piece of information or given a particular piece of the context, you know how to do question answering, but at least the extractive question answering we know how to do. This, of course, we are using the pipeline object. If you did not use the pipeline object, right? If you did not use this pipeline method here, let me show you how the code looks like. Right? Let's actually look at how the code will look like if you did not have that. So had you not done this, okay, what you would have had to do is you would have had to do from transformers, or rather import auto model for question answering. And from there, you would have, of course, had to also do from tokenizers, import auto model for auto tokenizer for question answering. Why is that the case? The package is not available. Did I make a error somewhere? No, I just want to do it specifically for question answering. Okay, sorry, this is my bad. Okay, cool. From tokenizers, import auto tokenizer. Hey, why is this not reading? Just a second. Yeah, that's another thing. Okay, and then you simply go. The model is the same. This is the checkpoint is the same, and then you say, so the model is going to be auto model for question answering dot from pre-trained, and then you simply pass checkpoint, which is the model, and then you say tokenizer is equal to auto tokenizer dot from pre-trained of CKPT, which is basically both of them. The models will be loaded right now. And once the models are loaded, of course, I can then take it one step further. I can use both the question and the context. I'll use the same question and the context here. And now simply going to say, hey, look, the inputs are going to be tokenizer of, remember this is the tokenizer. So question comma text, I need to pass both of these. Return tensors is going to be, let's see if it can return a numpy. Sorry, this is context. This is not text. Let me stop this. And let's go. Let's execute this. This will take a couple of seconds for it to get executed. All right, perfect. So now this has been executed. Let's quickly go to the inputs. let's see. So my inputs are now been created. So if you just look at, this is, by the way, the NumPy arrays of, actually, let me just go back to PyTorch. I think it returned it as NumPy arrays. So let me just return it as PyTorch so that I can then pass it into the model itself. So now if you look at the inputs have now been returned with this is nothing but, so if you see here, if you look at the tensor, it has, you see the 101 all the way up until 102, but I'll just quickly highlight one part wherein you see a quick difference. See, look at this. So 101 all the way till 102, and then you have the rest of the same thing all the way up until 102. Why is that the case? So the 101 all the way up until 102, this is the question. That's the question. And from there, this is the response. Or rather, this is the context. So both of them are sort of combined together. So if you see, which is why if you see something called as token type IDs, right? If you see the token type IDs, there are a few zeros and then the rest are ones. The zeros are nothing but your questions. The ones are the context. So it is a way to tell your model that, look, when you generate the response, only generate the response against the ones. Don't generate the response against the zeros. These IDs are predefined. I can actually show that to you as well. These are the IDs that the model actually bears with it. Let me actually show that also to you. You can say tokenizer dot convert IDs to tokens. So what you could do is you can take these IDs. So this particular tokenizer, my friends, is a very, very specific tokenizer for this model alone. Remember that this BERT model is a large model. It has been trained on massive corpus of data, right? It has been trained on a lot of data in the past. Google News, this and that. It's been trained on a lot of the corpus. So what you could possibly do is you could simply, take these IDs. Sorry, input inputs of input IDs. So you see these IDs. I can actually pass these input IDs as tokens here, and I can ask it to generate the whole thing. Okay. Let me try to pass this. See, there you go. The moment I pass these tokens into, I pass these exact tokens back into this function called convert IDs to tokens. Look what it has done. It has actually given me how the sentence has been broken. What is Jersey Act question? So each of this is a token separator. The Jersey Act was introduced to prevent the registration of most American bred thoroughbred horses in the blah blah blah, and so on and so forth. So this is how it has actually been tokenized. And these words, my friends, are exactly the same words that would have been also tagged against these IDs when the model was first trained on its large data set. The model would have been trained on a very large data set, right? So it would have been trained against a particular set of IDs. Every word would have been mapped against a particular ID. All of those are going to be here. In certain cases, what may happen, there might be words here that might not have been seen otherwise, right? In such cases, they will all be tagged as something completely random. So for example, if I say, if I have a sentence like that, now let's see what happens. Either this should get broken down into individual tokens, that if the tokenizer is smart, or it would simply tag it to something random, which I would guess it should. Now see what it has done. It has taken that particular sentence or that particular token, and it has actually broken that particular token down into smaller tokens. Because the tokenizer doesn't recognize this particular word. What it has done is it said, okay, I don't recognize this word. the tokenizer has this functionality of also trying to break that particular token down or that particular word down into the nearest tokens that it might have seen in the past, that it may have seen in the past. So that it can at least match for some similarity there in that case. Instead of simply saying, "Oh, I don't know what this word is." Does that make sense to you? Is this clear, everyone? Cool, fantastic. Now that you know how the tokenizer works here, now that you know how the tokenizer has created all the tokenizer and all of the IDs, what do you do then? You take the inputs and then what do? You pass it into the model. Right? So you say, hey, no, first you need to generate the output. Right? So output is equal to model of star star inputs. How many ever inputs you have. In this case, it's only one input, but I'm just passing it anyways. So now if you look at the outputs, so look what the output has created. So question answering model output, start logits. So now if you observe, it has given me logits for the start and the end logits. So if it has given me start token logits and it has given me end token logits, basically I need to then find of these the one that has the highest logit and then work from there. Does that make sense to you? Everyone, do you understand? So from here, I need to find, okay, the logit that has the highest value, highest logit, that would become my start. And the logit that becomes my end, that would become my end. Then I need to use both of these and stitch the answer together. Let me show this to you quickly. Let me quickly show you. By the way, I'll just remove this. I don't want to confuse the model. Okay. So now let me generate the output. So I have the outputs. So let me show you what we'll do from here. So now what I'm going to do is I'm going to say output of, I think, start logits. So you see the start logits, it's a tensor, right? And from here, I'm going to say, let me just import NumPy or PyTorch also should work, but okay, this is the start logits. Okay. Let me just say with no grad. No grad. Sorry, guys. So the torch no grad is essentially a way to say that, hey, I don't need these tensors to go through any more gradient computations. Especially when you're doing inferencing, you don't need to do that. Now it'll just get converted into a NumPy array. So from here, or I can also do a simple argmax. So it says, hey, it's the 12th tensor. It's the 12th token that has the highest value in this case. That's the one. Similarly, the end logits. It's the 28th one. So the start is the 12th and the end is the 28th. And all that I need to do now is I sort of will have to simply, all that I have to do is I simply will have to, run through the, run through the input IDs and then go one after the other. Right? So I'll have to simply say, where did this go? This is the start index. This is the end index. Right? And all that I need to do now, I simply will have to say whatever inputs I have, which is nothing but this of input IDs. These are my input IDs, right? All that I need to get the start index all the way up until the end index, right? I need to go from the start index all the way up until the end index plus one so that I also cover that part. What is the start index and the end index? Oh, okay. There you go. That's it. That's the response. I need to get the 0 because without that, it was indexing the other one. So that's it. These are the tokens, right? So these are the output tokens. These are the response or rather output IDs are these. And what do I need to do? I need to put these output IDs through this function. Remember this one. All that I need to do is I just need to do that. That's it. There you go. That's the response. So I can simply say that's the response. You would have had to do all of this, or you could just use this, or you could just do this. Right. So this is method one, whatever you saw here. Right. Or this is method two using this and this. You could use anything that you are comfortable with, anything that you would want to use. That's totally up to you. Your choice, of course. You could either use the auto model for question answering and auto tokenizer, generate the predictions. This would give you a little more clarity exactly what you're doing. You'll have to do all of this extra stuff, which is sort of indexing, extracting, and all of that. But this is also actually not a bad idea because it might also be a good exercise for you all, to exactly see what goes first, what goes next, and so on. Or you could just use the pipeline object, and pipeline will take care of all of that under the hoods. That's the beauty of the pipeline object. The pipeline object will take care of nicely putting all of this for you together. So this is so much more simpler that way. Cool. So congratulations. So that's how you go about doing any kind of question answering using the BERT model. Or I mean, question answering is just one task. You could basically follow the same approach for any other task that you wish to. Okay. Now that we understand all of this, let's go one step further. So this is great, right? I mean, everything was nice and rosy. All yeah, don't worry, guys. I'll provide all the code that I have. So do not worry about that at all. I'll definitely share all of it. Now, so what now, right? So this is great. overflowing from your mind. Yeah, sure. uh, cool. I'll share this as well anyways. So don't worry about it. Now, this is all great. Now what, right? So let me just open this. So we understand how transformer models work. We've tried out these transformer models through through the Hugging Face interface. Now the next part, which is, this is all great. What suddenly happened, right? So this was nice. There was still some skin in the game for data scientists here until this particular point. But now what happened after this completely threw the data scientist under the bus, right? So it simply said, look, man, we don't need you anymore. Um, because these models have now suddenly become they have suddenly become extremely powerful. So what happened there? What happened was that large language models suddenly came into existence. So people realized that these transformer models had a lot more to offer, right? So they simply just did not stop there. They of course said, okay, let's use the same encoder decoder architecture, right? So the same encoder decoder architecture. Let's take the same models. So the same transformer models with attention. Let's actually pump in more and more and more data to it, right? So they started pumping in more and more, and to their surprise, these models started getting better and better and better. They just started getting so good that more data simply meant better models, right? That is where that took us to this very interesting space called large language models, right? So then instead of just 330 million parameters, 250 million parameter models, you suddenly started to see 7 billion parameter models, right? You suddenly started to 7 billion, 8 billion, right? The number of parameters just suddenly shot up. And that's where things started to become super interesting. Why? Because these models have now pretty much become like, they've become so good that they understand languages like never before, right? Even better than, let's say, these BERT models, so to say. The BERT models were good. There's nothing wrong with it. The BERT models were very good. The GV2 models were fine. But the beauty of the transformer architectures just made these models so much better, moving into moving into the next area. So now what all of these folks started doing is they, be it uh, the OpenAIs of the world or the Googles of the world or the Metas of the world, they started training larger and larger and larger and larger models. That's where we started to see this whole new branch come through called as these large language models. Now, to be very honest, large language models are just another part of transformer architectures. It's just another transformer model. But what but the way they've been trained, these large language models suddenly starting from the launch of GPT-3, uh, or rather, to be more precise, Chat GPT, so to say. Since the launch of Chat GPT, the world was taken by a storm, right? So this was in November 2022, was when November, December 2022, it was when this particular thing happened. Chat GPT was launched. Within no time, people started to use this capability, and it saw like this insane adoption in terms of usage. Everybody started using it. The model started to become better and better, and the way they OpenAI sort of set it up was also very interesting. They kind of set it up in a way that the more the people started using it, the model actually started to get better and better. So what is it that these guys have done? Right? Let's take specifically the case of, let's say, a Chat GPT. What have these guys done which is significantly different from that of, let's say, any other transformer model? Is it the model itself that has changed, or has there anything been different, or have these guys approached this whole setup very differently? The answer is actually the latter. Right? The model has not significantly changed. Of course, they've trained it with large volumes of data. We still, to be very honest, don't know how the models powering chat GPTs were trained. We still have no clue, right? We still have no idea how a GPT 3.5 was trained. We still have no clue how, let's say, a GPT-4 is trained, but we know broadly how the setup sort of looked like, right? Let me actually bring up the one of the slides that was presented by the person who had trained the GPT 3.5 models. Let me actually bring that up. Uh, okay, so let me start with how uh, you know some of these models are trained, right? The size of these models, right? Size of the data that sort of goes into this. This is like a good example of how one of these models was trained. Let me just this is actually not the GPT model, this is actually the llama model, but still you get an idea of broadly how they're trained. So this is common crawl. Common crawl, for all you know, is like a yeah, common crawl is basically like a very popular is like a publicly available scrape of the internet, right? It's like a crawling engine that was built by some very normal very noble folks out there who wanted to make data available for everybody to access. So this is, by the way, Common Crawl. It's an open repository of all the web crawl data that can be used by anyone. So you and I, anyone can download this data. You can use it for whatever you want. It's for your consumption, right? This is a data set that is available since 2007. And it's crazy, right? The amount of data that's available, it's sort of crazy over here. So if you look at statistics, just for you to understand how big this data is, let's actually go. Yeah, so if you look at the size here, I wanted to show you one particular part, which is the size actually. Yeah, I just want to show you the size. But anyway, actually we can actually see it here as well. That doesn't matter. Let's actually come back here. So if you look at this, so almost 3.3 terabytes of data is what we are talking about. That's how big this data set is. For training and learning, isn't data sets in Kaggle enough? No, man. I mean, this is just to let you know, right? So the Common Crawl database is 3.3 terabytes. This is the whole of the internet, publicly available internet. It's as big as that, right? And of course, there is no way you and I can use any of that data on your machines, right? 3.3 terabytes, right? And then there is bunch of others. GitHub code 328 GB, right? All of the publicly available GitHub. Wikipedia 83 GB. Wikipedia is as small as that. Stack Exchange, right? So your archive, which is nothing but your publicly available papers, 92 GB. Books, 85 GB worth of books, and so on and so forth. So if you actually take all of this data, this is massive. So a good 67% of the model has been trained on almost all of the internet, right? And if you look at the number of epochs, which means that the model has barely seen all of this data once. GitHub barely seen 0.6. Only 64% of this complete data has actually been used during training, right? So Wikipedia, books, and so on and so forth. The model actually hasn't even seen all of this data, or maybe has barely seen some of this data at least once. So the point is, that's how big of a data are these guys using to train these models. So imagine it's way beyond your and my from an accessibility standpoint, is just you have the access to this data, but it's just impossible. I mean, the amount of resources that is required to train something like this is crazy. That's how much data you really need to be able to train these models. And the beauty is the large language models or the transformer architectures are actually able to consume so much amount of data and give out something extremely good. So that's the more interesting part here. It's not to say that the model is You're just pumping in so much data. The model is actually able to also consume so much data and extract some very, very valuable insight out of it. And then people have started to make some very interesting changes to this particular model. What have they done? So, what they've done is here, the first to start with, right? Uh, this pre-training is like your regular model pre-training, right? So language modeling, predicting the next token. So the raw internet was taken, basically everything that you see on the left side, all of this information was taken. That information was passed into the model to predict the next word or the next token. That way you were able to build the base model using a regular transformer architecture. Of course, this is the GPT setup, and these guys may have used something very, very specific that you and I probably don't know. They might have come up with some innovations, some inventions under the hoods that you and I probably don't know, and that's okay. Broadly, it is still the transformer architecture, that much we know. Then what they've done is, to be able to train this model itself, they required like thousands of GPUs, months of training. And this is basically all of your GPT models, your Llama models, Palm models. They're all basically the same category of models, so to say. Right? That's essentially the pre-training part of it. Then comes the second part, which is the supervised fine-tuning. Now, when we access the BERT model, my friends, right, that is essentially this part. That is essentially just this part, right? We just had access to this particular model. Nothing, we did not have to do anything beyond this. What now people started to do is they started to not just stop here, right? But they started to take it one step further. What they started to do is they started to now train this particular model on something called as an instruction set, right? Now what they've started to ideal assistant responses. So now they started to say, hey, look, given a particular question, what is the ideal response that I'm looking at? Remember, in the first go on the left side, the model was simply pre-trained to predict the next token. That's it. It was not doing anything else. But here in the supervised fine tuning to assess how good the model is, because you always have the raw data. You have this sentence. If I am trying to predict, given all of this, if I'm trying to predict this next word, I can predict and I can always compare, right? Because all of that data is already available. So it's not that complex for me to predict the next token and compare. But the complexity sort of kicks in here, right? Where you need ideal assistant responses. So what they started to do is they started to create questions, or rather prompts, right? And associated responses to these prompts, right? And they're saying, hey, given this particular prompt, this is the best quality response that I'm looking at. This is the ideal response that I'm looking at, like an assistant. And as you can imagine, this information has to be manually written, right? So nobody might have this. Somebody has to actually curate these responses. So as you can see, written by contractors, low quantity, high quality. So they're actually fewer in number, but they were written by specialists. They're fewer in number, but they're very, very high in quality. This is to tell the model how it needs to respond back as an assistant. So that is what happened here. So they used that and they then further used that to further train this particular model. So this part is done. So you train the raw model using all of the internet. Here you have trained it to do something very, very specific. So you fine tune that model to do something very specific. So until here, it is the regular BERT like model. It is until here, it is regular GPT like model. Nothing changed, nothing different here. But here is where things started to get better, right? Now from here, what they started to do is they started to do something called as reward modeling, right? Again, 100,000, 1 million comparisons written by contractors, low quantity, high quality. What they now started to do is they started to evaluate all the responses that are given by the model, if they're good or bad. So the thumbs up, thumbs down, you might have seen on the chat GPT thing, the thumbs up, thumbs down. Before they even actually put it out there, they started to do it themselves internally with a lot of contractors. So they can predict, given any particular response, or they can actually predict, given a particular response, is this actually good or bad? Right? Is the response actually good or bad? Given the question, they're trying to predict, is it actually good or bad, good or bad, good or bad, and so on and so forth. Right? If it is good, they went ahead. If it is not good, of course, they further went back and they fine-tuned. Then comes the last part, wherein the reinforcement learning sort of then kicked in. What is the last part of reinforcement learning? This is where, again, now that I know that the response is good or bad, can I actually go back and adjust my response to make the response better? So that is referred to as reinforcement learning, RLHF, reinforcement learning based on human feedback, right? So it learned a reward function. It learned that, you know what, if I do this, then it is good. If I do this, it is bad. Now the model knows that given a particular question and a response, as a user, would the user like it or not? Right now, I've trained a specific model just to learn that part. Right now, what I can do is I can adjust this response in such a way that I can make this always great. I can always get this response well. So I need to solve for a specific sort of an optimization problem, given a particular prompt and a response. How do I ensure that I always get a thumbs up? So I need to keep adjusting this response time and time again. That, my friends, is reinforcement learning. It's basically like, imagine I give you a car, right? And you put a foot on the pedal. The person sitting next to you, who's your instructor, says, "Oh, great job." You suddenly see an obstacle, you turn left, great job. You suddenly see a cat, you don't press the foot on the you instead of braking, you press the foot on the pedal and you actually accelerate. The cat dies and the guys on the instructor on the left side gives you one smack at the back and says, "Man, look, you've created an error here." So now you've learned, because you, with the smack on the back, you've learned that, oh, you know what, I'm not supposed to do this. So the next time you see a cat, you again turn left. So now you get a thumbs up again. So your head, you're actually trying to course correct and trying to always make the right choice given a certain circumstance. The circumstance here is the prompt and the response. And you're always trying to adjust the response in such a way that you always get a thumbs up, right? So that, my friends, is the last part, which is the reinforcement learning part. Now, before they could actually even put this thing out for the users to use, for the end users to use, they would have had to do this internally. So at that time, there was probably no human feedback. The human feedback part wasn't there. It was just reinforcement learning because they did it they would have done it internally. But once they put it out, as people started to interact more and more, then they introduced the human feedback part, because then they said, you know what, you like the response, give me a thumbs up or a thumbs down. Because the moment I get that information, I can always improve this reward function and I can always improve my reinforcement learning. So both of these steps will improve over a period of time, will get more and more customized over a period of time. So, and also just to let you know, right, this part is very specific to how I would want to see the response, right? This is very much for the chat interface. This is not very much for the, if you think about it, this is not so much about this is not so much about the underlying model itself and its understanding about the language. This is more about, okay, how do I want the response to exactly be? So this is very similar. So this is also referred to as instruction training, right? This is also called as instruction training because you're kind of training it for specific instruction. You're training the model to respond back in a certain way for a given set of instructions. That's basically how the GPT models work. So this is a very, very common process. Whatever you're seeing on the screen is a very, very straightforward, common sort of a process where to train a model like GPT, you typically will go through a bunch of different steps. In this particular case, these are 4 steps. Just to let you know, we still exactly don't know how a GPT model is actually trained, right? Let's say how a GPT, any of the GPT-4 models, how are they actually trained? We still have no clue. But one of the researchers had actually given a talk about this. And then it was actually in one of those presentations where he spoke about how the GPT models are actually trained behind the scenes. It's more like sneak peek, a 1,000 feet view of exactly what's happening. We don't really know the exact detail of what happens under the hoods. What you're seeing on the screen on the left side is the data sets that are typically used, or the type of data that is typically used to train a model like this. And what you see on the right side is essentially the process, how this particular data typically goes through this training. We spoke about the fact that typically these data sources are mostly the internet, right? These data sets, of course, have a lot of they have a lot of information, or rather, they use a lot of data, ranging from almost all of the internet, all of the crawlable internet. There is this data set called as Common Crawl that's available for people to use. What you could do with something like a Common Crawl is you can just download the complete data set. It's around 3.3 terabytes of data. Like what you see here, it's around 3.3 terabytes of data, which, by the way, is a lot of data, right? So the 3.3 terabytes of data is a lot of data. And then it's almost 67% of the data that's typically used for the training process is actually the 3.3 terabytes. And then the remaining 40% is from a bunch of other sources, right? So you have C4, GitHub, Wikipedia, there's a bunch of books. There are these papers from archive. And then you also have Stack Exchange, right? All of this data has been combined together. And then this, by the way, this, apart from Common Crawl, all of this data contributes to the remaining 30%, so to say. So all of this data put together has been trained. Just to let you know, whatever data that you're seeing on the left side is actually for GPT-3. I'm sure they've been pumping in more and more data for GPT-4s and the others, which we can maybe discuss about later. But if you see on the right side, we just spoke about how the GPT training actually works. There are 4 steps in this process, right? What you need to understand is the first step is nothing but your pre-training, your model pre-training. All that you're doing in the model pre-training is basically training it like, let's say, your typical BERT-like training process. What you're doing here is you're taking all of the data from the internet and all of these trillions of tokens, trillions of words, and this information is sort of being passed into a typical language model. And this language model is like your any other transformer model, so to say. And then that transformer model is sort of trained to predict, let's say, the next token. That gives you your base model. That gives you your first base model, so to say. Now, from there on, of course, you require more and more data sets. By the way, this is like the BERT model that you and I have seen a while ago, right? But that's not it, right? So these models are actually also taken one step further, because at the end of the day, you want a chat-like interface, right? As I said, more data means these models actually get better. So they're actually fine-tuned for a bunch of different steps, right? So to start with, there's a bit of a supervised fine-tuning that goes on. You, of course, want these models to behave like a chat interface, right? So you want to provide a chat interface for these capabilities. So that is where things can start to get a little interesting. So what you are able to do here with these chat models, or with the base model, is you are sort of providing an assistant-like persona to this. What do you mean from that? What do you mean by that? We have taken a set of 10,000 to 100,000 questions and responses. Questions is simply nothing but a bunch of instructions, right? A set of instructions. And then there is a response associated to it, right? An ideal response. And this data set is curated by experts, right? Experts have actually curated this particular data, hand curated. And then they take this data and they sort of fine tune this model under the hood. So they are saying, hey, look, whenever you get a question like this, you're expected to return a response like this, right? So you do a bit of supervised fine tuning over here. The idea is for it to be able to predict exactly the same words as these experts have come up with. And then it is trained for, as you can see here, right? It has been trained for a fair amount of time. Once that is done, right? Once it is done, then you know that this model just doesn't only uh, it doesn't only respond to questions, but it also has a bit of a, you're sort of giving it a persona as well. And then after that, you're going two more steps, because just training it once and just leaving it there is not good enough. Because what they've also realized is that, in reality, for these models to actually work or to be useful in real world, it's important to also provide some kind of an interface where you could provide this feedback back to the model, right? So you need some kind of a feedback going back into the model. So what they have done is they've also, in the process, trained a reward model. So they're saying, hey, look, given a particular question and a response, you've trained this model to do that. But in parallel, you've also trained a binary classification model, which basically says, is this model good, or is this response good or not? And they have trained that particular binary model to reward, right? So rewarding essentially means, is it a good response or a bad response, right? Thumbs up, thumbs down, right? They have trained that particular model, because that model will then be useful, or the output of that particular model, the reward model and the actual output put together, you pass it into some kind of a reinforcement learning model, where you tell, hey, look, this is the question, this is the response, and we don't think that this is a good response. So now the model will learn and will try to course correct itself, will automatically try to adjust itself. So that process of reinforcement learning is also known as RLHF, reinforcement learning from human feedback. Now, what you need to understand is this reward modeling exercise during the training process is sort of trying to mimic a human feedback. This is trying to mimic a human feedback. This model by itself is not very useful. This model is only useful during the training process. But when it is actually being in production, when you and I are actually interacting with something like a chat GPT, you give a thumbs up or a thumbs down. The moment you give a thumbs up, that is already saying, you know what, I'm happy with the response. When you give a thumbs down, it says, no, you know what, I'm not happy with the response. So basis that feedback which you will provide, the model will also learn a little better. So this reward modeling is more of a training process than actually a inference process, meaning than actually an actual production sort of a setup process. That's how this has sort of been trained, which is why once you have this model trained, then you have this reinforcement learning and everything set up. Once this is also put in place, these two steps are also put in place, this model is now exposed through the chat interface. Now, let's understand the inferencing pipeline. What exactly happens in the inferencing pipeline? What happens in the inferencing pipeline is you take this model, the model that was supervised, fine-tuned. You take the model that has been fine-tuned model. So I'm going to say, right, any fine-tuned model, right? The fine-tuned model can be a GPT fine-tuned model or whatever. And then you provide an interface, right? So this fine-tuned model, also referred to as a foundational model, which you would very often hear, is exposed through the chat interface, like your chat GPT or anything for that matter. So you ask a question, chat GPT responds, then once basis this particular response that you get, right? Then you provide, hey, am I happy with this or I'm not happy with this? By the way, you providing the happy or not happy is basically reward modeling, because you're actually going to provide the thumbs up or a thumbs down. You don't need to create a model. But when you are training, you don't have the human feedback, which is why you're building a model that gives you that reward model. So this thumbs up, thumbs down, once you say it is happy, great, you don't do anything. If it's not happy, you take the question, you take the response, and you take the fact that, hey, the user is not happy with this. You then take all of this, pass it into the reinforcement learning setup, and then you train the model, you retrain the model. Now, what you need to understand is that this retraining does not happen every time. This retraining is only when required. That's one thing you need to understand. Either you can trigger it, or if you don't have the control, chat GPT will trigger it behind the scenes. It depends on who is governing the model If it's OpenAI that's governing the model, if you're using a public instance of OpenAI, then then the OpenAI folks themselves will decide when to train this particular model, retrain the model. But if it is your own local deployment of ChatGPT, then you can decide when to retrain the model. Maybe you collect, let's say 100 such samples, right? So you've collected 100 such feedback samples, then you take all of that put together, then you pass it back to the reinforcement learning model. And that reinforcement learning model, taking all of the 100 samples of questions, responses, and the feedback, all of that are sent to the model, and the model will then try to learn itself, and it'll come back with hopefully a better model. It's not always guaranteed that you'll have a better model, but you have the flexibility to try and fine tune it. That's how, my friends, the training and the inferencing pipeline of a GPT works. One of the topics that I'd want to talk about here is how open source versus closed source models actually work and their deployment setup. Right. This is a little complicated. This concept is a little complicated. So stick with me for a few minutes. I'll explain how this works. This is extremely important in the sense that, it is extremely important because you need to understand what models to use or how to use these models, and stuff like that, right? So let's talk about this for a few minutes, and then we can go a few steps further. So let's go, right? More often than not, when we talk about these models, one of the things that often keeps coming up is, okay, what's like the best way for us to access these models, and so on and so forth. So first things first, let's talk about what these models really are. So you have, of course, all of these foundational models, or you can, when I say foundational models, I'm talking about your GPT-3, your Llama, whatnot, right? So all of the large language models that are available for anyone to use, right? These are publicly available models. Some of them are owned by a few, some of them are not, are open source. What do I exactly mean by this? So when we refer to a model as open source, what do we exactly mean by it? So when we say an open source model, what I mean by open source is these artifacts, starting from the model architecture, the source code, the data sets, and the trained model. All of this information is publicly available for everyone to use. Right? It's publicly available for anyone and everyone to use. It's open source. What do you mean by that? So a good example is something like a BERT model, or even if you go back, your VGG16 model is also a very good example of this. So you exactly know how to use the VGG16 model. You exactly know how to use the BERT model. You exactly know how the BERT model was built. You exactly know how the VGG16 model was built. You know on what data sets they are built. You actually have the trained model as well. When I say trained model, I'm referring to the pre-trained model, meaning the final trained model. And by the way, when I say a trained model, it's essentially with the weights and biases, right? All the parameters, the trained weights are all available for people to use. What will people do with if something like this is available? Well, they will take this model and they can build newer versions of the same model. They can maybe choose to fine tune it on other models, right? Imagine if I provide you access with all of this information, you can say, you know what? A BERT model was trained on some data sets. I can actually take that model completely and I can use that I can maybe fine tune that particular model for maybe my medical domain, or I can fine tune that particular model for my finance domain, whatever, or maybe on your proprietary data, whatever is available for you. So that is a very, very common use of having all of this publicly available. Now, there are certain challenges with things like these. I'll tell you what these challenges are. Now, when you talk about an open source model, if you take, for example, any of the BERT model or the VGG16 model, the good part about these open source models is that the models, of course, are available for people to use. But how will, let's say, if somebody builds a model, let's say you build a model or I build a model, how do I make it available in the first place, right? How do I make it possible for you to use? So if I ask you, hey, look, I have built my own version of the BERT model. I have done some research and I've built my own version of the BERT model. How do I make it available for people to use? Well, I can use platforms like, I can use something like a Hugging Face. So I can use this particular model on a publicly available platform called, I can put it in a model repository like a Hugging Face. I can say, you know what? I can take this particular model, right? So the model has already been trained and I put it, whatever model I have, right? I put this particular model in the Hugging Face model repo, right? Remember, this Hugging Face is managed by a private company. You need to understand that Hugging Face is a private company, but they have created a community setup. So anybody and everybody, it's a very trusted source. So anybody and everybody can actually come in here and they can access your model. They can take your model, they will get the code, they will get the architecture, they will get basically everything. And what Hugging Face has done beautifully is they have actually built a small library on top of this. What do they call it? They call it the Transformers library for you and I to simply use it through a Python interface, right? As long as you know how to host your model in Hugging Face, right? I can use the Transformers library and I can access any model that anybody has published, right? This is nothing new from what we have already done. That is exactly what we have done. If you look at it, when I use the Transformers library, all that I simply say is, hey, look, I want the BERT large uncased whole word masking fine-tuned model. I want it for the question answering setup, and I simply just use the model. As simple as that. So when I actually execute this piece of code, the model is actually getting downloaded on my system. When I actually run this piece of code, I am not, what is happening exactly is this Hugging Face library, what it is doing is it is actually taking that model and it is downloading it on my system real time. And then once it gets downloaded, it executes this particular function, this piece of Python code, whatever this Python function is, it executes that particular function and it generates the response for me. When I'm essentially using, let's say, any of the open source models, at least so far, that's how we've been doing it. Earlier, if you remember the VGG16 model, where did we load the VGG16 model from? We loaded it from the Keras repository, if you remember, right? And if you remember, we also did object detection. And when we did object detection, we loaded the COCO model, commonplace, the common objects model for object detection. We loaded that particular model from the TF Zoo, the TensorFlow Zoo, which is essentially a repository of the TensorFlow models. So there are, Hugging Face is not the only such repository that hosts models, right? Hugging Face hosts models, Keras has a few models, TensorFlow has a few models. If you remember, we also use something called as Word2Vec or Glove and stuff like that. Where did we load these models from? What is the common repository for these models when you are executing this piece of code? Gensim or Spacey for that matter. Okay. The point that I'm trying to drive, guys, is when you talk about open source model repositories, there are many open source model repositories. There's Hugging Face, there is Keras, there is TensorFlow Zoo, there is Gensim, there is Spacey. There are so many open source model repositories that are available for people to just use any of these pre-trained models. You can download any of these pre-trained models from anywhere you want. By and large today, Hugging Face is one of the largest or the most popular one. Hugging Face today is one of the most popular open source model repository. Now, here comes the challenge. See, these models, mind you, right? Hosting these models has not been, this is how it has been until very recently. Okay. Nothing's wrong with this. But see, when Hugging Face is providing these models, what is in it for Hugging Face? You need to understand, okay, why will they do it, man? I mean, what is the whole point? Why would Hugging Face do it for free? What is in it for Hugging Face? Well, that's their open source play. That's their strategy. So they basically get people to use, and then they have an enterprise play, right? So they say, you know what? This is for everybody out there in the open source. And then what they're going to do is they're going to say, you look, you know what? If you are an organization and if you're worried about security and everything, let me provide an enterprise interface for you to access as well, for your company to store models, for your company to manage models. You might have data scientists in your team. They might need a way to manage their own models. You don't want to, let's say, put it on a public platform. For example, I might take a BERT model, an open source BERT model, and I might fine tune it on my company data, but I don't want to put it on the public Hugging Face model hub. I might want to put it elsewhere. I might want to store it because it's my company's IP now. So what Hugging Face does is, you know what? Okay, you don't have to put it there. I'll give you an enterprise interface. I'll give you an enterprise setup. You can host it there. And typically these companies, a company like a Hugging Face would charge you for it. That's how Hugging Face makes money. So Hugging Face, while on one side they're doing social service, on the other side they're using the same the same game to make money in the in the enterprise space, in the B2B space. That's how they operate. Now let's go one step further. This was all great until LLMs arrived. This setup was working fantastically well until LLMs arrived. I'll also take one step back, right? Before we go to the LLMs. How did the world work before, let's say, the BERTs? How did the world operate before BERT? All that all we were doing is we said, you know what? You need to build a machine learning model. Great. How do you build machine learning models? Your traditional models like your, like your random forests, linear regression, random forests, decision trees, gradient boosting machines. How do you build all of these models? Well, great. For that, we have a open source library called scikit-learn, right? So this was the open source software, right, called scikit-learn. And the scikit-learn was basically a Python library. And all that you and I did was we downloaded just the library. The data was on your machine. You downloaded the library and you built the model on your machine. The life was very simple. But then once larger models started to come, a good example is something like a VGG16, right? Once the concept of whole pre-trained models came in, first generation pre-trained models, right? So you can call it as first generation pre-trained models, right? A good example is something like a VGG16, other deep learning models, any of your other, models like, let's say, your ResNets, and so on and so forth. Other pre-trained models came in. Then what happened is this space, which was previously only scikit-learn, and also when deep learning sort of came in, this space started to become a little more crowded. What happened? You, of course, have your scikit-learn, where you could build models. Then other softwares like your PyTorch, right, TensorFlow came in, and they said, you know what, you can also build models using these. But then in parallel, these were how you could build models, right? So these are model building softwares, right? So these are all model building softwares. But what they also said is, look, you don't need to build, yeah, exactly, Spark ML, right? Spark ML lib, right? I'll just call it ML lib or Spark ML. They all sort of came in. Why all of these came in? Then you started to also have model repos started to come in. What model repos started to come in? So PyTorch or rather you had repos like your Keras, right? You had stuff like GenSim. You had stuff like TensorFlow Zoo, and so on and so forth. A lot of open source modeling repositories started to come in. So you have the regular, I'm just talking about a bit of a evolution here, guys. And I apologize in case this is getting a little overboard, but this is important for you to understand. Because this is how this space has evolved. Only then you will understand why some of the reasoning behind why we are operating the way we are operating. Then what happened is, and suddenly, somewhere in between, you would have the whole transformers. A lot of things happened in between, right? And I'm talking about some of the macro concepts here. Then, my friends, what happened was transformers came in, right? So I'm going to call it first generation, or let's call it your second generation pre-trained models, right? A good example here is, let's say, your BERT, and let's say all of the variants of BERTs sort of came in. And while this came in, GPT, we'll come to GPT. GPT, let's actually say the GPT-2, GPT-1, GPT-2, the initial versions of GPT. There was still open source models at that time. All of these models came in. By the way, here a good example was Word2Vec, right? Your Glove, all of these embedding models. But the moment the second generation models came in, the moment BERT sort of came in, then what started to happen is these models were not built on scikit-learn anymore. Scikit-learn started to phase out. Scikit-learn is still relevant for your regular traditional machine learning, but scikit-learn sort of lost its sheen. Then we started, even MLlib did not have a huge role to play. You were left from a modeling software standpoint. The software space was primarily crowded by your PyTorch and your TensorFlow, right? PyTorch and TensorFlow. To be more precise, actually, PyTorch has an edge over TensorFlow as we speak. But what happened was, while PyTorch and TensorFlow were the open source softwares for you to build models, the model repositories started to also evolve, right? So these started to phase out. Your GenSims, your Kereses, your TensorFlow Zoos, they all started to phase out. So by the way, here, when I say TensorFlow, by this time, TensorFlow and Keras sort of got merged, right? So now TensorFlow and Keras have sort of merged. By the way, Keras can also be used with PyTorch. A lot of things have happened under the hood. A lot of detail there, not worth going in. I'm talking about some of the macro concepts. What happened here was, interestingly enough, you started to have other modeling repos sort of come in. One of the most popular modeling repos, my friends, that has come in is your Hugging Face. I'm not saying the others don't exist. Actually, let me be a little considerate there when I say this. Hugging Face sort of came in. The Hugging Face modeling repo became super, super popular, right? And interestingly enough, because Hugging Face as a repo came in, Hugging Face also nicely came up with a small middleware in between. And they said, you know what? You want to use Hugging Face? Great. You can use Hugging Face, my friends. You can use my transformers library on Hugging Face. You can use my transformers library on Hugging Face. You can either directly use it or you can use it through PyTorch. But the point is, if you want to use any of the open source models that are hosted on Hugging Face, you could use it through these transformers libraries. This is, by the way, what we did, right? So we used this concept of Hugging Face transformers and the Hugging Face models to actually do these examples. This is what we did, right? Earlier, we would have done, TensorFlow with TensorFlow Zoo. We would have done TensorFlow with Keras using some models. We would have also done something with GenSim. We did all of this, by the way, if you're aware. This is how the space has progressed. Hugging Face can be used in TensorFlow as well. The Hugging Face models can be used with TensorFlow as well. Here comes the advent of, these transformers models have now started to become better and better. Now comes the LLM era, right? So LLMs came in, large language models, massive, massive models. What happened in the LLM era, large language model era? Now, by the way, when I am talking about era here, trust me, this is just like 2 years ago, right? This is not like long ago or something, 1.5, 2 years ago scene that I'm currently talking about. So what happened here? So now your newer models came in, your models like GPT-3, or 3.5, 4, 4.0, and a bunch of others, right? So your llamas of the world, and so on and so forth. We are in this era right now. Exactly. We are currently, when we are talking, we've progressed from here to here. This is what we discussed in a previous session. We're going from here to here right now. What happened here, my friends, is this is where a lot of, companies started to flex a little. I'll tell you why, right? So companies like OpenAI, companies like, let's say, Microsoft, and all of these then started to play a bit of a interesting game here. Now, this is the Gen AI wars, generative AI wars. Okay, that's been happening out there in the market. So what happened here is, see, as we went from here to here, right? As you go from left to right, can you tell me what is changing from left to right? One thing is increasing as you go from left to right. As you go from here to here, what's happening? From left to right as you go, size of data is significantly growing up. The size of the model is significantly going up. The cost of building these models, building these pre-trained models, my friends, is exponentially going up. Right? Until here, it was okay. It was expensive. To build a BERT model is not easy. It was expensive. But it was okay. But what happened is that because of the size of the data, size of the model, and the cost of the model has gone up significantly, it started to become more and more and more complex for people to use these models, right? Until here, what was happening, even if I was using the Transformers model, Transformers library, it was difficult. I was still downloading. If you remember, if you were, if we were using, where did that go? Let's actually go up all the way up here. When I was actually downloading these models are not small. These models are as big as, yeah, look at this. Look at this, 1.5 GB, 2 GB, 10 GB at times. These models were already fairly big at that time, right? And this is a simple zero-shot classification model that I was using. There's already a distill BERT, which is a much smaller model. These models were big already here. So I was actually downloading these models and accessing these models on my machine. But if the size of the model becomes so large that downloading this model every time is prohibitive to the extent that you, let alone downloading the model, even if you download the model, you cannot load it into your memory anymore. If I have a 16 GB machine, and if I have a model that is 30 GB, 50 GB, 100 GB, what will you do with a model like that? Can you even load that model into your RAM? You cannot even load the model into your RAM. So now the challenge is now more so with the fact that these models are so large that even if you download the model, you will not be able to use it. So two things have coming in parallel here. One is the models have become so good that you will get a lot of benefit. But in parallel, the size of the model has also gone up so high that you actually cannot download these models anymore. So what do you do then? Well, that's where these companies started to flex a little. Here is where the open source world started to take a slightly different route. They were primarily these open source companies. A lot of them, especially companies like OpenAI, some of these companies decided not to open source the models. They said, you know what? I'm not going to open source these models anymore. They said, we'll tell you broadly how the model was built, but what we'll do here is we will start slowly making these models accessible for you through slightly different ways. So though I've put GPT-3 3.4440 over here, what I want you to understand, my friends, is that these models, though GPT and GPT-2 were open source, GPT-3, 3.54 and 4.0 are not open source. These are not open source. They are not open source. Llama 2, they are open. Llama and Llama 2 are open source. Meta has actually, actually, that was a bit of a bummer by Meta. The Llama model was never meant to be open sourced, but they actually ended up open sourcing it by mistake. Google has not open sourced their models, right? So Gemini models are not open source. There are some other companies like Claude is not open sourced. There's a model called Mistral, which has been open sourced. So some companies have open sourced. Most of them have not open sourced. They have not opened their cards yet. What is their game here? What do they want to do here? Because these models have suddenly, right, exactly at this time, what has happened is suddenly these models have become so good that people now start seeing some crazy benefits with these models, right? Some tasks have started to become automated. ChatGPT became so popular that it could actually solve some very, very obvious problems, right? Handwriting, meaning handwritten documents wouldn't have to be written anymore. It was automating a lot of tasks. And that's where these guys started to realize, you know what? Let's see what we can do here. So, and companies like OpenAI, though they say they are open AI, though they're in theory they're supposed to be open, what they say is, you know what, we don't want to open source these models because it's in the benefit of the world. These models could be misused for some wrong reasons. That's what they claim, which to me is not just to me. I mean, in general, the AI community does not think that is totally true. They actually are doing it because they want to hold back some of the IP. So what are they doing here? I'll tell you. I'll first talk about the companies that are open source them, right? Some of these models like Llama and the others. Even though they have open sourced them, it's very difficult for you, me, some of the smaller LLMs, smaller models, you can still download and you can use it on your machines. But how do you download them and how do you use them on your machines? Well, Hugging Face is still there. Hugging Face is still here for people to use. And the smaller LLMs, Hugging Face is still there. The Hugging Face Transformers library is still relevant, right? There are other smaller libraries as well that are there. Like, for example, every company that provides the models, they are also hosting these models. They're also providing. So all the smaller LLMs, they are all made available through Hugging Face. Okay. So the process still remains the same, right? So Hugging Face. So all that you could do is you can just go to the Hugging Face library, Hugging Face Transformers model library, and then you can download the model and you can access it. But the big wigs, right? All of the big models, they went down a slightly different path. They said, you know what? Our models are not open source. Our models are not open source. Okay. Then how do we access these models? They said, you know what? Okay. If you want to access these models, there are different ways you can do it. We will host the models. When I say we, meaning the companies themselves will host the models. So what OpenAI started to do, I'll take the example of OpenAI, but this is sort of true for almost every closed sourced model company or every company that has closed sourced these models. What OpenAI did is OpenAI said, you know what, we will host the model for you, right? So OpenAI has hosted these models on Azure or on AWS, depends on wherever they wanted it. They've hosted it, and they say, you don't need to download the model. I will provide an interface for you. So it can be the OpenAI. I'll give you the OpenAI library, or you can use the Llama or you can use the Gemini library or whatever, right? So you have a bunch of different libraries that are there. And if you want, you can use these models through these libraries just through APIs. You can just use it through an API. So you will get a private key, and then in your code, You just will have to use the OpenAI library to make calls to this particular model. So the model, remember, now you're not downloading the model anymore. You, let alone downloading the model, you don't even know any of these things about the model. You just know broadly the architecture. You don't have the source code of the model. You broadly know what datasets have been used. You don't have the raw model access to you at all. You don't have any of these with you. Now, all that you're doing is, okay, the model is sitting somewhere on Azure or on AWS or on GCP or on Google Cloud Platform. And then you can start accessing these models through keys, right? So just the way we did in the first session, we open the interface and then you can start accessing these models. So now these companies have started to say, you know what, it's hard for you to access these models. You cannot deploy these models by yourself. You cannot host it by yourself. It's very, very cost prohibitive, blah, blah, blah. And then now the only way that you can access any of these models is through APIs, right? API essentially is a simple function that you will have to make a remote call. It's like a website, right? So you'll have to make a remote call and then you will have to, it's hosted on a server somewhere on the cloud. And then you're in some data center on some other part of the world and you're just making a call and then you're fetching the response. That's it. So you're merely doing inferencing. You can also do fine tuning if you want, but it'll all happen on the other side of the world. I'll talk more about how this world works. Now comes the question, man, this is painful because now if you want to use some models, you can use Hugging Face. But if you want to use these models, you need to use these OpenAI LLMs, you need to, or the OpenAI libraries, or you'll have to use the Gemini libraries. I don't know, I'll have to probably use a GCP library that they have, or some library somebody provides. Like, what the heck? Like, how can I standardize this? Like, how can I, as a developer, for me, what is my best way to access all of these models? Well, there is an answer to that as well. The best way for you to access all of these is they said, you know what? You don't worry. There is another open source company that came in and they created another layer on top of it, right? They created another layer on top of it. This is another abstraction layer on top of your Hugging Face. This is another abstraction layer on top of your models that are hosted here. That, my friends, is LangChain. Or there are other players in this space as well. There's something called as Llama Index. This is LangChain or Llama Index. So now I'll just talk a little bit about this space here, okay? I'll just talk a little bit about how these open source or these closed source models today are typically being accessed, right? So how do you access these closed source LLMs? They are, as I said, there are two setups for this, right? So one is for personal use and the other is enterprise. One is the personal use and the other is for enterprise. What do you mean by personal use? Like you and I, we want to do some stuff. So how do I use these models? And if I'm doing it in my organization, in my company, what's the right way for me to use these models? See, there is always a fear. You need to understand one thing, right? You do it on personal or you do it on enterprise. Chat GPT, or rather these GPT models, the Llama models, okay, so let's actually talk about this, right? So how do you use it for personal usage? For personal usage, right? If you choose to, let's say, go with OpenAI, you will do like what I did in the beginning of the session. What you will do is you'll simply go to the OpenAI library, or you will go to the OpenAI page. You will create a key for yourself, right? And then once that key is created, then you will use that particular key in your Python interface, right? So you have your Python interface or your VS Code or whatever. You will essentially use this particular key and then you will access the model, right? So the underlying model, whatever GPT, I'm just giving GPT 3 point, or rather 3 is gone anyways now. 3 doesn't exist. 3.5, 4.40, any of these models, you can use it through the OpenAI key. But how do you access this model? You can use LangChain, or you can use LangChain, or you can use the OpenAI library to access the model, right? Now, the challenge here is that if you were to access these models through this, when I go to the OpenAI website and when I host this model, when I'm saying I want just the key, I am using a public version of this particular model. This model, I have no clue where this model is hosted. By the way, the same thing holds good for, let's say, a Gemini model as well, right? So if I want to use a Gemini model, it's the same exact story. I'll just show you the same thing here as well. Right. So if I want to access the Gemini models, any of these models, right, build with Gemini, it'll take me to this website, right? I need to get an API key on Google Studio, right? And cancel. Let me just go here. Accept, biggest lie on the internet. I don't want this, continue. So I can just go in here and I can simply say, hey, create an API key. Got it. And of course I need to put my credit card details or whatever. I need to create a API key in a new project, whatever. Basically create the key. I can then come back and then I can my my Gemini key, right? So whatever key that I create here, and then I can access it either through the OpenAI, library, any Gemini library or the Gemini interface, or I can use it through some kind of a LangChain sort of an interface in my Python. Right? I can do any of it this way. The problem with this, remember, is these are models that are hosted publicly. These are models that Gemini is hosted. These are models that GPT is hosted. I have no clue where these models are hosted. Are these models hosted in Pakistan? Are these models hosted in Russia and Ukraine? Are these models hosted in China? Are they hosted in the US? I have no idea which data center they sit in. I have no idea what is happening to this data because I am a consumer and I have literally nothing that I can hold them against because I am trying to use these models for my personal use. It's very hard for me to access these models. The problem is, and when I make an API call, I'm actually making a call to wherever these models are hosted. These models probably are hosted in China. I'm probably making a call to China. These models are probably hosted in Pakistan. I'm making a call to Pakistan to access these results. So if I am using anything sensitive, then I am in soup because I have no clue where this particular model is. Because I'm making a remote call, I have no clue where these models are. And that's a bit of a challenge. Maybe for a personal use, it's okay. Maybe I'm using this to write an email for my own self, it's okay. Maybe I'm using this to create a resume for myself, maybe it's fine. Maybe it's okay if I am trying to create some images for a YouTube channel that I might want to create. Maybe that's okay. But if I start to do the same with my company data, I'm trying to write an email on my company data somewhere, or I'm trying to copy paste something from my company setup into this, and then I'm trying to do the same. Then I'm in deep soup. Then I'm in deep trouble because I have no clue if what, let's say, an OpenAI or a Gemini is doing with that data. Hence, this is all right if I am taking care, if I'm doing it for my personal use. But the moment I start using this for enterprise use, my friends, right? Then I have to change these ways of working. These models cannot be hosted wherever they want. If my company wants to use this model, then I, as an organization, need to have a better clarity / confidence on where is this data going, because the whole GDPR thing kicks in, data privacy kicks in. Somebody spoke about AI ethics, all of that kicks in, like a million other aspects that, let's say, companies that need to take care of this. That's why the best way to, in an enterprise setup, to access some of these closed source models is always through your cloud provider, right? So you may have an Azure account, or you may have a GCP or whatever, right? So you may have Azure. Let me actually make it simpler. You may have an Azure or GCP or an AWS accounts. Azure cloud interface, Google cloud interface, or a AWS cloud setup that your company might be already using. Maybe one or two, or in certain cases it's one, in certain cases it's multiple. Depends on organization to organization. This might already be your cloud strategy. You're probably already using Azure or GCP or AWS in your companies. Now, what these companies are doing, what an Azure or a GCP or AWS is doing is they are saying, hey, you know what? You don't worry about all of this. We will give you a secure access to all of these models, right? All of these foundational models, LLMs, I'm just going to use LLMs here. You have a secure access to all of this, right? You have a nice secure access to all of these models. It's like taken care of. It's locked under, let's say, your organizational policies. You don't have to worry about it. We will host it for you in your setup, in your organizational subscriptions. So you don't need to worry about it. If you want to get the key, don't go to the OpenAI interfaces or don't go to the Gemini public interfaces. Rather, come to the Azure interface or the GCP model interface or AWS's Bedrock. So Azure has something called as Azure AI Studio. GCP has something called as Vertex AI. AWS has something called as AWS Bedrock. These are all enterprise model repositories. These are like, again, Hugging Face hubs in the enterprise space. By the way, just to let you know, Hugging Face also has a game here. Hugging Face also plays here in this place. Hugging Face says, you know what? You might not want these complex models, these complex foundational models, these meaning these closed source models, but you might require the open source models, right? Then I will also provide those open source models through the Hugging Face game, right? So Hugging Face also says, I'll embed myself into this as well. Yeah, there's a big complex stuff that's going on here. The point is, now as a user or as a developer, you, right, as a developer or a data scientist, right? So I'm just using the word developer loosely here. As a data scientist, you will only get the key from here now. Your model keys will come from here. You still don't have access to the model, by the way. You still don't have access to the model. You still cannot download the model. You still cannot see the model. Somewhere it is hosted. You have no clue where it is hosted. But you know that it is hosted in your subscription in your Azure account or in your GCP account or in your AWS account. Private cloud. So everything is safe. If something goes south, your company can hold the neck of, let's say, an AWS or an Azure, a Microsoft or an Amazon, and say they can sue them for their life. So now enterprise agreements sort of kick in. This is the safest route, right, that you could use any of your large language models. This is the only and the best way for you to access these. By the way, LangChain plays here as well. So now you have the whole LangChain set up here. So it doesn't matter LangChain accesses these models or these models. It doesn't matter. LangChain also gives you a LangChain or Llama index for that matter. Both of them will give you a nice interface for you to access all of these models. So if you are doing it in your enterprise setup, my friends, do it the right way, meaning the way on the right side. If you're doing it for your personal use, it doesn't matter. You do it the thing on the right or the left, it doesn't matter. But if you're doing it for your enterprise, do it right way. Do it the right way, literally the right way, the thing that you see on the right side. Simply put, don't use the keys that you are creating for your company stuff. If you've done it, don't tell it in your company today, in your organization today. If they get to know, you might lose your job. So please don't do that. Big red flag that is. You might have already, if you're using any of your, even if it's a private key that you're using from, let's say, your personal, from your personal subscription, my friends, you have no clue what they do with that data. So do not use any of these models, even with your private keys or whatever, from your personal from your personal subscription. Do they misuse? Here's the thing. Do you and OpenAI have an agreement? Do you have a personal agreement? If they should, no. So yeah, when there is no agreement, you have no claim at it. In fact, you also ticked some boxes over there which you and I have never read. There's a lot in that fine print that you and I have no clue. In an enterprise setup, the procurement teams, the legal teams, they all read that fine print. In our daily life, you and I don't read anything in that fine print. For that reason, never use the OpenAI models or any of these models that are available in public. Do not put any company stuff on ChatGPT. You will be screwed over if you do something like that. If they misuse our company data, if you do it the enterprise route, then you can claim. But if you do that through the left side, and if you say it's company data first, you will lose your job, right? So let's actually see how one could access any of these models. So what we're going to be doing, and in probably we'll try to also do an open source model as well. So we'll try to access like an open source LLM as well. Maybe not right now, but maybe after that. Um, so let's start with actually creating OpenAI. So if you go to the OpenAI portal, right? You go to the OpenAI portal. By the way, this is the O1 models which have recently launched, by the way. So you could sort of access them as well. This is a strawberry model. But anyways, I mean, we can come to that later. The O1 models, by the way, are pretty good apparently with science and coding and math, which is fantastic, because I think that way you could access some of these models well as well. And these models will only get better, right? Just the thing that you need to understand is these models over time will just only start getting better and better. So anyways, so how do you access these models? So try it in the API. That's how you and I will have to access. I'll just quickly log in. Perfect. Let's go. I think I've logged in. So now this is the platform, right? So this is the OpenAI platform. They do say that the API and the playground request will not be used to train our models. They do say it. But you have to be careful, right? So you just have to be careful, right? So they've added this very recently. ChatGPT is not the case. ChatGPT, they train it, but then if you're using it through this, generally they say that they don't use it. But again, you've got to be very, very careful here. But again, let's go here. So how do you access the models itself? So go to the API reference on the left side. By the way, before you even get started, the first thing that we need to do, just go to the billing. Looks like some of you guys have been using my models clearly. So I have, of course, recharged this. I've added some credit balance here. You need to, of course, add your credit cards. You need to, of course, make your payments through this, just so that you have some credits to start using. Once you, and it's pretty straightforward, just go to the, to the billing history. Actually, let's go back here. You could just add a payment method and you can start using it straight away. Now, once you're back here, how do you actually use these models? So you can, let's go back here. Let's go to let's go to the dashboard. In here, you can create, of course, a project, and you can start using it through a project, or you can just go to API keys here. And what I have done is, by the way, there was previously called as user keys. We recommend using project-based API keys for more granular control over your resources. But that's okay for the moment. What I would simply request you to do is just go to the user keys. But the moment you start using, if you start using the project keys, the way you access it has to be slightly different. That's the only small thing. User API keys is essentially how, and by the way, I'll also tell you how to switch from the user keys. I had created a user key here, and this was the key that I had provided all of you access, right? And you can also specify which, you can, of course, do like a bunch of different things here. There's a default organization. If you want, you can also go here, create a new project, and you can do it as well. But for the moment, just to kind of simplify the access, the most simplest way to access it is go to user keys, user API keys, create a key, give it some name. The moment you do it, it'll give you a secret key name. It'll actually give you a key. Once you have that key, you're good to go. Save that key somewhere, and you're good to go from there on. So how do you do it from there? How do you access it from there? Well, it's super easy. I'm just going to switch to the first. Once you have that key, my friends, all that you need to do No, you cannot see the key again. You will have to, once you've created the key, it will not be shown again. You have to delete that and create a new one if you want to. You cannot see it again. After that, of course, once you come back here to your OpenAI or to your Jupyter notebook, just install the OpenAI library. Just install the pip, just do pip install OpenAI. And the moment you do that, of course, some of the necessary libraries are downloaded. And then what I have also done is I've created a file called .env, as you can see here, and I've put the key here, right? Whatever key that you see here, and by the way, this is the same key that I have provided all of you the same access, right? It says OpenAI API key, and I've provided this as the value of that OpenAI API key. Now, once I do that, this is just for me to manage keys, right? So why do you need to put it in the file? The only reason why we put it in a file and not straight in the code is because it becomes so much more easier for you to access, for you to do version controlling of this code. See, imagine if I put the code here, then I cannot version control this notebook, because if I try to publish into Git, then somebody will have access to this, becomes so much more complex. So instead, if you just put it in a .env file, you can push this notebook, but you can restrict the .env file from getting pushed. That way, you can version control the notebook without actually exposing all the private keys. All that you need to do is import .env, this library called .env, simply say .env.load.env. That will load the key for you. That key is now loaded so it parses a .env file and then load all the variables found as environment variables. So whatever we just saw is now loaded as an environment variable for you. If you're doing it in Colab, you can do the same as well. If you're doing it in Colab, you can also provide a path, right? So if you just want to be doubly sure, you can also provide a path here. You can simply say is equal to whatever dot. In my case, I already have it here. If you're doing it in Colab, just make sure that worst case, if you're unable to do this, copy this, come here, put it in here. And the best thing you could do is simply, whenever you're creating this OpenAI key, you see something called as API key. API underscore key is equal to OpenAI key. Worst case, if you're not able to do anything, just copy paste the OpenAI key in your notebook. And whenever you're creating this client, when you're creating this particular client object, it's probably because you're not creating the .env file. It's okay. Forget about the .env. Forget about all of this. Don't worry about all of that. Just do this. Take the OpenAI key, paste the key here. As simple as that. And just say from OpenAI, import OpenAI, and then simply put client is equal to OpenAI. And when you're creating the key, just pass the key here inside this and just run. That should work. No .env, nothing, just works. If this also doesn't work, then either your key is incorrect or you're just not writing the code the right way. I mean, you're just making some errors in the code. Okay. Now, so what is the pricing of these models like, right? So the pricing of these models is, if you actually go back here again, now you will start seeing. So if you actually if you go to API reference, and if you go to models, no, not this. Hang on, not this. Dashboard, just a second. Must be here, just a second. I was trying to find it. You know what? The simplest way to do this is just Google it. OpenAI pricing. There you go. Perfect. Simple. This is the simplest thing to do. So if you look at it, so multiple models, each with different capabilities and price points. Prices can be viewed in units of either per 1 million or 1K tokens. You can think of tokens as pieces of words, where 1,000 tokens is about 750 words. Okay. Language models are also available in the batch API that returns completions within 24 hours for a 50% discount. Yeah, that's okay. These are for batch related stuff. Like for example, if you're doing some batch executions, you could use this. Much cheaper. But anyways, doesn't matter. So if you look at it, this is the pricing. If you take, for example, the 4.0 model, the GPT 4.0 model is as much as what you see on the screen. The GPT 4.0 charges you $5 per 1 million tokens. 1 million tokens is approximately around 750,000 words. And you can think of how big or how small 750,000 words could be, right? 750,000 is, I think, approximately around, is as big as a book, or even probably much larger than that, right? So long story short, the point is this is the pricing that you see here. One of the things that you could actually do is you can actually ask ChatGPT to benchmark this cost for you, right? So let me actually just open this up. Benchmark the cost of GPT 4.0 and the latest Gemini models and return. So if you see, right, and this will of course return quickly, the cost of all the other best models. So the GPT 4.0, I think per million tokens, I don't know why does it say $3. It's actually not $3. It's actually slightly larger than $3. So for example, if you take, for example, Claude or Gemini Flash is around 0.125. Claude Sonnet, which is one of their best models, Claude Sonnet and Claude Haiku. These are still not available. The pricing, because I think it's still an open source sort of a setup, you can have to install. I mean, you'll have to set it up and then start using it. If you take, for example, the Gemini models, 0.125. These are slightly cheaper than the other models, but it has a subscription fee. So you got to pay like $20 upfront as a subscription, and then you can start using it. The per call cost is much smaller. Per million tokens cost is much smaller here in this case. The point is that different models have a different pricing setup. Like for example, 4.0 mini and Flash are actually comparable. So that way you could sort of use it pretty straightforward. By the way, 4.0 is super easy. Is actually free through ChatGPT. So that's one good thing. So everything is almost on the ballpark. You know what? Actually, these companies are not making money with subscription fees right now. This is just barely meeting their needs. They will not be able to survive on this for the moment, at least. But let's go back here. So that's as far as how you simply use an open source OpenAI, sorry, a closed source model through the OpenAI key. Now, just one more small piece here of information, right? If you remember here, if you come back here, let's go back here. Let's go to OpenAI, product, platform. Okay, so if you actually come here to the platform, to the keys section, you can actually create, as I said, a project, right? And you can actually use the project key as well. So this was the user key that we had created a while earlier. What you could also do is you can actually create a project, right? Like for example, I can say Intellipaat project, and then I can simply create. This is irritating. Right. So, and then what you could do is now I have this particular project set up. So in this project, I could sort of come back here. And now what I can do is I can create a project key in this particular case. So this is my name of the project, and I can create a new project key. So this is very specific to a particular project. So remember, I might be running multiple projects. So this is IP user, and this is the project that I'm creating this particular key for, Intellipaat user. And I'm going to create a key. So now I'm just going to go back here again, but this time right? So this is my project key. The second one, the key 2, is my project key that I've created. But if I simply switch to a project key and if I execute, this might typically fail. Okay, perfect. It actually got executed straight away. There you go. So this is my project key and I simply executed it. And if I run this, there you go. Perfect. There you go. I could also here pass my project, which is the name of the project that I am using. For example, I was probably using this for the IP project. Yeah, ideally I can actually tag it to the project, but looks like something is not right. Even without the project is actually getting executed, I think what it's able to do is it's able to decipher that from this particular key itself. If you see it goes with a project, and the key is much larger. So it is indeed, I think it is already encoded in the key itself. So that is actually not bad. So if you look at the completion response, it's executing. So that's not bad. At least the point is, even if you were to use the project key, you can also use the project key straight away if you wish to it. I think they've changed something with regards to accessing the project keys. Let me just check one small thing. Yeah. So one more thing that I just want to talk about is this, right? So if you look at this, so I just executed the whole thing, the completion output. And if I I took the output and I simply converted it into a dictionary. So if you look at this, what it has returned is, of course, it is telling me what the execution ID of this particular chat is and everything. And it, of course, gives me the responses, results and everything. Now, the point that I want you to understand is it, of course, tells me which model it has used. It tells me it's a chat completion object. But this is the part that I want us to be and that I want us to understand. The completion tokens totally are 184. The prompt tokens are 57. So what does that mean? The output that was generated here had a total of 184 tokens. The prompt tokens, which means the question that I had asked for over here, all of these, my friends, right? So everything that you see here, this and this put together is a total of 57 tokens. So 84 plus 57 tokens, that sums up to a total of 241 tokens. So if you know the total number of tokens, you should be able to compute the cost of the cost of this particular call as well. So the cost of this particular call is total underscore. So if you take, for example, 241 tokens multiplied by what was the cost of these models? OpenAI. And if you actually go here, and we are currently using the GPT-4o mini. This is the model that I'm using. The 4o mini model is what I'm currently using. So if I simply change this to 1000, the 4o mini model that is currently being used, which one? Oh, sorry, here. The GPT-4o mini model 0718. That is approximately, as you can see here, 0.00015. That's the cost of this particular model right now. So you buy per 1000 tokens. So this divided by 1000, that's the total cost of this particular call right now. Whatever this call was, that's the total cost. So 3.6 into 10 to the power of minus $5. That's how much it costed for me to execute this one particular call. By the way, one of the things that might also happen, and one of the things you need to understand is if you actually go in here, there is a concept called as rate limit. Okay, so if you actually scroll all the way till the end, sorry, docs. If you go all the way till the end here, you see something called as rate limits. There's a concept called as rate limits. Rate limits are basically to ensure that they essentially throttle some of the requests. So if you have made too many calls, then there are some rate limits that you would have, right? So if you just paid $5, there are some specific, in the free tier, you can access it to a certain level. In the tier 1, there are certain rate limits. There's a bunch of rate limits that you have here, tokens per minute. So you can only fire a certain number of tokens per minute. So in case you are firing too many tokens, it might fail as well. Just bear that in mind. Because not all models are available forever. Because if too many people are using it at the same time, it might also shoot up their cost, which is why they throttle requests beyond a certain point. All right, so this is how you access, let's say, an OpenAI model through the OpenAI model interface, right? So through the chat interface, or rather the API interface, as I said. Now, the thing is, if you actually go back here again, so if you actually go back here, one of the things that you will also observe, right? So if you go back to the playground, this is, by the way, text to speech. TTS is text to speech playground. So you can just write a piece of text and it'll generate that text into speech as well. But if you actually go here, right, you can also fine tune your models. For example, we'll actually come to that in a few minutes. But the point is, there you go, in the dashboard. So if you actually go to fine tuning, what you can do is you can start creating a job, right? So you can essentially create a data set. You can pick any model that you want. Like, for example, if I'm using the GPT-4o model or the 4o mini model, and then you can pass a JSON file with all of the data that you want, right? So some new fresh data set if you want to pass with a question, with an answer, and so on and so forth. You can decide the batch size, the number of epochs and everything, and you can actually train it. You can actually fine tune it. But what you need to understand is fine tuning is expensive, has a separate cost associated with it. The fine tuning cost is actually much larger than simply just using the model itself. By the way, this is how the format of the data set should look like. This is a question. This is the content. So system response, and so on and so forth. It should sort of look like this. And then there is also a cost associated with it. So if you, for example, base training cost per 1 million tokens, you can sort of think of approximately around, as you can see, approximately $2.4 with a GPT 3.5 model. A file that has 100,000 tokens, 2 or 3 epochs would cost you like $1 for a GPT-4o mini model. But if you have a larger data set, which has, let's say, many documents, and if you want to train it for longer, then as you can imagine, this cost could shoot up very quickly. So that's one thing that you have to keep in mind. So if you're trying to fine tune a particular model, then this model could be very expensive. So that's point number 1. This is for a closed sourced model, my friends. So as you can imagine, accessing these models there's a cost associated to this. You need to pay for this. You need to be a little mindful as to how you would be using any of these models. So back again, right? So let's think about. So here, as you can see, we're using a GPT-4o mini model. All that I'm saying is, hey, look, I'm asking it a question, and I'm giving the role of a user. I'm giving the role of a system, and then I'm simply asking it to execute. Right? I'm just simply saying, hey, complete this particular chat for me, and I'm saying what are the differences between AI and Gen AI, and the expectation is it actually responds back to that particular question. Same here as well, right? Again, chat completions. And then I'm saying, hey, look, I'm using a GPT-4o model here, which is a slightly different model. And I'm actually asking it to create a poem, and so on and so forth. So this is basically what we did in the first session. And if you remember, right? Nothing different from all of this. My point is that these are the models that are currently being used. So when we talk about large language models, it's these models. This was our first session, if you remember. This is exactly what we all did. We had discussed about zero-shot classification, right? So I could simply do this. I can just go back here and I can say roll. I'll just remove all of this and I'll say I'm giving a system persona. You are a data analyst that is an expert with understanding language and its nuances. And here I'm saying, and I'm also going to say, classify each of the input sentences provided into one of the following classes: positive, negative, and neutral. Also provide a score against this classification that depicts the strength. Okay. And now I can simply pass any sentence. This was a horrible day. There you go. Class negative, confidence score 0.95. That's it. Okay. But for things like these, right, you don't need a 4O model. You can do this using a simple 4O mini model, because these are simple language related stuff. You could get simple models also solve for this. That way it is going to be super easy. By the way, what you could also do, right, is you can, just to kind of make this very predictable, you can say ensure that the response is always a JSON with the keys class or sentiment class and what's the other one? Score. So if you write something like this, it'll make sure that the output is always standardized. It'll always ensure that it'll return it in that fashion for you. It'll always return a dictionary for you. Whenever you execute this, it'll always return a dictionary for you. You can use this for whatever you want. For example, the beauty about something like this is I can also write my in-laws were, or rather are, as sweet as Nazis. Now, the thing is, a sentence like this is sarcasm, by the way. If I use a GPT-4o model, 4o mini model, it does identify it's actually negative sentiment. Though it might seem like it is positive, it's actually negative sentiment. So these models are actually very good at coming up with stuff like this. They actually assess sentiment like this as well, and they're actually fairly good when it comes to capturing sarcasm, capturing slightly more nuanced concepts as far as sentiment analysis is concerned. These are very, very good at this. Okay. Awesome. Yeah, I can also say the product has 3 features. You can simply say a camera, I don't know, phone calling, and 5G internet. What would you expect the class for this to be? Neutral. That's a fact. Facts don't have sentiments. It's neutral, as you can imagine. All right, cool. This is how your classification would work. By the way, this is the beauty of, let's say, these OpenAI models. And you could not, when I say OpenAI models, what I mean is you could, of course, use this for a bunch of different, tasks, like what you can see here. But this is great. But of course, I want to take it one step further, right? I, of course, want to take it one step further. These are some very simple tasks that I can maybe, stuff like this, I can probably do it using some other BERT models as well. But this is great. There is text generation, content generation that we did earlier, like code generation, content generation. These are all some very useful, capabilities. But where I really want to start using this, right? Where I really want to start using a capability like this is in slightly more complex aspects. Like what? I might want to use a capability like this to be able to maybe do question answering like what we did with BERT. Right? You remember BERT, right? The BERT models did question answering, but they did a different kinds of question answering. What is the kind of question answering that we did? We did extractive question answering. You remember? We spoke about two types of question answering: extractive question answering and generative question answering. Extractive question answering is basically a question answering system which would essentially extract some sentences or some words from an existing sentence and respond back. But the thing is, I might want it to do slightly something beyond that. I might want it to do generative question answering. Let's take a simple example, right? Let's actually take the same example as that of the BERT problem that we had solved. Let me actually pull up the same recent files. Perfect. So let's actually go here. So this is a question answering, but blah, blah, blah. We did a lot of stuff. Let me actually copy the same thing. And let me actually ask the same question. And let's see what it has to say. Let's go back here. And I'm going to remove all of this. You are an intelligent assistant that has the ability to infer from a piece of context and respond back to questions, right? And then I'm going to say, hey, look, answer the question from the below context, right? And this is the text that I have provided. Right? And this is the text that I have provided. And I'm saying, hey, answer this particular question. Oops. And the question what is the question that I wanted to answer? What is Jersey Act? Right? That was the question. So if you remember, in the Hugging Face, sorry, when we did it using the earlier one, it actually extracted to prevent the registration of most American bred thoroughbred horses, which is basically to prevent the registration of most American thoroughbred horses. It exactly extracted those words and it responded back. But now when I do this using these OpenAI models, look what it has to say. Look what it's saying. The Jersey Act was a regulation introduced to prevent the registration of most American thoroughbred horses in the British General Stud Book. It aimed to address concerns among British horse breeders, blah, 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 which were perceived as potentially having impure bloodlines, particularly during the early 20th century. This was influenced by factors such as loss of breeding records, due to American Civil War and later start of American thoroughbred registration, which led to doubts about the purity of American bred horses in British racing circles. If you see this, this has basically taken this complete sentence and it's actually rephrased the whole thing for us. That's pretty cool, right? So it actually did question answering, but it kind of course, did not just return the same sentence. It, of course, tried to keep it. It actually came up with its own response. It did not exactly extract a certain set of words and stitched it together, but rather it actually came up with its own response in this particular case. I'll give you another. I can also ask it to keep the responses short and do not make up things that you don't know. And I ask the same question. This time the response is much shorter. So much shorter. Now, if here I ask, right now, if I ask, let's say, what is, I don't know, what is Simon Act? I have no clue what that is. That's what it says. Because I asked it not to make things up. Does that make sense, everyone? Do you understand? This is generative question answering. Here, it's not just randomly, extracting words and stitching them together, but rather what it is doing is it is trying to come up with a response from the context that it sees. Right. Let me just change this to context. And let's see what it says. I just want to, yeah. But if I don't do this, and if I remove, and if I make it a little loose, it could, yeah, it still doesn't. And I'll say, infer from a B and respond back to the question to the best of your knowledge. It's still trying to be very restrictive here. I think it's still, yeah. It's still trying to be as restrictive as possible. Let's say commission. I don't think it'll still respond back, because the thing is, if you need information about Simon Commission, please let me know. It does kind of lure you into asking more questions, but of course, it's not answering that question in the first go for you over here. My point is, this is generative question answering, my friends, where it's not just randomly coming up with things, or it's not just extracting a certain set of words like what you had seen earlier, but it's actually looking at the question and the content that you've passed, and it is trying to respond back, which is the next level of question answering. If it's able to do question answering on this small piece of question, then can it do it from, let's say, a Wikipedia article completely? Can I pass it a complete Wikipedia article, and can I ask it any kind of question that I want? Well, maybe we can, right? That's what we will see, right? So what we're going to see moving forward, we'll see how we can pass a complete Wikipedia article, or maybe a bunch of Wikipedia articles, or maybe, a bunch of Word documents or PDF documents, and say, hey, look, and then start doing question answering on top of it, right? How can we get these models to do all of that stuff a little more smartly? Not just from, let's say, a piece of paragraph, but rather how can I provide it a much larger paragraph, and how can I get it to do question answering?
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
So we'll use one of the GPT models, right? So 3.5, GPT-4, 4 mini, whatever, doesn't matter, whichever models, right? And the objective that we're going to be doing is I'm going to try and walk you through some very interesting examples, right? To start with some very, very simple question answering setup. What do I mean by that? Let's take a look at this. So we'll start with simple generative question answering, and then we'll build on top of it. Let's say I have a question, right? Which athlete won the gold medal in high jump at 2020 Summer Olympics? Right? Very simple question. Which athlete had won the gold medal in high jump at 2020 Summer Olympics? Now, what I do is I create a simple chat interface here, right? So I simply create the same OpenAI model. Let's use the let's stick to this. That's okay. So I'm simply asking a question: which athlete won the gold medal in the high jump at 2020 Summer Olympics? I pass this particular question to the GPT 3.5 turbo model, and it simply replies back saying, "Hey, Mutaz S. Abersim of Qatar and Gianmarco Tamberi of Italy both won the gold medal in the men's high jump in 2020 Summer Olympics. They decided to share the gold medal rather than participate in a jump off." This is actually a very, 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 very sweet sportive incident, or rather event that has happened ever in the history of Olympics, where actually two athletes just decided to share. This is beautiful how they actually did it. But anyways, but the question is, I asked a simple question about 2020 Summer Olympics, and your GPT model, GPT 3.5 turbo model, was actually able to answer this particular question. Well, I actually, if you want to cross verify this 2020 Summer Olympics, if you actually scroll down and if you look at the results, let's go all the way down. Where did that go? So if you actually look here on the left side, on the right side, Mutaz Abersim and Gianmarco Tamberi, both of them had had actually won gold in this particular event. So which was actually true. There's nothing wrong with the model. The model did the right thing here. But let's ask a slightly different question. Which athletes won the gold medal in curling at 2022 Winter Olympics? Right now, you're aware of the sport curling. It's an Olympic sport. This is the sport. Yeah, they have these kind of cases, right? They're pretty much stones actually, and you have people sort of guiding it through the thing. You have a bullseye. This is sort of how it works. It's actually a pretty interesting sport. Anyways, but point is that I'm asking this question: hey, which athletes won the gold medal at curling at 2022 Winter Olympics? I'm asking this particular question here. And it replies like saying the gold medal in curling at 2022 Olympics was won by Swedish men's team and the South Korean women's team. Let's actually check this, right? Let's actually check this out. So 2022 Winter Olympics. Let me actually Google this curling. Let's actually go here. And if you look at it, Sweden won the gold medal, and Great Britain won the silver medal. Canada won the bronze medal. But if you actually come back and if you look at it here, the gold medal in curling at 2022 Winter Olympics was won by Swedish men's team and the South Korean women's team. Well, the Swedish men's team, probably not bad. But if you look at the women's one, it says South Korean women's team had won the second. Well, that's actually not true. It's actually Great Britain that had actually won in women's. So what happened here? Of course, the model was wrong. Do you agree with it? Do you agree that the model made a mistake here? Yeah, of course it made a mistake, right? So why did it make a mistake? Well, there are two things here. The response seems like super confident. but it actually made a mistake there. It's a factual error. Grammatically, spot on, right? From a language standpoint, spot on, but factually incorrect. Why is that the case? Why do you think that happened? Model is not trained to remember facts, only make predictions on language. See, you need to understand one thing, that large language models are language models. They are not quiz masters. Large language models are not fact books. Large language models are not. It's not a memory bank. It's not a question bank where it has answers to all questions that you want. That's not what a large language model is. A large language model, an LLM, is a language model which is very, very good at understanding language. So if you're going to ask it questions as if it were like the most intelligent person on the planet, it will make mistakes. It will absolutely make mistakes because you don't know how it is actually making up that answer. But why did it get the right answer here then? Even here, it got half of the answer right. The other half, it made a mistake. Why is that the case? Well, the reason for that is actually pretty interesting yet simple. Right? So the reason for that is that these models, right? So whatever models that we're talking about right now, so whatever models that we're talking about so far, right? So your large language model. So let's take, for example, the GPT 3.5 model. Now, the thing about this particular LLM is that this model, because it had to be trained, right? This was, of course, trained on a lot of data, right? This was trained on what? On Common Crawl. This was trained on Stack Overflow. This was trained on Wikipedia, and so on and so forth. Right. So when it was trained, remember what was the task that it was trained on? This was trained to always predict the next word. Right. It was trained to predict the next word. Right. So the model is always trying to predict the next word. So in the process of trying to understand the language, your GPT 3.5 model, because it was also trained on Wikipedia, it was also trained on it. It learned, it sort of became a muscle memory for the model to predict certain facts, right? It understood, or it was not intentional, but because it was always trying to predict the next word, in the process of always trying to predict the next word, it so happened that it now is able to actually predict sentences which almost look like facts. So it actually comes up with sentences as outputs which look like facts. In certain cases, they are facts. In certain cases, they are not. In most cases, they're actually not facts. But see, you need to understand that the model is merely trying to predict the next word. That's it. Given any particular set of questions, it's merely trying to predict the next word. So which is why here in this particular case, it actually made up this response merely from the memory that it had. Now, the unfortunate reality, my friends, is we don't know how that memory came into existence. Did that memory come through Wikipedia? Did that memory come from some website in some website in the internet? Did that memory come from some book? Did that memory get influenced by some research paper? Did that memory get influenced by some news article? I have no clue where that memory has actually come from. So for that reason, I will never trust, or you also should never trust, large language models' innate ability to just respond back to answers, like the raw ability to respond back to answers. Hence, what do you need to do? By the way, this thing that it's doing here, another word for this is referred to as, any idea? Hallucination. It's called hallucination. Exactly like your commonplace word hallucination. He's just hallucinating. He's just coming up with things that may or may not exist. Right? You would see people hallucinating at times, right? Like how people just say, there's something in my room. You're probably high on some weed or some drug, and then you're probably making up stuff. Just that way. The model is also hallucinating here. The model is also high on some kind of a mushroom, I'd assume. But the point is that the model is also making stuff up for you that seem absolutely right, It's quite likely that's not the case. Then how do you control for this? How do you handle this? Well, there are some interesting ways to handle this, some very, very cool ways to handle this. Let's talk about that. So if you actually go down, this is where prompt engineering comes into the picture. You ask it nicely, right? So for example, you simply tell it that if you don't know, just say, I don't know. Don't make stuff up, right? Just be very explicit. Just be very, very explicit with the model to not make things up. For example, I'll ask the same question. You answer questions about 2022 Winter Olympics. Answer the questions as truthfully as possible. And if you are unsure of the answer, say, I don't know. And now you ask the same question, and it actually responds back saying, sorry, I don't know. It just actually comes back and says, boss, I don't know. I don't know what the answer to this question is. Now it's not making things up. It's not just randomly predicting words, but it really sees this as an instruction and it says, you know what? Great. I'm going to shut up. I'm not going to say anything. Does that make sense? It's now these instructions that are sort of guiding it to not make things up. This, my friends, is referred to as prompt engineering. This is all prompt engineering. You're essentially asking the model to operate a certain way. You're instructing the model to operate a certain way. All of that is referred to as prompt engineering. This is one of the most simplest ways of managing prompts. There are a lot of different ways of handling prompts. We'll discuss some of those, but this is one of the ways of how you could get the model to not make things up. So now then, of course, it said it doesn't know. But then one thing we know is that the model can actually do question answering very, very well. If I give it a piece of, we remember yesterday we did that, right? So I could just pass it a paragraph and I could simply ask it to respond back to questions, right? I could give it a paragraph and I say, hey, look, you don't use your brain. You just use your ability of language. You just use your ability of inferring from language. I will give you a paragraph. I will give you a question. You take this question, you use your reasoning abilities and try and answer that particular question from that paragraph. We did this with generative question answering. So I will just ask it to do the same, right? Imagine, let's actually go back here to this page, right? To the curling at 2022 Winter Olympics page. If I actually take this complete page, if I just simply copy this complete page, right? And if I go back here, right? What I could do, I'm essentially taking that complete page and I'm simply pasting it here. I'm taking that complete page and I'm just simply pasting it here. I'm taking that complete Wikipedia page, this page that you see here, all the way up until the end here. And I'm just pasting it here, right? So essentially I've provided all of that as some kind of a context. I'm saying, hey, this is your paragraph now. Your paragraph is not 100 words or 200 words, but now it's actually this big. This is all your paragraph, right? Now I'm saying, hey, look, you have this paragraph with you, right? Now I'm simply saying, use the below article on 2022 Winter Olympics to answer the subsequent question. The article is here, whatever the article that I shared a while earlier, right? And I'm going to pass a question to it. And I'm going to pass a question to it. Which teams won the same question like in the past? I have this paragraph, I have this paragraph. And then along with this particular paragraph, I have this particular query. And now I'm simply going to ask it to respond back to this particular question, right? So let me just execute this. So now this is my question. This is my paragraph. Use the below article on 2022 Winter Olympics to answer the subsequent question. And I have this whole thing over here, right? Now I'm going to do the same. I'm going to now I'm going to use this complete query. I'm going to pass it into the same model, right? Same query again, same OpenAI call that I'm making here, right? And I'm asking it to respond back. Remember, I just copy pasted that complete content here. I did not pass the link or anything. I just copy pasted the content from this Wikipedia page. Basically, nothing. Basically, simply, I just went in here, copied the whole damn thing, just from here all the way up until here. Copy, come back here, code, paste. That's it. This is all that I did. And I've taken all of this in one single variable. Yeah, sorry, back here again. Yes, I've essentially taken the whole thing into one variable. Now I'm simply attaching that particular variable here And then I'm simply asking this particular question. So it's like a paragraph that I'm providing. It's like a passage that I'm providing. And I'm saying, hey, do reading comprehension on top of this. So now when I ask it to respond back to the same question, like what I do here, now look what it does. It says, the teams that won the gold medal in curling in 2022 Winter Olympics are men's curling Sweden, women's curling Great Britain, mixed doubles curling Italy. So now if you actually go back here, verify that from this, verify that from the Wikipedia article. Yeah, men's curling Sweden, women's curling Great Britain, mixed doubles curling Italy. Bang on. It got the right answer. So what did it do? I am now asking it not to respond back from its memory, but rather I'm getting it to ask from a paragraph that I pass it. And I'm saying, boss, you know what? You don't use your knowledge. You don't use your memory. Use your ability to read language. And what I'm asking it to do is I'm saying, hey, use this passage, take this question, and then respond back to this particular question from this particular passage. So here, it's actually not doing extractive question answering, it's doing generative question answering, because this kind of a response doesn't exist anywhere. It actually made up this complete response and it gave it back to you. So basically it has generated this complete response for your consumption and it responded back. Okay. I think there is, okay, let me try and make this very explicit for you all. So what did we do here? We use the scenario 1. We use the raw GPT 3.5 model, right? This is the model. And in this case, I did not pass anything to it. I just simply asked a question and the GPT 3.5 responded back to this particular question. It gave me an answer. Now, when I look back, this GPT 3.5 model, when I asked this particular question, the question was on curling, right? So who won the curling gold medal in 2022 Winter Olympics, right? 2022 Winter Olympics curling winners is what I had asked. That was the question. And then it kind of responded back to this particular question with a certain response. First, in the first go, this response was it accurate or was it inaccurate? In the first go, this response was inaccurate. It made a mistake here in the first go. Why was it inaccurate? It was inaccurate because the model here was trying to come up with it was not referring to any kind of a knowledge base. It was just trying to come up with it from its own understanding of this particular question. It was just merely trying to respond back to this particular question from what it was trained on in the past. And even if it was trying to predict on what it was trained on, it does not have the ability to memorize information. So it is just trying to only predict the next word, the next most appropriate word. That is why this probably did not came out to be the best response over here. So it ended up hallucinating. What did I do then? Scenario 2. Here, what I've done is we took the model, the same model again, the same GPT 3.5 model. In this case, I passed 2 things to it. I passed the question. Along with the question, I also passed some context. This context is simply nothing but a passage or a paragraph of, this is the Wikipedia article, and it's the same question that I had passed here, the same exact question. Along with the question, I also passed this context. Now what I'm asking GPT 3.5 to do is, hey, look, don't over-engineer. Answer this question from the Wikipedia article that I have provided. Now it came up with a response, and this response was more appropriate. The reason for this response being more appropriate was because we guardrailed the GPT 3.5 model to only answer this particular question from the context that we provided, from the passage that we provided. For that reason, the response here was appropriate. The point is that if we are able to provide the right kind of context, what we realize is if you're able to provide the right kind of context here, right? If you provide the right context here along with the question is more often than not answered appropriately. The answer is appropriately is pretty decent. So the magic is in ensuring that you always provide the right context. But the problem is, how do I know what context to provide? For example, in this case, if you think of it, because the context is about 2022 curling, Winter Olympics curling, it was able to respond back. But if I ask this particular query, hey, same question, but instead if I provide the complete Wikipedia corpus to it, right? Instead of just passing just one article, can I pass the complete Wikipedia corpus to it? Is it possible? It's possible. But is it feasible? The answer is no, not the API. It's possible, but it's not feasible beyond a certain point. Why? Because there is a limit to the total number of tokens that you can pass in a given prompt, right? So if you go back here, my friends, so if you actually go back to these models here, so if you go to the models, right? So if you take any of the GPT-4o models or 3.5 turbo models, the context window, you see something called as context window here? The context window is 16,385 tokens only. The output size is only 4,000 tokens. Maximum output is only 4,000 tokens, right? If you go for something like a GPT-4 turbo model, the context window is 128,000 tokens, right? So, I mean, just to kind of give you a sense of what 128,000 tokens mean, how many books is... Yeah, so it's going to make some assumptions. It'll come back with you on this. So approximately 128,000 tokens is around 96,000 words. And if you assume 96,000 words as 350 words per page in any book, that's approximately 274 pages, which is approximately one book, right? 270 to 300 book pages. So if you take a novel, for example, which is 200 pages long, so you're talking about like approximately around what, slightly above one complete novel, so to say, 200 to 300 pages. So you could at any point in time provide 128K, which is essentially one book, and you can ask any questions to it. This is a novel, right? This is a small book that I'm referring to. It's not a big book, because it's assuming 350 words per page, which is actually slightly on the higher end, but it's okay. It's like a pretty decent novel, so to say. The O models that we have right now, right? So the GPT-4o models also have 128K in tokens. They are all 128K tokens. They can actually also respond back pretty heavily, right? 32,000 tokens and stuff like that. Point being that these models have slightly getting bigger now. But even if at that point, what we are saying is you will only be able to use, right? You will only be able to use maybe at the max one book here, right? And if I were to ask, how many tokens does Wikipedia have? 6.6 million articles totally, and 4 to 5 billion words, which is approximately around 6.6 billion tokens is what you're referring to. So 5 to 6 billion tokens is what Wikipedia has. And we are talking about what? We're talking about 128K tokens. So now you know how the difference is, right? You know how big the size is. You now know how to benchmark it. On one side, you're talking about 128,000. On the other side, you're talking about 5 billion tokens. So you're barely talking about what? What is 128K? What percentage is in 5 billion? So it'll probably come back with a response on this as well. It should give you a percentage, approximately 0.000 whatever percent. 0.00025% of 5 billion. That's hardly anything. So that's the amount of context that you can only pass in a given call, in a given prompt. Do you understand the complexity here, everyone? Do you understand why you cannot pass the whole Wikipedia corpus into this? Then the question is, how can I build a universal chatbot? How do I build a universal chatbot? Something has to change. what do I need to do here in such a way that I don't see the need of passing all of the context. So I'll give you a small idea here. Even if you train the model, one thing that we know, Mir, is that you can train the model, but the model again might not remember, right? You can fine tune it. That's one possibility. If you have enough data, you can of course fine tune the model, but there are better ways to solve for this. So from here, there are 2 to 3 ways to solve for this. Number one, so how can you, so here, I'm going to actually talk about one after the other. So enriching the inputs to a large language model. How do you enrich the inputs to a large language model? The first step is by prompt engineering, right? In the prompt engineering, what are you doing? You're essentially taking a question, you're passing a question, and you're passing a piece of context here. So as I said, the first step here is about prompt engineering, is to make sure that you ask the right question. Along with that particular question, you also pass a little bit of context, right? And this context is a simple paragraph, right? And you manage the whole the question and the context combination within the prompt itself, right? The most simplest way of doing this, which is what we were doing so far. But things start getting a little complex after this. Why? Because the size of the context at times is very hard for us to manage. The size of the context could become actually so large that it becomes almost impossible for us to control. And for that reason, right, we need a slightly different technique, right, to be able to do this. What do we need to do in this particular case, right? So the thing that we need to do in this particular case is called as retrieval augmented generation. So this is actually very similar to basic prompt engineering, but it is slightly different than that. And it is very much like prompt engineering, but it is slightly different than that. What do you mean by it? So what we do here is you take the question, right? Whatever question you have, and then you try to find a way to pass the right context, right? You do the same. At the end, you pass this to the model, but how do you exactly get the context? How do you exactly get the right context is where the magic is. So what you do in the case of retrieval augmented generation is you may have a large corpus of data under the hood. You may have a huge corpus of data. You somehow find a way, given this question, you try to find the relevant chunk of the context that needs to be added here, right? There is a small technique that we follow wherein given a question, not all the corpus is important. Maybe there are certain parts of the corpus, meaning the answer to this particular question may lie in certain areas, right? Maybe it's here, maybe it's here, maybe it's in some other part of the document. So you only extract that chunk of that particular corpus and then add it in this context. That's how you basically create the context, which is why the context is based on retrieval to start with. So you retrieve the context and then you do the generation. Then you basically try and do the generation or generative question answering. So the generation is augmented by retrieval. So it is retrieval augmented generation because you are generating basis a context which was retrieved from a large corpus. The question is, how do you retrieve this? How do you know which parts of the corpus is the relevant question, relevant part of that, or the relevant chunk from the existing corpus? Well, we'll talk about that. That's where we'll be spending majority of our time in the next few minutes. The third approach to be able to do this is referred to as fine tuning. Fine tuning is like your fine tuning, is like every other fine tuning, right? Here, you don't need to pass the context. The hope is you take the model, whatever model you have, and then you take this complete data, assuming you have enough amount of data, you take that complete data, you pass into the model, you train the model or fine tune that particular model, right? And then use this model for any kind of direct question answering. Because the model has been fine tuned on your data, you could just do straightforward question answering after this. Just to let you know, what has often been very, very successful, as I said, is your prompt engineering and your RAG approaches, your retrieval augmented generation approaches have often been very, very, very successful. It has been a lot more easier for people to control these than this. I'm not saying fine tuning is bad, but in the case of large language models, fine tuning is a tougher battle to fight. Okay. For that reason, we don't simply just go down the fine tuning part straight away. We start with prompt engineering, we then go into retrieval augmented generation. Okay. Now let me talk to you a little bit about what RAG is, what retrieval augmented generation is. By the way, a very common terminology or an acronym for this is RAG. We use the acronym RAG to refer to retrieval augmented generation. Now let's talk about how RAG actually works. RAG is actually pretty simple. As I said, what you do, and hear me out. So imagine you have a question. The question is, who won the 2024 T20 Men's World Cup? Right? That's a simple question. Who won the 2024 T20 Men's World Cup? Men's Cricket World Cup. Let's be more precise here. Right? That's a question that you have. And let's say you want to somehow answer this particular question. But to be able to answer this question, you of course have picked any kind of a large language model. Let's say you've picked any of your GPT models to start with. You pass the question into the model. But before you actually pass the question into the model itself, what you do, and let's say you have, let's say, the bunch of Wikipedia articles. So I'm going to try and depict your Wikipedia articles for a lack of a Wikipedia or let's say some kind of a corpus, right? Corpus so big that it is not easy for you to simply stuff it into the prompt itself. It's a fairly big corpus, right? So, and I'm going to represent it slightly differently here. And let's say these pieces that you're seeing here, these chunks that you're seeing here, let's consider them as articles, right? So this is Article 1, Article 2, Article 3, Article 4, Article 5, and so on and so forth. You may have n number of articles over here, doesn't matter. So now what you do, and there is of course a lot of text in this. Right? This is a lot of text. Now you have this particular question. So what you do with this question is, of all the articles that are there over here, there might be n different articles over here. Not all of the n articles have to do with Men's Cricket World Cup. Some of them may be about football, some of them may be about golf, some of them may be about terrorism, some of them a bunch of different things. So the first step is, there's no point in me trying to search for this response throughout this document. So somehow I need to find the relevant chunks of these articles which are useful for me to answer this question. How do I do that? Well, to do that, what we are going to do is something very interesting. So we're going to take this question. Okay, we're going to take this question. We're going to pass this question into the large language model, right? And what we're going to do, right? I'm not going to use the complete large language model. If you remember earlier, a large language model is simply nothing but an encoder-decoder architecture. So you have an encoder, you have a decoder, right? You can essentially take the question, convert this into an encoded representation, or any input can be converted into an encoded representation. Do you agree with it, everyone? Then you pass that encoded representation into the decoder, pass an input, and then this will start spitting words. That's how the encoder-decoder architecture sort of works. So what I'm going to do is I'm going to just pass this question into, instead of calling it an LLM, I'm going to simply refer to this as an encoder model, right? I'm going to pass this into an encoder model. What does an encoder model return? When I pass a piece of text as input, what does the encoder model return? It returns an embedding as an output. That's the first thing. So I pass this question into the into the encoder model. So I get a question embedding, right? A fixed length embedding, right? I think in the case of the GPT models, it's I think 3000 long vector or something. I'll confirm, but I think it's a 3000 unit length vector or something. But whatever, a fixed length vector is what you're going to get. Lot of numbers, 2.35, 5.28, 5.28 minus 3.65, and so on and so forth. You're going to get a lot of numbers over there, but basically a vector, a fixed length query embedding is what you're going to get. Now, do you agree that if I pass this corpus also into this encoder model, do you agree that I can also convert this into a corpus embedding? For every article, do you agree that I can convert every article into an embedding? So I can have something like, so I could have something like A1E, A2E, A3E, A4E, and so on and so forth. So basically, every article could also be converted into an embedding. So same corpus that we see here could be also converted into a fixed length embedding. Now, what can I do? Now, can I take these embeddings, right? And if I compare this particular question, I'll just repeat so far before I go any further. I'll just repeat until this point. What did we do? We took the question, passed it into an encoder model, converted that question into an embedding. We took the corpus, passed it into the encoder model, article by article, I created an embedding for each article, right? Now, if I want to find articles that are relevant to this particular question, what can I do? If I compare this question embedding with this article embedding, do you agree? How can I compare? How do I know? How do I find similarity between any two vectors? Not correlation. Cosine similarity. No more common words. We'll look at cosine similarity. There's no words anymore. These are numbers now. These are numeric embeddings now. So you find cosine similarity here. Right? You find the similarity of that with this, that with this, that with this one, the same one with this one. You're going to get defined cosine similarities. From that, if you know, and of course, you will do this for all the other articles that are there here. If there are n articles, you will of course do n comparisons. From that, if let's say any article and query comparison, or rather has a very high cosine similarity, what does that tell you? If let's say this article and this question have a very, very high cosine similarity, what does that tell you? That this article may have something something relevant to the question. I'm not saying the answer may be there, but something relevant to that particular answer may be there in that particular question or in that particular article. So what I can do is, now that I've compared the similarities, I can then only retrieve the ones that have, let's say, a similarity of greater than 0.95. If I say, hey, you know what? Only return those articles which have a similarity greater than 0.95. So what will happen? Now, can I filter down if I have, let's say, n articles here, right? If I have n articles here, can I filter that down to maybe like 5 or 6 articles? So as an outcome, I might simply be left with article 1, article 3, maybe like a bunch of other articles. Now, what do I do after this? So now I know that the relevant or this question, there are some relevant documents that in this particular corpus that are relevant to that particular question. And now I've identified article 1, article 3, whatever. What can I do now? I extract. What do I do from here? So now what I do is, now I say, okay, now I know that these article and this article have relevant information, associated to this particular question. So what I do is, now I construct my prompt. Now let's construct the prompt. How do you construct the prompt? So now you take the question that you have, which is the initial question which you had here. And then for context, what do you pass? You pass all of the raw information from article 1 and article 3. You don't pass A1E and A3E. You pass A1 and A3. You pass A1 and A3. The actual articles itself you pass. You create this prompt now. You append article 1 and article 3, and then you pass them as one large paragraph or one large chunk of text. You're saying, hey, now you answer this question from this particular article, from this context. What do you do after this? You pass this to the LLM. You pass this particular prompt to the LLM. No, you don't need to decode the article. The decoded part of the article is already here. The raw article is here. You don't need to decode anything. You are simply just trying to extract the similarity with the encoder model. That's it. Once you know which articles are similar, that's it. This part of the job is done. Now you've identified that A1 and A3 are relevant. So you take the A1, A3 articles along with the question, and the A1, A3 articles means that this is a small piece of text. So what can I do? I can take the A1 article, the complete article, A3 article, complete article, combine the two of them into one large article, and then combine it with the question and pass it to the LLM and say, hey, LLM, now go ahead and answer this question for me. Now, instead of looking at the complete corpus, my large language model will only have to read across these 3 or 2 articles that I have passed. Now, do you agree that your LLM will be able to answer it from here? From here, it is the same as what we did earlier. From here, it is the same as this one. We are just using this whole technique to filter, to retrieve the relevant question, the relevant articles. We're not doing anything else beyond that here. This is time saving and chances of getting accurate responses are higher. Exactly. And it is cheaper because you don't need to pass the complete corpus. You only pass the relevant articles into the model. Thereby, the cost is also cheaper in this particular case because the number of tokens are smaller. Now, my friends, this is exactly how ChatGPT works. This is what ChatGPT does. When you ask a question to ChatGPT, what does ChatGPT do? Basically, ChatGPT does something very similar to this. It takes a question, finds the relevant pieces of information behind the scenes that it needs to put together to respond, extracts all of it, summarizes it, and then takes a question, takes the article, and then passes it into the LLM to extract the final response. So ChatGPT is not just a model. ChatGPT is a system, is a product. ChatGPT is powered by the GPT models behind the scenes. ChatGPT is much more than just the large language model. Yeah, man, that's it. So instead of putting 0.95 over here, put 0.98. Or maybe just say, look, I'm going to pick the top 3 articles, top 3 chunks. There is a concept called as chunking, which is essentially taking the piece of text and then breaking it down into equal sized pieces. We'll talk about that in a few minutes, but you'll have to make a trade-off. Either you pick a fewer articles, or you pick part of the articles, or you pick maybe use a larger model. Like for example, in the case of something like Gemini can have 1 million tokens. Yeah, 1 million tokens also is not a big deal now, right? 1 million tokens is what, 10 books. 128 tokens is one book. 12 million tokens is 10 books. 1 million tokens is 10 books. That's hardly anything. No big difference. But you get the point, right? You get what I'm trying to say. So the thing is, you will have to make a trade-off somewhere. I'll show you how to do that as well. But this, my friends, is retrieval augmented generation. Whatever we just did is retrieval augmented generation. This is RAG. Okay. Now, let's actually take a look at the example. Now, let's actually go back here. Let's take a look at this example. Let's see how we could do RAG. So, in this example, what we are going to do, so this is, by the way, a good, so you have a question, you convert the question into an embedding, right? And then you have a document or a bunch of documents. You break that document down into smaller chunks, create embeddings. From the question, you find the most similar embeddings. You pass that similar embeddings along with the question into your LLM and generate the response. That's basically what it is. So now, guys, let's quickly take a look at how to put this in action. So what we're going to do, my friends, is we're going to extract. So we're going to be taking, there is OpenAI has already provided some kind of embeddings for us, but I will of course show you how you can extract the embeddings yourself as well. Let me actually start with that. let me actually show you how you can access any of the embedding models. So let's look at the embedding models, embeddings. So if you take, for example, this is using, I think this will be using one of the embedding models. So there are only a few embedding models that are there right now. Text embedding 3 small, text embedding 3 large. These are the latest embedding models that they have. What you could do is, this is how you can actually generate. Let me actually copy this for you. So from client.embeddings.create. So instead of earlier, if you remember, what were we doing? We were doing client.completions.create, client.chat.completion. That is what we were doing, chat completions.create. Instead, here what we are going to be doing is we're going to be doing client.embeddings.create, right? And then what we are going to be doing is I can pass any text here. This is, let's say, we'll take the same question from here, right? Where is that question? Let's take the same question. Let's go back here. I'm just taking any question, for example. So if you have this particular piece of text and I'm passing the text embedding 3 model and I'm asking it to generate the embedding for this particular question, and boom, there you go. That's the embedding that's created. So if you actually look at the embedding, so 1536, that's the small model. If you take, for example, the large model, this will be, I think 3000, if I'm not wrong. Yeah, 3072. That's the size of the embeddings that we are talking about over here. Okay. So you could use any of these models for you to, this is how you can actually create the embeddings for any input question you have. Or input piece of text you have, you can simply pass it into the model and the model will generate the embedding for you. So for this input text, this is the embedding that I have, right? What I could also do, embedding 1 is equal to, okay, this is the first embedding. And what I'm going to do is I'm going to also try and create one more embedding here. So I'm going to have this ask the same question slightly differently. Let's see if the in Winter Olympics 2022, who won curling across all formats? Same question, but a slightly different way. So let's create a different, let's create the embedding for this question as well. Ideally, if you think of it, these two embeddings should be very similar. Same question, but written slightly differently, right? And I'm asking, I'm generating the embeddings for both of these questions. Technically speaking, the embeddings of both of these should be very, very similar. So let's actually verify that. Import numpy as np, np dot array of embedding 1 and okay. So I just created both of these into embeddings. So if you look at the shape here, that's the shape 1536. So now if I want to compute the cosine similarity, I can use the from sklearn dot pairwise dot metrics dot pairwise import cosine similarity. Cosine similarity of, I can pass x and y, which is embedding 1, comma embedding 2. And if you actually, this might require me to change the shape. This needs a 2D array, else it doesn't work. There you go. So if you look at the cosine similarity, what does it tell you? It tells you that both of these metrics, both of these sentences have a cosine similarity of 0.85, which is pretty good, right? Which is a very heavy similarity. Same question, written slightly differently, still has the same embedding score. Or so say still has a very, very high similarity score, even though the embeddings themselves are slightly different from each other. Now that we know how to create embeddings, we actually put this as yeah, perfect. So please explain the last code once. Yeah, this is just a second. Let me just ensure I stack everything so that I don't want to. Perfect. Yeah, so the last piece of code here, all that I'm doing is I'm computing the cosine similarity. The reshape here is because the reshape here is essentially to ensure that, so if I don't reshape, or rather, if you look at cosine similarity, if you look at x and y expects n samples and x features. It expects a two-dimensional array over here. For that reason, I need to make sure that I'm reshaping the cosine, the embeddings into two dimensions. One row, all columns. One row, all columns. That's essentially what the reshape 1 comma minus 1 here translates to. Meaning one row and everything else, one row, and essentially the remaining values are essentially like a column. That's all that I'm doing. I'm converting this into a two-dimensional array. And then I'm computing cosine similarity. That's it. Okay. Awesome. So now that we know how to compute cosine similarity, what we're going to be doing right now, or rather, we know how to extract embeddings. What has happened is OpenAI themselves, for a couple of data sets, they've actually extracted the embeddings and they provided it to us. So for example, here, if you take, for example, this one, so they've hosted this pre-processed data set. You can just download it all by yourself. So what they've done is they've taken the Wikipedia page of Winter Olympics 2022. So they've taken the Winter Olympics 2022 page, not the curling page, but the Winter Olympics 2022 page. So this page, they've actually taken this page, and what they have done is they have extracted the embeddings of this particular page all throughout. Okay, they've extracted the embeddings of this particular page. And what they have done is they have converted this particular page into embeddings. So they've taken the page, they've chunked the page, they've broken this particular page down into smaller chunks, right? What do you mean by breaking it down into smaller chunks? Meaning they've taken the complete data set and they have cut the paragraph, that particular page into smaller pieces. And in that process, what they've done, and for every piece that you see here, this is the piece. And what they've done is they've converted this into embeddings. Second, this is the second part, converted that into an embedding. Third part, converted that into an embedding. Fourth, converted that into embedding, and so on and so forth. This is how they've gone about converting everything into embeddings. So if you actually take, for example, this particular data frame, you can just directly load it from here. So it's actually going to try and download this particular page while I speak here. It's actually downloading the CSV file. And once that happens, just quickly show you the shape as well. Taking a little long. It's actually 200 MB file, so it's going to take a little long for it to download over the internet. Once that gets downloaded, I mean, one way to do it is I can do it myself. Like, I mean, we can take that complete page, store it in a document, and then chunk it, and then convert that into embeddings. We can do it ourselves. I'm just using something that's already available. In most cases, you would have to create your own embeddings. Like using this particular piece of code, whatever you've seen here, you will have to create your own piece of embeddings like what I just showed. So the question is, once that is done, that I'll show you the shape in a minute. But as you can see, this is the chunk and this is the embedding. Chunk, embedding, and so on and so forth. So if you actually take, for example, any of these information that you see here. I mean, this is, by the way, any 5 random pieces of text. This is how it looks like. Now what I can do is, of course, we can, of course, you could now start extracting or generating some kind of a, once that particular thing is done, you can of course start using these embeddings for the subsequent steps. Like what? Forget about all of that. Right. So you could start using that for actually generating the responses. What? Like what? So for example, in this particular case, I have created a simple function over here. What this small function does is it takes this data frame, of course, as an input, and it tries to generate the embedding for any piece of text, right? And now all that I'm going to have is for any embedding. The good part is all of these embeddings are already created for us, so I don't have to create these embeddings. But if you want to create it, you can just create it using this particular function. You just have to run this particular piece of code, then you will be able to execute it. The good thing is all of these is already created for us. That's one nice thing for us. Now, what do I need to do once you have every question? So each time we receive a question, we calculate an embedding vector for this particular question using the get embedding function. So we created a small function called get embedding. We'll try to extract the embedding using the get embedding function. For each chunk in our custom dataset, we calculate the similarity of this chunk embedding vector and the question embedding vector. Remember, that's what we need to do. Whatever the embedding vector, question embedding vector, and the chunk embedding vector, we need to compute the cosine similarity. We rank the sections from most cosine similar to the least cosine similar. That's it, right? So that's all embedded in this piece of function. You can actually go through this function. It's very easy to understand. If I'll just explain this to you line by line. This function takes the raw question as the input, the data frame with all the chunks as the input and the embeddings, right? It's asking what function. So it's using the SciPy cosine similarity function. And it is asking me how many top documents should I return, right? I'm saying 100 observations you return as the response. 100 is actually a little too much. You probably like 5 or something is what you would require in most cases. Okay. So now what I'm saying is, hey, given any particular query, first extract the query embedding. So this will return my QE. This will return QE. After that, what am I doing? I'm comparing whatever function I have, relatedness function, which is nothing but the cosine similarity function. I'm taking the row embedding and I'm taking the query embedding and I'm computing cosine similarity and I'm putting it into a simple list. I'm putting this in a list over here. I've written this as a list comprehension. This is written as a list comprehension, which is why it might look a little weird, but it's basically a simple extracting everything and putting it into a list. After that, what am I doing? I'm simply sorting on a key. I'm sorting on a key in the reverse order, right? After that, what do? I just simply extract how many ever top n have been asked. I simply extract those top n pieces of text, right? Pieces of text. This row of whatever the string is, that is what I'm going to return. That's it. That's what's being returned here. That's what this complete function is. Returns a list of strings and relatedness sorted from the most related to least. If you actually take this piece of code and if you execute this for strings, so this is the output, okay? So strings, relatedness, which is nothing but the output from this particular function. So strings ranked by relatedness, and I'm passing a simple piece of text here. And once I execute, it is returning all the outputs for me here. Right? It is essentially displaying, it's printing the whole thing for me over here. It's printing this whole thing, curling at 2022 Winter Olympics, and it is extracting the whole thing for me here. Yeah, after that, very simple. Now I can create a larger function. All that it does is it creates this particular question, right? This creating this large query for me, right? What is it? What is the query? What does the query do? It takes the output from the relatedness functions, right? The strings from the relatedness functions, and it takes one string after the other and it simply stitches it together. It simply stitches it together. Of course, there's a token limit, right? I want to make sure that the tokens are not very, very large. So we try to optimize for the token limit here, right? For example, if I have a token limit of 3,700 or whatever, I try to ensure that the token limit is within that particular budget, so that I don't create like very, very large sets of tokens. Right. Earlier, we were using the GPT 3.5 model just had a token length of 4,096, 4,096, which is why 3,700 is what we were trying to restrict it to. But now you have a limit of 128K with GPT-4o mini, so which is pretty good. So you don't really need to worry about this as much. After that, you just create the query: which athletes won the gold medal at 2022 World Cup? Winter Olympics. And then if you look at the question, it's not just the question, but along with the question, you have all the articles also over here. Where did we get these articles from? Where did we get all of these articles from? From Wikipedia, of course, but those were the relevant pieces of articles that we got from the strings ranked by relatedness function that we had created earlier. And that's it. Now you simply ask the question. It returns the response. Your questions are about 2022 Winter Olympics. And then you simply ask the question. Whatever message you have, you simply pass that particular query message here, and it generally responds back. It says the athletes who won the gold medal in curling at 2022 Winter Olympics were Stefania Constantini and Amos Mossener from Italy, and the mixed doubles tournament, blah, blah, blah. You have all of that information that is required here, by the way. Perfect. So these are all the outputs with the top 5 outputs only, of course. If you look at the relatedness, similarity 0.879, 872, 869, 868, 867, very, 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 very close. And now, of course, I'm going to simply, and then here, this is the query message, as you can see. And then, of course, once this is done, you can, if you see this particular function, the string relatedness, I'm just going to execute this function. So which athletes won the gold medal at curling at 2023 Winter Olympics? This is the final query that it was able to create. Now this is the final message, which is or rather the function, wherein this is the message, the function that says ask. And now what we can do is we can simply just create the message itself over here. So which athletes won the gold medal at curling in 2022 Winter Olympics? The athletes who won the gold medal are Niklas Edin, Oscar Eriksson. These are the guys who won the one from Sweden in the men's tournament. Yeah. Specifically, so I'm going to say specifically for GBR, let's say what it says. GBR should be Great Britain. So it should specifically return the answer for Great Britain. There you go. Look at this. It understood that GBR was Great Britain. The athletes who won the gold medal for curling, specifically for Great Britain, were these guys. We can actually verify this. If you actually look at curling, we should be able to verify this. For Great Britain, Jennifer Dodge, Haley Duff, Eve Muirhead, perfect. Millie Smith and Vicky Wright. Those are the right names. Perfect, right? I was able to actually respond back to these names here. And if I say, and in men's, let's see what it says. The athletes who won the gold medal in curling for Great Britain when the men's tournament were. Now it sort of, I guess, is making up, because for Great Britain, these guys didn't win the gold. These guys actually didn't win the gold. So now it's making an error, if you see. It returned the right names. It returned the right names, of course, but they actually won the silver. They didn't win the gold. This is a bit of a tricky question if you think of it. All right. But let me, if I rephrase which men athletes, it's making this up. Technically, this is not true. This is inaccurate. They did not win gold, they actually won silver. So again, as you see, there's still some scope for us to ensure that either the parsing is done properly, or let's say we pass the right pieces of information and stuff like that. But anyways, as you can see, there's still some scope for us to improve the quality of the responses here. But anyways, I hope you understand how the retrieval augmented generation part sort of works in this case. Let's talk a little bit about the good and the bad of this. Okay, let's talk a little bit of the good and the bad. What is the good? What is the bad here? The good is that you're able to get the job done. The bad is that this is complex, right? The code is a little confusing. I'll just give you a high level flow of this particular code, right? Let me just open OneNote. I'll give you a high level flow of this particular code, and that should already give you a good amount of understanding around how to go about managing this. So the code goes this way. So you start with something. So as I said, step 1 is for us to compute embedding of input query, right? Step 2 is compute similarity of your input query queue with the rest of the corpus, right? Step 3 is pick the top n, the n is your choice, top n most similar chunks from corpus, right? Step 4 is append all the similar chunks into one large string. Step 5 is pass this string as a prompt to OpenAI or any LLM to summarize, or actually to answer as a prompt. Actually, let me just erase this. As a prompt along with original question to answer, right? Pass the string as a prompt. You need to pass this particular prompt to an LLM. That's it. These are the 5 steps, guys. If you're able to do these 5 steps, you're done. So in our setup, this first step in your code, this is done by the get embedding function. This is the get embedding function. The compute similarity of questions with the rest of the corpus, pick the top most similar chunks from the corpus. This is done by strings by relatedness or something, as that's the name I'm assuming. I just want to confirm the name of the function. Strings ranked by relatedness. There you go. Right. And then this one is done by the query message function.
which basically takes this as the input. This one takes this as the input. And then this last one is done by the function called ask, which takes this as one of the inputs. That's it. Those are the 4 functions that we had created. So here are the 5 steps that I just spoke about, everyone. So step 1, compute the embeddings of input query or question that you plan to answer, right? That's the first one. The second one is to be able to is for us to be able to, is to compute similarity of a question with the rest of the corpus. Rest of the corpus, that is being done by the strings ranked by relatedness function. Step 4 is append all the similar chunks into one large string, that is the query message function. Step 5 is pass the string as a prompt to an LLM along with the original question to answer. That's the ask function. These are the 5 steps that we have. These 5 steps are covered as a part of 4 questions. The corpus here, my friend, is nothing but the pandas data frame with all the embeddings. Whatever you want to use to respond back to the questions, this is the pandas data frame with all the embeddings that you have. Now that we understand this part, now that we found this part and we understood this part, let's now go back. By the way, I've switched my screen to code again. I've switched my screen to code right now. Let me know if you're all able to see it. No, I switched to the VS Code right now. I just want to be doubly sure here. I don't want to. Okay. So if I were to put all of this code together, very simple for you, for all of you to use. All right, let's just go here. Import pandas as PD. I just want to quickly copy some of these functions. This is the strings ranked by relatedness function. I'll just copy all of that code at one place so that it is easier for you to understand. And then I just want to copy a couple of others quickly. And just one last part, which is nothing but the client. And the definition of an embedding model. And that's it. So I need to just define the embedding model, whatever is the embedding model. In this case, the text embedding 3 small or whatever it is. I think the model that's actually being used is, I think, not just this. I think the model that is probably being used is the, let's use the ADA 002, which is slightly an older model. Okay, awesome. So that's it, guys. So this is essentially your complete code. That's it. So the get embedding, and I think we need to have one last function, which is nothing but the ask function. Let's just get the last function, which is the ask function. Where is the ask function? The query message is here, and we need to get the ask function. That's it. So that's it. That's your code. So this is the get embedding function, and as you can see, the get embedding function essentially is the function that we have for computing any kind of the get embedding function essentially is the function that we have for any kind of computing the embedding. The strings ranked by relatedness function is the function that returns the list of strings and relatedness score, sorted in the most related to least, and you can also pick the top n. The ask over here is the function. I think we're missing one function here, which is the query message function. Where is the query message function? And that's it. That's the query message function, and that's it. This is the query message function, which is essentially going to compute the query message for you. And then last but not the least, this is the ask, which is nothing but the function that takes the query or the complete message, organizes it into this particular format, which is the role. So you answer questions about 2022 Winter Olympics, and then you put all of that message over here, combine all of it, and then write the response back. So that's how your complete code base sort of looks like. This is how you do retrieval augmented generation using using the OpenAI models. But as you can imagine, which is the point that I was trying to get at, this is a lot of code. You see the screen right now, which is, I'm assuming you're able to see my code, which is essentially the retrieval augmented generation code. And this code that is currently all about how you can create a simple retrieval augmented generation flow as such. The problem with a setup like this is that there's a lot of code, tough to handle. How else can we handle this? How else can we solve for this? Well, that's exactly where we will introduce ourselves to something called as LangChain. What is LangChain? If you remember, if you go back to a couple of sessions, we spoke about a concept called as LangChain, which is nothing but a platform or a middleware that helps you answer, that helps you sort of abstract a lot of the code that you would have had to write if you are directly interacting with OpenAI. So you can have like an abstraction library that does that helps you interact with the underlying OpenAI models, but with a much smaller much smaller pieces of code, so to say, shorter pieces of code, so to say. So let's talk a little bit about how LangChain is set up, right? So let me quickly introduce you to LangChain, and then we will take you from there. Let me just let's go. LangChain. Let's look at LangChain. So what is LangChain? I'm assuming you can see my LangChain website, right? So I open the LangChain website right now. I'm hoping you're all able to see this. So if you look at the LangChain screen, so today what you have is, what you see here is LangChain is essentially like a company that is like an organization that does like a lot of, I mean, as you can see, they do a lot of cool stuff. If you look at their products, you have three specific products, something called as LangChain, LangSmith, and LangGraph. We'll come to LangGraph in a minute, but let's talk about LangChain to start with. What is LangChain? So this is essentially an abstraction library. It's a Python library that helps people build LLM applications, right? So apps that sit on top of LLMs. So what are the things that LangChain provides? LangChain provides something called as vector stores. It gives you some way to manage prompts. It gives you a very interesting way to load documents. It gives you an interesting way to access models. It gives you an interesting way to access tools. It gives you access to text splitters, and so on and so forth. The point being that LangChain here as of now gives you sort of a very, very easy to access way, an easy way to access all of these different components that you see on the screen. How do you do that, right? So as I said, LangChain is essentially a very, very simple library-based setup, right? For example, as of now, if you observe here, what you see is, and I will of course get into the details of the library itself. I'll walk you through how you can use all the different components in the library. I'll show you the documentation and stuff like that. The point is, you could sort of use the LLMs to build very, very cool RAG applications, retrieval augmented generation applications, by tapping into multiple types of search engines, right? So you can connect to internets, you can connect to a bunch of different places that will help you access all of this information. Again, with very few lines of code. The best part is all of this is very, very few lines of code. So let me quickly show you what I mean by all of this. Let's actually go to a quick piece of document. Let's go to LangChain, the documentation. This is the LangChain documentation. This is an open source software, right? That provides you, that will let you build a lot of these applications, as you can see. If you go to the application, if you go to the LangChain, if you go to the LangChain code itself, right? So you can build a chat bot by yourself, you can build an agent and build a lot of stuff. But let's start with something super simple. Let me actually go back there. Let me actually show you an example using the same setup that we had. Okay, so I'm going to load the same .env. What I have here is I'm loading some stuff. So if there's a library called LangChain Community and LangChain Core. So I'm essentially loading a set of libraries here. I'll talk about what each of this does in a few moments. The first thing, so remember, one of the things that we want to do, of course, in this particular case is same setup as what we had done earlier, right? We want to be able to query against, let's say, an existing piece of document, right? So you have a document and you'd want to query against that particular document. Let's take, for example, in this case, the 2024 Summer Olympics, which is essentially the same kind of query. Let's say you want to query something about the 2024 Summer Olympics. One thing you will have to do here is, if you were to do it earlier, you would have had to, if you remember, what did we do? What did we do here? We kind of copy pasted that complete document as piece of text here. You remember, we copied that complete document and we paste that as text. And then we pass this piece of text as a part of the prompt and then ask the question. Right here, what I'm doing is, there's a very interesting. So LangChain has this loader. It has something called as a document loader. In the document loader, they have something called as a web-based loader. What does the loader do? It takes a link as an input. It takes this particular link as an input, and it actually tries to scrape that particular page and store it as a document, right? So it does all of that scraping for you. It is using something called as Beautiful Soup. A Beautiful Soup is simply nothing but a library in Python that does web scraping. Okay, so it used the web scraping and then it kind of parsed that complete document. So as you can see, that complete document is here for you right now. So what you would observe is this particular document, docs of 0.page content. There are 11,000 characters in this particular thing, right? And then if I just pass, if I just print the first 5,000 characters, this is how the first 5,000 characters sort of look like. Let me just open it here. So this is the first 5,000 characters. These are the first 5,000 characters, right? So let me just go back and show you what I did here. All that I did is I used this simple line of code called from LangChain community import document loaders. So let me actually show you all the different document loaders that are available. Where is the API documentation? So as you see, the LangChain core base abstraction is LangChain community. This is the one where you have third-party integrations, right? Odd kind of integrations that you have. So let me show you the API reference here. So if you look at the API reference here, on the left side, you have text splitters. If we go to community, in the community, you have something called as document loaders. So in the document loaders, you would see that there are different types of document loaders that are available, right? I have Airbyte, Zendesk support loader. I have Archive loader, which is essentially like the loader that you can use for this is a loader that you can use to load any kind of a any kind of a loader, any kind of a document from the archive repository. You can just pass a link and it'll download it and it'll parse it for you. So all of that is essentially all those different loaders that you see are all available over here. The loader that I used for the moment is the web-based loader. So if you see the web-based, so if you see here, this is the web-based loader that I have currently used, right? So the web-based loader here currently loads, if I pass any path, it automatically loads that particular path for me. It completely loads that particular page and it returns it converts it into a document like what you see here, and it nicely keeps it available for itself. Now what can I do with this? I can take this particular document, and of course I can use that for a bunch of different things. I can use that for retrieval augmented generation. I can use it for a bunch of different things, which I will show it to you in a few moments. So what I've been able to do is I've been able to load a simple web page here right now as a document. What I could also do is I can instead this is an archive loader, and all that I can do is I can just use this. This is the archive loader, and you can look at anything that goes into this. Sorry. So if you look at the archive loader, I can pass any kind of a loader into it and it will nicely load this for me. As you can see, I can pass a query, which is simply nothing but original PDF format into text, right? So I can just I can just simply load any kind of a loader here, any kind of a an archive PDF. I should be able to comfortably load using this. I'll show that to you as well. So let's actually go back here. So if you see here, all that you need to do is you just have to pass any kind of a document and it should be able to load. Right? You can, as you can see here, you could just load any kind of a keyword and you should be able to load it. Yeah, archive is this, guys. This is the free distribution of all of your papers, right? So whatever you search for here, so you simply search whatever you want to search for here. You say, hey, I want to search for large language models, and it'll give you all of this information, right? It'll give you all of these documents. That is what you can get for. That is what you can simply get here. So what you could do is, let me just go back here, sorry. So what you could simply do is you can simply say, okay, let me just go back here in Python, archive loader, and query is equal to, let's say, I simply search for large language models, and I'm simply going to try and load. I need to install a library. So it's saying that I don't have this module archive here. So I'm just going to install that for a second. The point that I want to show you is what LangChain firstly provides you is it provides a very, very easy interface for you to connect to any kind of third-party softwares or third-party platforms and load this information, right, like in like literally no time. There's another pip install and another module error, pip install fits. I could do the same for Wikipedia as well. I could do for any of the others as well, right? So I'll show that to you one by one. I'll show you some examples on that in a few moments. Let this be done. Just give me a second. I also will have to execute this PyMu PDF. I think it will also ask me for that. This is taking a little longer than expected, but while that comes back, let's go here, right? Let's understand. So now before that completes, let's finish. So now I have loaded this Wikipedia page, right? Then what I have is I have the document. As you can see, this complete document is available. What do I do next, right? The next step is about, hey, now I want to, let's say, do a querying against that particular document. What do I mean by that? So I've taken a piece of document. Let me just go back here, right? Once, if you go back to the, to the RAG code flow, the first step is for us to be able to query against, or the objective here with RAG is for us to be able to query against any kind of a raw document that you have, or a raw piece of document that you have. So now I have this corpus, but just having the corpus alone is not enough. This corpus should also be converted into some kind of embeddings. Remember, in the earlier case, the corpus that you had, right, that was already broken down into sub chunks, and the embeddings are already available for us. But in this case, in most cases, you might have your own document, so you would want to also convert them into embeddings all by yourself, right? So you need some kind of an interface that helps you convert this corpus into these embeddings. So how do you do that? That is where you have this process called indexing. Indexing has a couple of substeps, right? Indexing has two substeps. One is splitting, which is basically taking the corpus and then breaking it down into smaller parts. And the next part is storing it into a vector DB and then converting that into some kind of an embedding and then storing it into a vector database, right? So how do you do that? Here you go. So remember, I'm just using, so LangChain has this library called LangChain text splitters. And all that I'm doing is I'm taking the recursive character text splitter, and then I'm simply splitting this complete piece of text into, or this complete document that I have. Remember the document that I had, whatever documents that we got here, this complete document, I'm breaking that down into chunks of 500 characters each. Remember, 500 characters. I'm taking this complete document, breaking that down into chunks of 500 characters with a chunk overlap of 100 characters. What do I mean by that? The objective, folks, remember, is if you take, for example, let's take this complete, let's take this complete document, let's take this as the document, right? Now, what I'm doing here is I'm taking this document, I'm breaking this down into chunks of 500 characters. So I'm saying, hey, look, starting from here all the way up until here, this is 500 characters. That is chunk 1. For chunk 2, what I could do is I should ideally start from here, and I would go from here all the way up until maybe here. I'm giving that as an example here. But what I am trying to do here, so I would have ideally started here and I would have gone all the way up until here. But instead, what we are saying is, hey, look, if I create mutually exclusive chunks, then there might be some lack of context sharing between these chunks. So if I want some kind of continuity to still persist, right, then I might take maybe from here all the way up until here. I say, hey, this is your first chunk, but I have a bit of overlap. So you see this piece here, this piece of information is available in both your chunk 1 as well as the chunk 2. So this is referred to as chunk overlap. So chunk size is this whole thing. So chunk size of 500 characters, but chunk overlap of 100 characters. Now you may ask, hey, what is the whole point of these 100 characters? Why do I require this? See, the idea of chunk overlap is to ensure that there is some kind of a shared context between both of these. Between two chunks, you don't want to treat these two chunks as unrelated. So to ensure that there is some kind of continuity, you put that overlap so that both the chunks are somehow related to each other. That's the idea of chunk overlap. So by the way, this is done, I think. It says installed, and I think, let's see if it executes this. It might ask for PyMu PDF. Let me just install PyMu PDF. Now, so as you see here, that chunking, yeah, sorry, just a second. Let me just finish this part of, all right, fantastic. So I think this should get executed. So what this is doing right now, my friends, is while that gets completed, what this is doing is it is trying to fetch all of the search results for this archive loader. It's trying to fetch search results of large language models. Why is this useful? See, having these connectors is very useful because I can then build a system that can query against multiple chat systems, multiple bots and stuff like that. I'll show you how all of that can be used simultaneously in a few moments. But these connectors will always help us extract that information and then store them in a simple document. Because if it's available in like a readable document, then you can query against it. You can do a bunch of different things against it. So that's what's happening right now. It's trying to query for large language models and it's trying to load that, basically scrape it and store it in this documents folder, in this documents variable that you see here. Let that be done. It'll be done in a couple of minutes. It should be done anytime soon. While that happens, what is BS4? Samim says, what is BS4? BS4 is beautiful soup. It is a scraping library, web scraping library. Now, here, as you can see, once the once you finish the chunking, that chunks, as you can see, all these splits, there are a total of 239 splits that are created. So we're taking that Summer Olympics 2024 document and we're chunking it. 239 documents are, splits are available. In each split, approximately 481 characters. You will not exactly have 500 characters. You will have approximately 500-ish characters. And then if you move on, then what you can see, and if you move on, once the splitting is done, right? Once the splitting is done, then comes the next part, which is where you're trying to extract it and store it into a vector database. Now, what is a vector database? Now, vector database, my friends, if you remember in our previous example, of where we had a database, where we had the you remember all of these embeddings were extracted and these embeddings were sort of stored in a pandas data frame, right? So you had the chunk and then you had the embedding. Right? It was stored in a CSV file and we loaded the CSV file directly from the OpenAI library. But now this time, remember, you are not only splitting, but once the splitting is done, You're also going to convert each of that into an embedding. Remember, each of that is also going to get converted into an embedding. So you need a way to store this. You can either store it in a simple flat file, or you could store it in some kind of a database where, hey, storing such numbers is easier. So you will store it in something called as a database where you can retrieve these numbers also very quickly. You can do the comparisons very quickly. So that database is referred to as a vector database. Why is it a vector database? Because it is a database where you're storing all of your embedding vectors. It's storing the embedding vectors, right? So it is called as a vector database. So if you come back here, that vector database, by the way, this is also done. So it looks like it has extracted all the documents from large language models. How many has it extracted? Let's see. Bad idea. Bad idea. So that's the size of all the documents that it has returned. We can, if required, maybe look at the top 5,000 if needed for the first document. See, lost in translation, large language models in non-English content analysis. So it has extracted basically, one of the first article, and from the first article it has extracted the summary of that particular article, which is basically the abstract. It brought the abstract of this particular page. There is acknowledgements, there is abstract, and there's a lot of the details. It didn't bring the complete file, but it brought the abstract from that particular page. And if you see, it has so it brought back total 100 documents. 100 results is what it was able to bring back. Now, when you extracted this, we can come back to this. For the moment, let's switch back to the earlier one, which was this one, which is your web-based loader one, right? Let's try and reload this Wikipedia page. It'll, of course, and all of that Wikipedia page is available for you here. This is the Wikipedia page. You can look at the length of the content, the first set of results. Let's split this, right? And then if you look at length of all this, the splits, total of 319 splits, right? The first one has, the first one has a total of 482 characters in size, the first split. Now what I'm going to do, as I said, I'm going to store it in a vector database. How will we store it in a vector database? So as you see, there are different types of vector databases that are available. LangChain also comes with a bunch of vector stores. What are the different vector stores that are available? So Chroma is one of the most popular ones. There are a lot of vector databases that are available. So to give you some examples, you have Chroma, you have, so on the open source ones / in memory, and then there are enterprise ones as well. So you have Chroma, you have something called as Face, you have yeah, I'll give you the enterprise ones. You have Redis, you have the Postgre, VectorDB, Postgres VectorDB. You have the Azure vector search, and so on and so forth. So you have a bunch of in-memory, and you also have a bunch of open source as well as a bunch of enterprise vector databases that are available. For this example, I'm going to be showing you an open source one, right? So erase all drawings. Now, if you look at this here, I'm using the Chroma one. So Chroma dot from documents, and I'm saying, hey, look, I'm passing all of the splits, the chunks, and I'm also saying, hey, look, use an OpenAI embedding model. Which model is it using? It's using the text embedding ADA 002 model, and it's going to convert all of that into embeddings, and it is going to store these embeddings straight into this vector store that you see here. So if you see the vector store, that vector store is already there, right? So vector store dot, and if you want, you can look at add documents, find similarity search. I can get the embeddings. I can get any of the I can get the embeddings. If I want, I can retrieve something. I can also search for specific documents. I can update documents. I have all of these different functions that are available for me over here. So now the first part of it is done. So my corpus has been broken down into chunks, and it has been stored as embeddings for me in this vector database. Now what do? Now I need to compute the embedding of an input query, right? So that's where the retrieval part comes. So the first step is done. The first step of indexing is complete. Indexing has two sub-steps. What are the two sub-steps? Splitting and storing into a vector database. Remember, super easy, just 2 lines of code here, right? Then you have the next one, wherein you're doing retrieval. How do you do the retrieval? Now to do the retrieval, remember, here to do the retrieval, we wrote this massive piece of code, right? We ended up writing this complex function over here, and we had to write a for loop that loops over it and returns the results. Here it's just this, and I'm saying, hey, look, I want to search by similarity and return the top 5 for me. I don't care whatever it is, right? So I'm calling it a retriever, and I'm saying, hey, look, use this vector store as a retriever and retrieve the top 5 for me based on similarity. Okay, and I'm going to say, hey, retriever.invoke, and I'm passing the query, and simply passing the query over here. Where is the Summer Olympics 2024 happening? And if I look at the length of the retrieved documents, there are 5 documents. And if you look at the content, this is one document, this is the 0th document, this is the 2nd document, and so on and so forth. So each of it has different sets of documents, as you can see here. I have a total of 5 documents that have been retrieved. Is this part clear, everyone? So you've indexed all the chunks. You have one question: where is the Summer Olympics 2024 happening? And you simply had to write just 2 lines of code to get everything with a similarity of which have the top 5 results. I'm not using, I mean, you can put a score threshold as well if you want, which will return everything, or you can simply say I want the top 5. Now what? The last part, generation. Super easy again. So I have the retrieved documents. This is one content, one document. This is the 0th one. The Summer Olympics, officially the games, is branded as Paris 2024, where international multi-sport event held from blah, blah, blah. Paris is the host city. You actually have the response to this here, as you can see. And this is in the 0th one, the most similar question. The content is here. Now the last part, which is the generation part. How do you generate? Well, simple, very simple. So I'm going to use the OpenAI models here, as you can see. And I'm going to, all that I'm going to do is I'm going to use this small template, right? And I'm going to pass the context, which is nothing but this retrieved documents. And I'm going to pass the question. So as you see here, this is how I'm structuring this. I'm saying, hey, format documents, take all the documents and simply join them. You see, if you look at this is not rocket science. It has simply taken for doc in, sorry, where is the retrieved docs? For doc and retrieved docs, I'm simply appending everything together over here. So I have the final response. For doc and retrieve docs, I have all of the ones, and that's it. I just simply have to execute this. And I simply have to execute saying, hey, look, or I can just do it here also. However, it doesn't matter. But basically, my point is, you can just combine all of the documents, and then so this pipe symbol. This is basically it's called as an expression language. So it's taking the retriever, it's taking the documents, the question, the prompt that I have passed here, whatever prompt that I have here, and then it is going to simply execute. See, the simplest way to do this is this. Once I get the response here, I found the retrieved documents. So I can take the retrieved documents. Let me actually simplify this way before I complicate it. Yeah, I need to iterate for the content. Oh, completely forgot that. Perfect. Okay, that's it. So this is the final retrieved document. I need to extract the content. So this is the final retrieved document, as you can see here. And all that I need to do now is to take this final retrieved document, pass it to the OpenAI model. So how do I pass it to the OpenAI model? So I'm going to use this simple prompt here. And this is where something called as prompt templates will help me. I'll talk about the prompt templates in more detail in a few minutes. But all that I'm doing is I'm saying, hey, from LangChain underscore OpenAI import, I'm opening a chat OpenAI model, which is essentially a GPT 3.5 or any model that you want. Right? You can pull up a 3.5 turbo model or a 4.0 mini model. Doesn't matter whichever model you wish to. And then I'm saying, hey, look, use the following pieces of context to answer the question at the end. If you don't know the answer, come up with an answer that sounds super realistic. Provide some evidences to make it sound real. So I'm basically asking you to fake it. I'm actually going to remove all of this. And I'm going to say, ensure you only answer basis the information that is available. Do not make up any answer. If you don't know, just say that you don't know. Always say thanks for asking at the end. And of course, you need to pass the context into this particular case. And this context is simply nothing but, in this particular case, so you have this template now. They've created this template. So, and I'm going to simply say, hey, custom rag prompt dot invoke context is what? The context is nothing but your final retrieved doc, and question is nothing but the where is the Olympics happening? So now if you look at the message, here's the complete message. Use the following pieces of context to answer, blah, blah, blah. And then I have the complete context. All that I have to do is I just have to pass this particular message to the LLM that I have created here. So I'm going to say LLM off, and I'm going to pass example message and hope it responds back. There you go. The 2024 Summer Olympics, branded as Paris, were held in France, with events taking place in Paris and 16 additional cities. That's it. Right, so of course you can print a response dot content. That's it, guys. Now, so this is basically like a far more, I would say, structured way of approaching this. Instead of just writing code after code after code, writing super complex code, you could sort of approach the same thing in a much more simpler fashion, right? So without too much, without I would say, I wouldn't use the word too much text, but I would go to the extent of saying without too much complexity, right? Let me just yeah, you can ignore this one. This is it. That's how you do retrieval augmented generation using LangChain. Super simple. Let's go back to this for a second. All right, so I think we spent a good amount of time trying to understand how you could do RAG using LangChain. Now let me actually take one step back, right? And then we'll understand some of the more core functionality of LangChain as well. By the way, I'm hoping you're all able to hear me. Perfect, cool, awesome. So so we looked at this example. We understand how to do indexing, retrieval, generation, and so on and so forth. What I'm going to show you right now is some of the more fundamentals of LangChain, right? So I'm going to spend a little bit of time trying to talk about how LangChain itself works. So let me show you how you can use LangChain, like the core functionality of LangChain. So if you remember, when we were trying to access these models, you remember we had to kind of write all of this code ourselves, right? So we had to create the OpenAI client, we had to tell what model, we had to give the message of the of the system, message of the user. You had to sort of draft it yourself, and then send the question, right? However complex the the prompt is, right, where you are adding some text, you are adding some question, you would have had to do it all by yourself, right? You basically had to shove everything into this. Now that started to sort of become a little complex, as you can imagine, beyond a point. That said, LangChain provides you certain abstracts that can help you access these models in a much more easier fashion. Okay, so how? So let's take a look at it. So you have to install these two libraries: pip install LangChain OpenAI and pip install LangChain. I'm loading these OpenAI. I'm showing OpenAI, but you can fundamentally even load other models as well. I will show that to you. So LangChain essentially uses something called as an LLM chain. A chain is simply nothing but an instance of making a call to LLM and fetching a response back. So if you think of it, you could chain multiple such calls to the LLM. So for example, you take a question, you pass it into the LLM along with, let's say, some context, you get a response. You take that response, you pass it into another LLM chain, and then this time maybe you're trying to, let's say, format it as a table. Then you pass it into another chain where you're probably taking that table and then creating that as a chart. Then you pass it into another chain where you're extracting that and then you're trying to pass it into extracting that chart and maybe writing some kind of a description about it, and so on and so forth. So every LLM call is simply nothing but an instance of this LLM chain in the case of LangChain. Okay, let me show you a simple example. So here I'm saying, hey LLM, and I'm loading this default GPT 3.5 turbo instruct model. it could be any model, guys, right? So that's the model it's currently loading. So LLM is equal to GPT 3.5 Turbo. It's essentially loading this model. And now what I'm going to do is I have something called the prompt template. Right? The most easiest way to use this, okay, even before I show you a template and everything, is I can simply say LLM off, and I can pass a simple string. I can simply say what is generative AI. It'll make a call and it'll respond back. It'll give me a response. Right, and let me show you. That's it. Right. So this is, by the way, I think sort of inaccurate, but it kind of came up with a response over here. Right. So my point is here, it's able to sort of take the generative AI. So I asked a simple question. I instantiated an LLM model, and I'm simply asking a question, and I got a response back. This is the most basic use of an LLM chain. A simple how you could use LangChain. Right? I created the OpenAI instance, the LLM, and I'm simply making an LLM call to respond back. Interestingly enough, by the way, this is simply nothing but a prompt. Right? This is the prompt. Now, this prompt, more often than not, one of the things we've observed is this prompt could have multiple aspects in it. It could have the role of a user, a role of a system. It would have a system prompt, a piece of context, a question, a bunch of different things. So what LangChain has done is they've created a simple template for us. What's that template? So they use something called as prompt templates. Look how prompt templates work. It's actually pretty interesting. So what does a template do? So imagine I have a question like this. Hey, I want you to act as a financial advisor for people. In an easy way, explain basics of financial concepts, whatever that financial concept is. Limit the response to 15 words. So this concept is a variable now. Okay. And what I'm going to do is I'm going to pass this template into this class called as prompt template. It's sort of a constructor, right? I'm simply going to pass this template into this prompt template class. And I'm going to say, hey, look, wherever you see financial concept, that's a variable. That's an input variable for this particular prompt. Okay. So from now on, I can simply say prompt1.format. And if I say income tax, this income tax will basically go and sit there. Yes. So if I simply execute this, I want you to act as a financial advisor for people in an easy way, explain the basics of whatever that financial concept is. And I can simply say, by the way, I can simply say, if I simply say prompt1.format, all that it would do is it would simply just return this income tax as an ask. Right now, this is sort of the most simplest way of using this particular prompt. What you could do is, instead of doing this, so the beauty of this is I can take this particular prompt and I can say LLM of prompt1.format of income tax, right? And it will generate a response, whatever the response is. Why did it fail? Sorry. So it will generate a response. Income tax is money taken away from your earnings by the government. I can also change this to whatever I want. GST, goods and services tax, blah, blah, blah. I can simply do this. What I can also do is use this as a chain, right? I can simply say, hey, look, so whatever I just showed you, here, right? So defining the prompt and then passing this into this, these two steps, right? You could define this as a chain, and I can say, hey, look, chain 1 is an LLM chain. I don't have to just define the prompt, but instead I can simply do it at a slightly higher level. I can say LLM chain, I pass the LLM to it, which is nothing but this one, and I pass the prompt to it. And all that I have to say is I have to say chain dot invoke. So it's as good as doing this, right? So this line is as good as this. These two are sort of the same ways of accessing the whole thing. Instead of you trying to define this whole thing, I can just use it using chain1.invoke. Right? So this concept of prompt templates, my friends, is super useful, because if you understand how this works, then it's super easy, right? So I'll show you another one. Exactly. I'll show you another one where you probably will have something that's a little more complex, but here you go. So I want you to act as a data analyst as good at SQL. You have 5 tables or 20 columns each. Assume entity relationship diagram for sales database. Answer the following questions with an SQL query. And then you pass the question, right? And then you're saying, hey, you've defined a simple prompt template. The template is this. The variable is question. You've defined that. And now you've defined the LLM. You define the chain. Instead of defining straightly passing it into an LLM, you define the chain. Hey, chain 1, LLM chain, LLM and prompt. And you're saying, hey, chain1.invoke. And then you're simply passing this, and it'll execute a response for you. It'll take this particular question, consider this as a variable, put it here, and generate a response for you. That's essentially what has been generated here. Same thing. Okay. Now let's go one step further. Here, of course, you can change some of these models and everything. This was a regular OpenAI model that we have used. What you could also do is remember that you also have these chat models, right? So you could sort of the idea of a chat OpenAI model is a regular model, a regular LLM does not take conversation into account, right? An LLM does not take a conversation. It's a very transactional activity, right? So you take a question, you respond back. You take a question in a context and you respond back. Simple. But in certain cases, you might want to have some kind of a chat setup. So in those cases, you can use you'll have to define the LLM differently. Here, what was the LLM? We defined the regular OpenAI LLM, right? Which was the regular OpenAI class. This was the LangChain class, but this was the traditional large language model class. But now I'm going to use the chat OpenAI class, right? To use this is a chat large models API. So to use, you should have the environment variable. Any parameters are valid to be passed, blah, blah, blah. Right? So I've, let's say, decided to use a GPT-4o. I'm doing this as a chat. So remember, when you pass something to a chat model, you will have to pass a system and a human message, right? You'll have to pass a system prompt, a human prompt, right? So for example, in this place, I'm saying, hey, the system prompt is, you are a very cordial translator. Please greet before. This is a system prompt, and the human prompt is translate this sentence. It's raining very heavily in Mumbai. And I'm saying LLM.invoke, print the response. It responded back here for you. Pretty simple. Okay. Now, how do you do the same for a chat template? How do you do the same for a prompt template, using a prompt template, but for a chat model, right? How do you set up the system and human concept? How do you set it up? But for a but in the case, let's say, of a chat model, well, you define the template. Here you use something called as a chat prompt template, right? So you say chat prompt template from message. So you have to define the messages as you see here. This is how the messages are defined. Human AI, human, blah, 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 right? So system, human, and I'll show you where this is going to be useful. I'll show you a very interesting case where this is useful. So the system saying you're a very cordial translator, please greet before you respond back. You're proficient in English as well as Hindi. Also after the question, also after you respond, share a small piece of trivia related to that particular question, right? Human is going to ask a question wherever. And the human is asking you a question. So I've defined this as the template here. So the template has input as one of the variables. Everything that I've defined in parentheses is a variable. This is a variable. I'm saying, hey, from messages, system, human, this is all defined as a nice list of messages over here. I've defined the chain, LLM chain, which is nothing but the LLM model, whatever model I've defined, and then the prompt, whatever prompt that I've defined, the chat prompt. And I'm simply saying, hey, look, chain.invoke, and I'm saying, hey, the input is translate this sentence, it's raining very heavily. It will not. Yeah, so the input is translate this sentence, it's raining very heavily out there in Mumbai. And I execute. The translation of the sentence, it's raining very heavily in Mumbai, is Mumbai mein bahut tez barish ho rahi hai. Did you know Mumbai experienced its heaviest rainfall during the monsoon season? Blah, blah, blah. So now I'm using the same concept, but in the case of a human AI setup. Now, so I'll show you something interesting as well. So let's say I'll show you where this whole chat templates are going to be very useful. So now let's say you carry this response further. Right? And you also capture the AI response. So the AI response is also what you're capturing. And the response is here. This is the complete response. Okay, so you have the system, human, AI, and then you again have, let's say, so you are essentially embedding that to this, and then you are creating one more. And this is human again. In this particular case, it's an input again. So the human is probably going to ask another question. So you've taken the whatever you have done from the previous step, and then you have added that as a, so this is essentially how you design a chat, right? And you will of course have to automate this. Here I have manually copied the question, the response from the previous step. But as you can imagine, this conversation history will have to be, this conversation will history will have to be automatically updated, you know, step by step. So now this time you ask a question saying, what is it? Now I'm simply saying, what is so special about this city? Now remember something, I am not again saying what city it is. And I'm saying, hey, what is so special about this city? So when I say this, now my model should be able to understand that I'm referring to Mumbai. My model should be able to understand that it's Mumbai. Because I've captured all of this history, it should be able to consider this input over here as Mumbai. So let's see what it does. Just a second. I have not talking here, which is fine. Oh, sorry. There was a comma missing here. That was the issue. There's a comma missing at the end. That was the issue. But anyways, let's go. So now I'm saying, hey, what's so special about the city? Now this time, hello. Mumbai, often referred to as the city of dreams, has many special attributes, blah, blah, blah. And it gave me everything about Mumbai. I did not tell what city it was, but I was able to figure from the chat that I had in the past, right? Because then I can stuff all of this nicely in there, and then I can use these as templates. Moving on. So this is all LangChain, my friends, right? Otherwise, remember, if you were to do it this way, it would have been like super, I mean, it's not that it's complex, it's just that you would have had to mention all of this unwanted piece of code and so on and so forth. Okay, let's move on. So yeah, these are some other examples. So for example, here in this case, I'm providing like a bunch of data, and then I'm telling it, hey, analyze this for me, passing the whole data set to it, and it'll actually try and analyze the whole thing, and it'll respond back. So what you could also do, right? You might have multiple examples, instead of one variable, you may have two variables, right? Sentence and target language. In an easy way, translate the following sentence. I pass the sentence and I pass the target language, and then I have two variables here, and then it can nicely do this for me. So sentence is so and so, target language is so and so, and I pass it into the LLM chain. Or I could do the same using the sit. I could do this. chain2.invoke, sentence is so and so, target language is so and so. I just have to pass it as a dictionary. That's it. Right. And that's it. That's dealing with more than one variable. So if you have more than one variable, you could do it as well. Right. Now, in the cases of question answering, right? So if you're doing Q&A, how do you do it? So question answers is also the same, right? You have a question, you have a corpus, you just have to answer. So it's actually the same setup as two variables. So you have one question, you have one variable, one context variable. You have to solve for this. So text and question, two variables. All that you have to do is chain3.invoke input. This text is nothing but this piece of text. Question is whatever question you want to ask. Just execute, and it will simply do this for you. Right? Chain3. Yeah. So as you see, the FIFA World Cup took place in Qatar. Thank you for asking. These actually very, very useful because you can have like a nice standard way of querying against these models instead of going into too much detail every time. So, which is why here, if you actually look at it, what we did in the OpenAI example is exactly the same. So we took the prompt template. You can take any prompt template. You can either take a prompt template or you can go for a chat prompt template as well, depending upon how you've set it up. In this case, you're going for a simple prompt template. And I'm defined this template with two variables, context and question. And I'm simply saying, hey, custom rag prompt dot invoke, and I'm passing the context and I'm passing the question, and I'm simply extracting the response. Here's the response, right? The only thing here, and something that I would specifically do, which I think is not what I wanted to do here, that's the small change I'm going to make here, which is just a second, let me just import the LLM chain. It's core only, no? Did I miss something? Dot chains, sorry. Dot chains, import LLM chain. So one thing I should have done here, which I think I made a mistake, is I should have simply said, I've defined the prompt template, of course. Rag chain is LLM chain of, and I can pass the LLM as nothing but the LLM, and then the prompt is nothing but this prompt template. Template is this template. Once this is done, what went wrong? Hey, did I make a small mistake somewhere? Times the that was the mistake. Dot. Yeah, so I should have had it defined as input variables, and that's the template, and that's the prompt, the template, and so this question, and this is context. Where did I make a mistake? Ensure you only answer based on the information that's available. Context and question. Template is template. Prompt template, context question. Sorry. Oh, okay, there you go. That's it. So that's the tip prompt. And then now I have the RAG chain. I can simply say RAG chain.invoke. And there you go. That's it. That's the response. Sorry about that. So this is of text. That's the response. So essentially the same thing, but just doing it exactly the way we've done earlier, right? Just putting it, wrapping it as a prompt template, and creating the chain, and then invoking with the context and the question. Clear, everyone? Is this clear? Can we use a different model instead of GPT? Of course, yes. You can use a different one. You can use a GPT 4o mini. And I don't think the answer is going to be different though. Slightly different. There you go. It's much more crisper. You can use a different model, of course, one history. So we understand how prompt templates work in LangChain. We understand how to do RAG using LangChain. Now, what I'm going to introduce you all to is a bit of an interesting sort of a setup. So let me actually show you. So I'm going to talk about specific prompting templates, prompting techniques rather. So one of the most, you would have heard, right, at the beginning of 2024, later parts of 2023, there's this whole hue and cry about saying, you know what, prompt engineering is the next big thing. Prompt engineering is the next big job. Well, actually, they're not completely they were not completely incorrect. There was a time where I felt, prompting is very good, is the most important thing. And then I later realized, prompting is super easy. Now I realize that's actually not that easy. Right? So writing the right prompts and structuring the complete notebooks and engineering the solutions is not easy, right? It might seem trivial. It's like just asking a machine to do what you need to do, but you need to also structure your complete code in a way for it to do all of these things. Meaning you need to tie the right chains together so that you can get them to do multiple things in parallel. So what I'm going to show you is I'm going to show you some interesting setup here. So there are 2 to 3 types of prompting techniques which are very, very popular. One is referred to as a few shot learning, and the other chain of thought. These are actually very popular prompting techniques, actually techniques that are often used or very frequently used these days. There are other techniques as well, like tree of thought, and so on and so forth. There are like a bunch of different techniques as well. But I want to focus on like a couple of prompting techniques over here. Right. The first one, let me quickly show you. What do you mean by the way a prompting technique? See, the way you ask a certain question matters quite a bit, right? So how you ask a certain question significantly matters, because you will then know how to get a few things done using these models. So for example, you want, let's say, let's say you want to use a very good example, right? A very common use of these large language models. I'll tell you one very, very common utility, how a lot of companies are using these models. So a lot of these companies are using your large language models to do social responding. What do I mean by this? So if you look at, for example, your Twitter or X, or Facebook, and so on and so forth, or Insta for that matter, lot of these companies have their social media handles, right? And they actually engage with their customers or consumers very, very actively on either Twitter, Facebook, or Instagram. But imagine, and actually today, to be able to respond back to these questions is not easy, right? So there's actually somebody who's manually sitting here at all times and then actually responding back to those tweets, or responding back to, let's say, some kind of comments that are being made against your handle, and so on and so forth. But that's complex, right? Point is that is in a way, you're using human labor to just kind of respond back to questions. LLMs are very good with language. So what a lot of the companies are saying is, hey, look, I'll get this guy to sit, but this guy doesn't have to write anymore. I'll get the LLMs to write for me. I'll get GenAI to write for me. All that this guy has to say is yes or no, or maybe regenerate. Worst case, this guy may have to write, but otherwise, all that this person has to do is yes, no, or regenerate. That's kind of cool. This guy's job basically got an upgrade. Well, 4 or 5 of other of his colleagues have just lost their job as well because of this, right? So point is, how do you do that? So a good case in point is, you can now start listing down all the instructions of how this should respond, how it should look, how the quality of the response should look like, how many words it should have, what it should do, what it should not do, how should the tonality be, and so on and so forth. You can write like a laundry list of instructions, but that's going to be very of course you can write it, some instructions for sure you can definitely write, but after that it becomes very complex, right? So the best way to do it is, you give a few instructions, but along with the instructions you also give some examples of how the response should look like, right? You just give it a few examples. That's it. Your LLM actually can learn from these examples. So this form of passing these examples is referred to as few shot learning, or FSL, very popularly referred to as FSL, few shot learning. A few shot learning is simply a prompting technique where you also pass a certain set of examples on how a particular question has to be answered. That's it. So let me show you that in action. So let's take this for example. This is a regular, regular prompting stuff. But here, a few shot learning. You're a very useful assistant. You're good at classifying tweets into positive, negative, neutral. Here are some examples of how the classification could be done. And I'm saying, hey, look, tweet. This is a tweet. This is a sentiment. Tweet, sentiment. Tweet, sentiment. Right? And then I'm saying, hey, look, take the human input question, and then respond back. Right? Input, classify the following tweet. Actually, I would simply put this here. Any of the tweets passed as input. That's it. And all that I simply have to do is now here, as you can see, I'm saying, hey, this is the tweet and this is the response, tweet and response, tweet and response. I'm passing this is the tweet. Let's see what it does. Set it up, model, and let's go. Let's execute. There you go. That's the response. So this is the question. This is the sentiment. Look what it did. The tweet and the response. Cool, right? So it actually transferred that complete style here. Basically picked up that complete style and it transferred the response style here. Do you understand? So I don't have to exactly tell it how it should look like. I just pass a couple of examples and I say, hey, look, just respond back based on this. And it simply did this for me. If you want, you can also pass each of these as variables, or maybe a list of this as a variable. This also can be a variable, right? And what that would do is it would make it super easy. Then that also becomes a, then the examples also can then become a variable. So basis every question, you can also decide what examples to pass. Okay, let's go on. The other very common prompting technique is called as chain of thought. What do you mean by chain of thought? Well, again, very simple. Chain of thought is where you are actually asking your large language model to break down its thought process, right? More often than not, what happens is these LLMs, when you simply ask them a question, they may or may not do a good job. They actually screw it up at times. But when you actually ask it to think step by step and break down the process and show you the chain of thought, they actually tend to do much better. So look at this example. Let me actually. So here's a simple question and saying, hey, you're good at math, and I'm asking it to respond back to this particular question. So instead of all the LLM chain and everything, let me just quickly show this to you. There you go. And I'm simply asking it to respond back. So I'm simply asking it to respond back to this particular question. I'm saying, hey, solve the following questions. And then I can simply say response dot so here you go. it gave me like a bunch of steps over here that it was able to answer this particular question. What I could also do is I can actually very categorically talk about how to solve for this. So this is it kind of gave me these responses over here. As you can see here, what I've done is, by the way, I don't know if the answer to this particular question is right or wrong. We can quickly verify though. What's the answer to this? 65. So it look at it, kind of responded back only a part of it. It didn't respond the rest of it, which is kind of weird. First of all, I don't know why that's the case. It only responded to one part of it. But even otherwise, if you look at it here, X is 65.26, which is not bad. I think that number matches here, 65.26. The first time it actually didn't respond back to the Y at all, as you can see here. It only did, I mean, it gave you step by step, but it failed to respond back to what the other one is. Now here, I'm simply saying, hey, you're an assistant that's very good at math. Break down the problem into multiple substeps, ensure every substep is perfectly validated and the response is appropriate. Only proceed to the next step once the previous step is complete. And now I've specifically asked it to break it down into few steps. And there you go. So now if you see, scrollable element. So it broke it down. It of course answered what X is, and then it also solved for what Y is. It gave me a complete response. So in this case, actually not a massive difference. But what it was definitely able to do is it was able to break down this complete question. And this is actually pretty good, especially with math. Is it was able to nicely break down this particular question into multiple substeps, and it was able to answer. Now, just mind you, it's always recommended to make sure that when you're solving specific math problems using large language models, you always get them to think like this, right? Because if you simply just ask them to solve problems, right? You don't know if they are actually capable of solving those or not. So look at this. It tried to solve for something, but nothing came out of it. Right. Let's go back here. Let me just. What model is this using? Turbo Instruct. Not sure what model this one is using though. I think the default model is. I don't know what the default model is. So here. Let me just go back here. I think it. Yeah. Not sure what model this is using here though. But anyways, the point is, I mean, it tried to respond back, of course, but it kind of failed and failed miserably. And simply saying, hey, solve for X and Y. At times it works, at times it doesn't. And that's the problem that we will have with, see, it kind of now gave me a very different response. It sort of tried to solve for it. It gave me the right value of X. And now it's actually going in, trying to solve for Y. Sort of went back into circles over here. Or actually did it solve for it 6.842 and X is 65.263, which I think is appropriate. I don't think is incorrect. The point that I'm trying to get at is, look, you might specifically always force it to do it this way, and that is essentially referred to as chain of thought, right? So you're forcibly asking it to express to you how it needs to go about answering specific questions, and that is how the chain of thought prompting sort of works as well. Right, let me also give you a very interesting example. So for example, especially when you have reasoning based questions, these these algorithms, they also sort of tend to make an error. Let's take, for example, this is a very good example of why I think prompting, chain of thought prompting works. Let me show this to you. See, this is a very good example why chain of thought prompting works. So if you look here, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So he already has 5. He's bought 2 more cans of tennis balls. Each has 3 tennis balls. So 6. The answer is 11. So this is good. If you look at this one, the cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples would they have? It says 27, which is inaccurate. If they used 20 to make lunch, which means they were left with 3, and then it has 6. So 6 plus 3 should have been 9. But it says the answer is 27, so it kind of screwed up here. However, if you say, hey, look, use chain of thought prompting, what I'm doing is I'm actually showing it how to actually break this particular question down. I'm specifically telling it, hey, look, take the question, think of how you need to answer this particular question rather than just simply saying what the answer is. So when you're when you're providing the responses, actually show it how you should get to the final answer. That way it knows how to think about. So the second time when you actually provide the right kind of prompt with the question, it can actually come back with the right answer. Do you understand what I'm saying? So you need to embed this part into the prompt itself. So you need to do chain of thought prompting, not just by telling it you need to think the right way, but rather what you need to think of is you need to kind of get it to prompt it in a certain way. You need to ensure that these examples sit as a few short examples in the in the prompting itself. Okay. So here is also like another way to solve for it, right? So you're an assistant that's very good at solving math problems. You provide it, hey, here's a problem, multiply the first equation with 2 on both sides to have a common multiple for y. So you're actually showing it how to solve the problem. Step 2, adding both the equations. Step 3, substitute, final answer, whatever. And then I ask it to run this. So any question, it tries to answer back in the same exact fashion. Hopefully this is, and I think it's inaccurate there. So my point is, if you get it to answer a certain way, then they are more often than not likely to get it right? I'll give you a good example here and see what has happened here. My prompt got it to operate a certain way. Let's see what it did here. Did it respond back? No, look, it screwed it up. So what I did here was I said, hey, multiply the first equation with 2 on both sides. So 2x plus 2y is equal to 20 and x minus 2y is equal to 5. And then I added both these equations because I had 2y on both sides. So I ended up getting what, 3x equal to 25, x is 8.33. I took the 8.33, I put it back here, and I was able to solve for this. Now I asked the LLM to actually solve the same way, and it actually did to its benefit. Multiply the second equation with 5 on the first equation by 3. Second equation with 5, first equation by 3. So to its actually benefit, actually did the right thing, but it ended up trying to equate both of these. Somehow it added both of the equations and it landed with 40y. 40y is right, but I don't know how it ended up with getting rid of the 15x and the 10x. So it did the right thing. It did exactly what I wanted to do, but it did it the wrong way because I kind of skipped one step. I didn't exactly tell it why I added both of these equations. So it sort of went in an incorrect direction here. But as you can see, it exactly followed what I asked it to do. I gave it an instruction and I said, hey, look, only proceed to the next step. And I'm saying, hey, look, this is the process that you need to follow. Maybe I need to give it one more example over here. Right. So if I did the same thing, imagine I did the same thing but slightly differently, it would have been absolutely fine. So imagine multiply the first equation. Instead of multiplying the first equation, I simply say as the here I say check if x or y, if the coefficients of x or y in both of these equations are same. Response yes, it is same for x. And then I say, let's subtract both of these equations. If the answer was no, then I would have had to multiply. So here is where I am. A common number. Right. So equation 1 is x plus y is equal to 10. Subtracting both the equations, response done, and I would have had how much? 3y is equal to 5, and y would have been 1.66. Step 4, substitute y in one of the previous equations. So x plus 1.66 is equal to 10. So x is equal to